Good morning, everybody, and welcome to the third annual meeting for developers and users of SU2. So, very warm welcome at the University of Strathclyde that this year is acting as the host of this meeting. So, first of all, I would like to offer a very big thank to Juan, Tom, and all our people from the SU2 community for having agreed to have Strathclyde as the host. I think that this is an honor for us to have all of you here and to have the possibility to host this important meeting for this very important code, because now it's growing big with a lot of interest all around the world. So today we have a very long day. Apologies for this, but the agenda is quite interesting. We have a lot of talks from a lot of people. And I would not like to take too much time, but what I would like to do is just to offer a couple of instructions just for practical items. The first one is related to security. So you have two emergency exits, one on your left, the other one is the door. Exactly. We don't have life vests, fortunately. Unfortunately. Even if, given the weather, might be coming handy. So there is no fire drill or fire exercise today. So in case you hear an alarm going on, it's real. So please follow the signs of the exit doors. For the rest, I think that everything is okay. I'm here to help you with any other practical item. So again, very warm welcome, and help me introduce Juan that will give the first overview with Tom. Thank you.
Thank you. Well, thank you, Marco. But you know, if we are thanking people, I think in this very particular occasion, the third annual meeting for SU2, we really have to thank Professor Marco Fossati here from the University of Strathclyde, because he's been the one doing all the groundwork to get everything organized, and so you guys have all the proper setup, the drinks, the food, and anything else that may come up. So I really would like to thank Marco, and please help me and join me in giving him a round of applause. So thank you, Marco. So it's great to be here at the University of Strathclyde. This is a wonderful venue, the Scottish Innovation and Insight Institute. So if you notice, the acronym is SII, and it's no design of ours, but it's really SU2, the room as well, and that's what it's actually called. So thank you again for setting this up, but welcome again. And as you know, we started this tradition of having an annual meeting, which initially was mainly just for developers joining us here and also online, but we are beginning to expand it to more users who are participating in both listening into the presentations, but also in presenting some of the work that's been done by users themselves. So Tom and I are going to do just the little bit of an introduction, but perhaps before I show you that introduction, it's probably worthwhile to put up the agenda again, so you know more or less what to expect this entire day. We're starting at around 8 o'clock this morning here in Glasgow time, and we're going to have essentially a full day of presentations, single session, one after the other, going all the way till about 4:30 to 5, depending on how well we can actually keep to the schedule. We've scheduled every talk to be 30 minutes, but we did want to have some amount of time for question and answer, so we're not expecting all the speakers to actually spend 30 minutes talking. So please feel free to think about questions and then present them to the speakers at the end of the presentation. And then we'll have some scheduled breaks. For those of you who are online, we will sort of just continue the webinar going, and we'll just be having some coffee over here, but we'll try to come back at scheduled times. And remember, for some of you who are watching around the world right now, it's an 8-hour difference with California and an even larger difference with some other places in the world. So I imagine some people are staying up very late or very early. So let me get started and just tell you a little bit about what's been going on in SU2 for this last year. I'll give the first half of this presentation, and Tom Economon is actually going to give the second half. So welcome all, developers and users, but mostly developers. The tradition did start 2 years ago, and our friends from TU Delft were kind enough to host that meeting, and you have all those and some men. We need more women in the SU2 group. This is a glaring thing, but that was the first meeting that we had that was such a success that we decided to do it again. And unfortunately, last year we forgot to take a picture until everybody had left. So this was in Stanford, the second annual meeting. And of course, Strathclyde is now the third annual meeting. And I think we're getting into the habit of cycling these meetings between Europe and the US. We'll see where it is held next year at around this time. So. The last list of registrations are broken up into different categories. If you're curious, on the very left, you can actually see that there is a number of people that have come from academia, then also people from industry and government, and students. I guess the industry, student, and academia category tends to dominate. These are self-described as in the registration, and then some other category, and only a few people from government. Turns out that we have people who are quite experienced in CFD, and that's not unusual given that we're talking about mainly a developers meeting or conference. But more than half of the people have more than 5 years of experience using CFD in general. A bunch of people are just new to CFD and they're sort of trying to learn this, less than 1 year, but the majority have at least 2 or more years of experience. And then as you can see there, it's fairly even in the rightmost pie chart, fairly even between developers and users, and then some people who are curious about SU2, have heard about SU2, but have never used it and are trying to learn about SU2. So welcome all, I guess. I don't think I have to tell this audience what SU2 is, but I think for completeness, for those of you who do not know very much about SU2, it is an open source, and we stress open source, software package, and it also stressed in the slides that it's supposed to be not just CFD, although it began in CFD, but really a multi-physics analysis and design. That's what we think distinguishes us, is the fact that we are using the codes not just for analysis, but that we produce sensitivity so you can use in design optimization. So gradients or sensitivities are always available, and we intend to make every capability that's available for analysis to have its counterpart in sensitivity analysis. In addition to being a tool, we also think of SU2 as a research platform for CFD, multi-physics, adjoint methods, and many other things that people are coming up with. And hopefully you're going to be seeing a sampling of all the things that we do. So it's this dual nature of SU2 that I think makes it unique. The fact that it can be used for many things, but the fact that it can serve as a platform for doing research that then can be transitioned to use for realistic problems. So the code is hopefully, I don't know if everybody agrees, but well set up for reusing, reading, and coming up to speed, but also porting to different platforms and starting new efforts. So, as always, open source, it's what we're about, and it's always going to remain open source, and we are releasing all of the versions of SU2 since at least 3 or 4 years ago under the LGPL 2.1 license. So C++, MPI, a few external dependencies, a lot of Python as well in order to make things in development easier, and we're hoping that the code is significantly well done to be scalable to large computing resources. So a bit of history, and you'll see the timeline that Tom is going to show you, but the first version was released in January 2012. So we're maturing quickly, I would say. We're now almost 7 years from the initial release of SU2. And as you can see, we've gotten into the habit of that says version O, which should be version 6.0, released in February of 2018. So you can see we've been getting in the habit of releasing a version every year, and you know where to go if you want to get some of these things. All these slides will actually be recorded and posted on the web afterwards, so those watching that need to take notes don't need to take any notes, really. So I like to always put up the slide, and I put it up last year, just to remind you that across the world, people have a fairly good consensus of where things need to be going in CFD. And in CFD as part of multidisciplinary analysis or multi-physics analysis capabilities. So about 3 years ago, a study led by Boeing and sponsored by NASA was published called the CFD Vision 2030. I encourage you to go and look at the report online if you're interested. But the bottom line of the entire, I think, 60, 70-page report is that a certain number of things were found to be critical in order for CFD to continue to have an impact on both research and industrial applications. And you can read the things as well as I can, but the emphasis on predictive physical modeling is there. managing errors and uncertainties is there, automation in all the steps of the analysis and design processes, using the capabilities of exascale computing that is coming along, and then making sure that CFD integrates seamlessly with other physics into multidisciplinary, multiphysics types of situations. So I'd like to highlight that our project, SU2, actually tackles each and every one of those main 6 elements or 5 elements that were actually being described in the Vision 2030 CFD report. And I'd like to remind those of you who are not familiar with that report, that report and the content of it was arrived at from worldwide consensus through a series of workshops that were held here in the US, well, not here in the US, but in the US, and where everybody around the world who is essentially a researcher, a developer, a user of CFD had significant input, both from the industrial side and from the academic and government side. So SU2 is very well aligned with that effort. The team of development keeps growing. So we like to put this little animation, and we have to shorten how quickly we animate each of the various different institutions, because everybody who is doing something in terms of development or helping develop SU2 is actually listed there, and a few more that are doing things but are not ready to be listed just yet. So the family keeps growing, and it's really exciting to see how many people from all walks of lives are actually making significant contributions to SU2. I'll just finish with 2 slides and turn it over to Tom to tell you that a lot of interesting things go on. And I do this from my own perspective at Stanford, but of course the community is so much larger. So you know, about 9 months ago, some of the students who were here and the Stanford group participated in an Airbus-sponsored workshop in order to design strut-braced wings. And we use SU2 for that. And a new geometry is being produced as we speak for the second Padre workshop that will be held sometime in March or April of this coming year. The timeline is being decided. So in theirs, the SU2 team was actually working together with people from NASA, people from various different countries around the world who were tackling the same type of design and flow control tools, mainly the reduction of drag due to the interference at the wing strut intersection of these very high span types of airplanes. So we were working together with many different countries around the world and sharing results. So that was quite exciting. You'll hear today a presentation from the adaptation library from INRIA AMG, and you'll hear an announcement from the INRIA folks for integrating much more closely mesh adaptation with SU2. At Stanford, we continue to work on uncertainty quantification. You'll hear a presentation today, but the work is much broader than that, and it's relying on SU2 and the structural and thermal solvers to do aerostructural thermal analysis, optimization, and design under uncertainty with uncertainty quantification for nozzle flows on aircraft of the kind of the X-47B that you see there. And we've recently also just received a new grant from NASA that's about to start, so it'll be a 3-year project in order to improve the linear solvers inside of SU2 so they're scalable to exascale architecture. So there's a lot going on. This is only, as I say, a sampling. In fact, there have been discussions with members of the industry that continue from all sides. We're talking to Lawrence Livermore National Labs in order to try to use their algebraic multigrid solver as a preconditioner and see how well it works. NASA is thinking of putting a framework together that they call T-infinity. They made a presentation at the aviation conference in June, and they're sort of discussing with us to see if SU2 could be part of that, the T-infinity framework, as they call it. Conversations with NVIDIA are just beginning. Pointwise and TechPlot have been wonderful partners, and they continue to be. And TechPlot is actually putting together the SZIL, as they call it, or the Zapzone load on demand. So this is sort of a parallel visualization capability that's now integrated with SU2. We're collaborating with new companies like Innova, and we're in the process of final preparations for the SU2 Foundation. So all of this is going on, and it's only a subset from my own vantage point. Tom is going to tell you about a few other things. And we're going to sort of continue along the entire day, giving you more details about, I think, 13 additional presentations that are going to go more deeply into the technical details. So I'm going to turn it over to Tom so he can actually start telling you a little bit more about what's happened with the code base and where we're going with version 7. So,
okay, thanks, Juan. So this is always quite a joy. I really enjoy this part over the past couple of years, so I'm pleased to share again. We always like to start with our timeline. Some of you have seen this a few times, but I'm going to animate it for you just for you to enjoy. sort of the history of the project, and then we'll come to the present day. Okay, so that brings us to today. I think maybe next year we're going to have to shorten the amount of time between the slides. It's starting to get too long, right? But I hope you see that it's a rich history, and we have a lot of great collaborators in the room, so I'll skip all the pleasantries. Juan and Mark already gave you a nice welcome, so thanks for being here. This is 2018. I can only, of course, highlight a handful of things, but I put a few important ones up there that I just wanted to share with you, remind you of what's been going on. So early this year, we released version 6.0. And along with that, we had a couple big exciting changes. We had an overhaul of the website. We had a new concept for the Developers Society that came along. Later in the year, in the summer, we put out version 6.1. And then you see here we are today for the third annual meeting. And yesterday, we had our first official hackathon. And so I have some pictures and a couple things to share from that. So you may have noticed if you go to our project homepage now at GitHub, we finally have a beautiful modern looking website. So we're very pleased with this change. And I guess folks who are online, if you need any information, it's live, it's linked there right now. If you go to the page, if you need any of the information about today, like the agenda, the links are updated. You can find everything there for today. Another concept that came along is we've been working on ideas for how we can really engage with the developers community, and how we can make sure that developers are able to discuss with each other what's going on in the code, how they can collaborate. And so this is the concept of the International Developers Society. So there's a link off the main page to this. We encourage anybody out there who's really working with the code, who wants to maybe connect with the fellow developers and get to know what's going on. This is a mechanism for that. And you're going to hear a lot more about it today. There's a presentation at the end of the day by a couple of the developers here who are going to tell you all about the philosophy and what it's all about. Okay, so where are we today? I like to keep this slide and sort of just update the numbers. So the background is a nice picture of a map where we have the most hits on our website. But then the typical things here. So we still have a little over 10,000 email addresses on our users list. The repository is being visited about 5,000 times every 2 weeks, cloned 500 times every 2 weeks. And the number I always like to watch the most closely is the number of active forks on GitHub, because for me, this is a proxy for developers. And I really like to see that number increasing. So that's very encouraging to me. This number keeps going up, and I think that's a great thing for the project. Okay, I only have a few minutes, but just a couple more hard numbers, because I think these things are kind of fun to see how much progress we're making. So we're coming up on 7 years, by the way. So next January 19th will be 7 year. And so we'll, of course, probably be putting out something for version 7 around that time. That's our typical habit. So this year, so far, only in September, we have a few more months. We've completed 51 pull requests. So these are us pulling code into the repository from developers and folks around the world. We have 455 commits now sitting in our develop branch. So basically, above the current or the past release since version 6, ready to go out in the next release. We're sitting at around 228,000 lines of C and C++ code in version 6.1. We have over 200 regression tests that are running at any given time, continuous integration tests, protecting our code and making sure everything is working okay. We have over 150 branches right now in the repository, so this gives you a feel for how many branches there are out in the wild of people developing new things and adding new capability. And again, there are over 360 active forks now on GitHub. So again, proxy for developers. We like to see that number increase. So yesterday we had our hackathon, and I just wanted to say briefly that we have a very well-defined developers process. And the way this works is we start with our branching model. We move into development phases, we make commits, we work with regression testing to make sure that everything is working as we expect and not broken. We are able to do pull requests, which is our mechanism for pulling contributions in from the community. And then those get reviewed, they get regression tested, and then eventually they get merged. And there's so much more to this. I don't have time to talk much about it, but if you want to know all the dirty details about how to be a developer, we will post the slides from yesterday. There was a 1-hour tutorial on everything you need to know how to get started, from Git to branching to pull requests to regression tests, everything. So please check that out. That'll be posted for you. And so yesterday was quite a day. I think it was a smashing success. We came together and the idea was to split into small groups and have problems that people could work on in those groups. And at the end of the day, have tangible output. So at the beginning, we defined a few problems. Here they are on a slide. I took some pictures showing that we had 7 challenges that different groups broke out to work on. There was a lot of good conversation around the room in different places, so people working at whiteboards and people having discussions in the corners. And at the end, we had a nice set of presentations to recap what everybody worked on that day. So I thought it was a great success, as evidenced by the amount of pizza we ate. It's a stack of about, what, 15 boxes or something in the back. So it was very good day, smashing success. So I hope we do this again in the future. Okay, I'm about out of time, but just some pretty pictures to get you excited about today. We have a lot of great topics, as Juan already said. It's all over the place. Juan and Marco introduced talks that go anywhere from acoustics and high-speed flows, non-equilibrium flows, down to incompressible, UQ, mesh adaptation. We really do have a diverse community working on a lot of great topics. So there's something for everybody. Okay, and that pretty much does it. I'll put this back up, but you've already seen it from Juan. So why don't we just keep moving? So let's go ahead and start the next talk officially. Yeah, thanks. Okay, so let's go ahead and start with Marco's going to lead off with the first technical talk today. He's going to give an overview of the NEMO projects. This is a new thing we're working on as a group. It's a large collaboration, as you'll see, and I'll let him give you all the details. So, okay, Marco.
Thank you so much, Tom. Today, I'm here just as a frontman of, as Tom said, a large group of people who have recently joined efforts in order to coordinate a little bit all the various activities and development efforts in the area of making SU2 a code that is capable of addressing a specific range of applications that involve chemistry, thermal non-equilibrium, finite rate chemistry, and these rather complex type of flows. So we call these SU2 NEMO, just to say that NEMO is a nice name because it calls up at the memory of nice adventures under the sea, but also because it's an acronym that fits with non-equilibrium models. So this is the name that we have agreed and that we will use in order to create a brand new branch within SU2 that will carry over this name. As you see, and as we said, there are a lot of people from Strathclyde, people from Stanford, people from Bosch, from TU Delft, from von Karman Institute of Fluid Mechanics, from a spin-off of TU Delft, and we are all contributing a complementary effort towards this activity. Let me start by looking a little bit at what is the rationale, the motivation behind this initiative. The idea is to enhance a class of multi-physics characteristics, the one that I just introduced earlier on, within SU2 and extend the spectrum of application, always keeping a focus and a special eye on the design of aerospace vehicles or the design of engineering, say, devices. And our objectives are summarized here, and we had a couple of meetings with all this group of people. The idea is to define a roadmap of coordinated development. So one of the basics, strengths of SU2 is the fact that the community talks a lot, and therefore we really want that anybody that has an interest in developing and working on these subjects talk to the others, such that we can really avoid any deviation or aspect that may not bring to something effective. We want to incorporate advanced model for finite rate chemistry and thermal equilibrium. I will explain this in a minute later on. We want to consolidate the implementation and the use of this advanced model for, again, a class of applications. And for those of you who might have followed the history of SU2 through the years, we just want to reboot under this new and empowered perspective what have been done already in a couple of years ago in the same specific area. So we want to start from there, but now bring it to a higher level. The group of people that as of now today are interested and are involved into this type of applications and this type of initiative are quickly summarized here. So we have a good group coming from academia, we have von Karman Institute, which is a research institution, and we have industry interested into this. But again, as I indicated in the title, to date, because we really want that this group will expand in order to have the widest audience and the widest advisory and steering committee as possible. On the right, on the left, you see, your right, my left, you see a list of applications. It's not exhaustive, but it's just a list of the main applications that the various people within this group are looking at. We want to be able to do aerothermodynamics of high-Mach regimes, study transition problems with high compressibility effects, with multiphysics in the shock layer and in the boundary layer. We want to address non-ideal gas dynamics of complex fluids, and we will see how this will fit, for example, with other initiatives and other developments that have been discussed in the years. We want to look to be able to address some combustion effects in terms of laminar premixed combustion for domestic heatings and extend it to a general application of industrial process, so combustion within industrial processes. As a matter of fact, we are looking at a very wide range of applications that mainly goes from atmospheric entry, meteor, biomass, pyrolysis. So it's really quite a heterogeneous set of applications. But in the end, as we will see, our idea and our ambition is to find out a polished and unified numerical and mathematical and physical modeling that will be able to allow us covering these elements in a nice and effective manner. So this was a rather short or rather long introduction. So this is the outline that I will be following today. I will start with just a short background. I don't want to give a lecture here. We are at a university and so on, but apologies, I will try to keep it short and sweet, and I will go very quickly. Then I will introduce a couple of libraries that we would like to connect in a seamless fashion, in as much seamless fashion as possible with SU2. And then we will show a couple of examples of some of the applications that we have started already doing and considering within the NEMO group. And then I will just show some ideas of what is the road ahead, so the roadmap of this development. So this will be a presentation that is, let's say, one part showing some of the results and the development that we have been doing in these months, but there's also a strong part that is looking at, okay, where is it that we are going? Where do we want to go? Short mini background about what we're talking about. So this is basically the starting point of our initiative. So we are looking at the classical Navier-Stokes equations written in this conservative form with thermodynamic equations needed for closure, and with the classical approaches, Fourier-based, to compute thermal conductivity and transport properties. So from here, what we want to do is that, okay, we want to address problems that involve chemistry, but in general, the presence of multi-species. So the fact that we might want to have a fluid that is not just air, a fluid that is a general fluid, which can be a composition of an arbitrary set of species. And we want to be able to address the fact that even if we might not have any chemistry going on, so the production and destruction terms in the equations will not be there, we'll still be able to account for the diffusion. So the fact that if we have some gradients of concentration of different species, we might have this phenomenon going on. And already you see that just by taking into account the multi-species elements, we come to the point where we have no longer one single conservation for the mass, but we have n, where n is the arbitrary number of species. We have that the mass conservation equations becomes a little bit more complicated because it's now an advection reaction diffusion equation. So also from a numerical and modeling point of view, that should be treated carefully. And also in terms of the equation of energy, things get a little bit more complicated. The equations of state in terms of thermodynamics, pressure, and energy in this case, again, get a little bit more complicated, and so on. We want to go even farther than this. And for example, if we want to address high-Mach flows and then consider high enthalpy flows where there will be a lot of energy, and the exchange between the various modes that the energy can be stored inside the molecules of the gas is not in equilibrium, we have the possibility to have multiple equations for energy, accounting for the fact that now we no longer have one temperature that is associated to the thermodynamic equilibrium state, but we are to take into account the internal structure of the gas that includes vibrational effects, and we can go on, including electronic effects or vibrational effects. So these equations can become a little bit scary, let's put it this way. But you see that again, playing around with the equations has, of course, an impact on what is then the thermodynamics, the constitutive relations, the transport properties, and so on, and so on. So I will stop here with the equations because I don't want, again, to get too much into it and bore people. But so what we want to do is, as I said earlier, to start from where the original developments of SU2 in this context were. And so there was an initial effort by Sean Copeland, who had his PhD in 2015 at Stanford, who started introducing many formulations, many models, numerical, mathematical, and physical, within SU2 to address this type of flows. And here I will not go through the details of it, but you can see that there have been quite a lot of efforts in trying to really introduce these elements. Eventually, the work of Sean, Juan, and a group of people who worked on this was a very, very good work, because they were able to address a lot of problems with a lot of physics in it. But SU2 has continued and will continue to evolve. So we are now at a position where we consider that it could be worth looking at a more coordinated and more coordinated efforts in a way that we can really have a more general, more powerful implementation of these elements, but even more aspects. So coming back a little bit to the same set of equations that we were discussing earlier, the first aspect that we want to consider is, and that we will consider, is the fact that, again, when we start adding a little bit species and various things, we need the capability to model some aspects. Like, for example, We need to compute diffusivity coefficients of each species. We need to compute production and destruction terms, which means reaction rates coming from, for example, Arrhenius laws or other models. We need to address this also, especially from a thermodynamic point of view, in terms of appropriate equations of state, and so on. And for this, we decided to talk with people who are experts in this area. Among the many, we have been talking with people from von Karman Institute for Fluid Dynamics, and our ambition, sorry, they are looking, but is it looking? Okay, apologies, I will just take a break because if we do not have a good resolution, probably the images will not. Okay. 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 Sorry. Oh, kind of magic. Sorry. So the mutation ++ library is very well developed and rather known library that has a lot of power and capabilities to be able to address elements that I was introducing earlier in terms of reaction rates, computing properties, and the fact that we have been looking at mutation, which is one among the many, is the fact that we have a direct connection with the core developers of this. So people from von Karman are the developers of this library, and therefore this will again open the let's say an extremely high bandwidth channel of communication with them. Mutation ++ is open source, so it fits nicely within the SU2 approach and philosophy, and we already have started creating a strong and consistent link with this type of library, with some of the examples that I will show you later on. Another library that it is under consideration is Cantera, which is quite a popular library for what is the thermochemical modeling of species and reacting flows. It's very widely used in the industrial community, also in the academia. We are not so sure that we're gonna go with Cantera, mainly because we do not have an equivalent channel of communication with the developers, but it is under consideration because we really want to have a formulation with an interface that will be the most general yet efficient as possible with this type of libraries. Coming back very quickly again to the basis set of equations that we want to consider. Again, it's not exhaustive, it's just an example. One further step that we want to consider is thermodynamics. So when it comes to defining equations of state for our fluid, for our gas, we want to be able to address a wide range of applications, as we were mentioning earlier, and therefore there might be the necessity to change and to have the possibility to choose an equation of state that is not simply the perfect ideal gas, because that might not work in all the cases. And this is where we have the other group from TU Delft that is bringing to the table and to the discussion this other library, which is called the Fluid Prop, which is another very powerful, very strong library with a lot of validation of all its methods and capabilities. And this library will become the reference library for what are the thermodynamic modeling of the NEMO branch, because this will allow, thanks to Fluid Prop, we will have the possibility to take into consideration other equations of state, for example, for pressure like Van der Waals, Peng-Robinson, and more advanced models for it. One interesting aspect of this library is the fact that we have, again, a high bandwidth channel with the developers who are sitting here Theo, Piero, Alberto has also collaborated on this, is that it is now working, there is now a lot of efforts in trying to make it as much efficient as possible. And so there is this initiative, and there will be some slides and some discussion later on, by trying to have these highly complex models for the thermodynamics available in the form of lookup tables, but in the form that still the accuracy with respect to a standard calculation, which will require much more time, will be very, very effective. So let's start exactly by showing some of the examples that we have already started working with, specifically in the case of using mutation fluid prop. So this is a nozzle flow, is a shock-induced nozzle flow where we have a very complex fluid, siloxane MM. We have some details about the methods, the numerical methods, and the turbulence. And this is something that has a very strong backup thanks to our colleagues at Delft in terms of their ORCID facilities. So the possibility to have, again, numerical tests and actual tests in experimental facilities is a strong drive, because will allow us to really have a first hand on the experimental validation and verification of all these models. Same, it comes when it's the same. It's true when it comes to turbomachinery. So turbomachinery with rather complex fluids. Again, some of the work that people in Delft and in Milano have been doing. And in this case, you can see a couple of images of the application of SU2 with fluid prop in resolving the flow on a stator vane of a turbine, of a mini turbine that they have in Delft. And with specific reference to this, what we're looking here is what I was mentioning earlier. So the comparison between the standard approach in introducing these complex thermodynamics models and the lookup table approach. In terms of accuracy, it's basically the same. You saw it earlier. And in terms of CPU time, you can see here a comparison between a perfect ideal gas, a complex thermodynamic model without lookup table, and the same complex thermodynamic model with a lookup table. And you can see here that in terms of computational cost, mainly the lookup table is behaving the same as a perfect ideal gas, without sacrificing anything in terms of the accuracy. External aerodynamics. Then we look at other applications where we are considering the link with the other library, which is mutation++. At this point, we are not dealing yet with chemically reactive flows, but still we have all the machinery in place. This is a standard test case. Apologies for the bad resolution of these plots. I hope that we will have a better one. And here you can see the Mach 7.11 flow over a double ramp, and you can see that the moment the animation at the top gets still is the moment where we took a screenshot and we did the numerical Schlieren for this flow. And here on the left part, you can see a comparison between two different models, one which is looking at a constant CP, so calorically ideal, calorically perfect model, and one where instead we are leaving it changing as a function of temperature. Another test case, again, in the supersonic flow, external aerodynamics, is the analysis of the interaction between an oblique shock wave and a bow shock wave that is forming over a cylinder. This is another canonical test case that has been provided in literature with a very identifiable interference pattern among the shock waves. And again, the problem is not steady. As you can see, there is short oscillations of the jet that is created as a consequence. Here you have a supersonic jet is created as a result of the interaction of the two oblique and bow shock waves. And here on the bottom part, we have a comparison between the time average values of pressure and shear stress, all normalized, compared to experimental experimental data. Very last example in terms of external aerodynamics is a 3D example, a little bit more fancy for what is the visualization. So we have the shockwave pattern interaction. So similar, let's say, type of problem that you saw in the previous example, but now this is in a 3D case, and it shows when it could be, it could happen. And we have two proximal bodies that are flowing at Mach 10. And for example, this is the case when you have either a satellite that is re-entering the atmosphere, and then some pieces of it breaks off, and then you have a big body and then a chunk of it that are moving, and then you see the interaction of the two. Oops, sorry. So just to conclude a little bit of what is the road ahead. The road ahead is to cover and touch quite a long list of elements and items that are all instrumental to the vision that we have, vision and objectives that we have introduced earlier. And these elements have been part of the discussion that we had yesterday during the hackathon, because we had a specific hackathon problem looking at how we should start in a collaborative and coordinated fashion working on this. And the first step that you will see soon is that we will be creating a new branch within the developers branch of SU2 that will bear the name NEMO, and that will be the merging of current branches, including SU2, branches including fluid prop and the lookup table, and the branch that was the original Sean Copeland branch, in order to really find the good starting basis to move forward to more complex numerical, physical models, and eventually applications. So thank you very much for your attention. Apologies for the resolution of the screen. I don't know how to fix it. Happy to take any questions.
So we do have some time for questions for Marco.
The lecture thing didn't work, you see.
I was going to say, Marco, is the focus on multiple applications, so high-speed flows, reactive flows, flows with more complex physics, I guess, physical properties. The idea is to combine it all in order to make a single solver within the structure of SU2, and why is that the reason to combine them?
Yeah. So thank you for this. I forgot to mention. So one of the elements that we discussed yesterday during the hackathon was really, okay, how do we tackle the problem of having those multiple equations for mass and then multiple equations for energy? So the idea is to start with one new solver within the SU2 class of solvers, where we have Euler, we have Navier-Stokes, and so on. And the idea is really to try to have a lean and smart and efficient place where people can go and work on it in a way to avoid problems, for example, in terms of convergence. If we want to segregate the solution of the species equations and the rest, we might incur in some convergence issues and numerical issues, because we're going to have rather stiff source terms when it comes to external aerodynamics, high speed, and so on. And we want really to facilitate as much as possible the numerical convergence and numerical aspect. And also, we want to be able to have into one single coordinated solver all these models converging into it. This was one of the
I have a very probably narrow perspective on the whole scope of NEMO. And of course, I participated to the initial discussions. What I wonder is if there was an in-depth reflection about combining so many different types of physics. And let me be clearer here. I do have some experience with software development, though I never went into these details. There is always a compromise to be taken between generality and in the end, portability, respect to development, maintenance, and so forth. Has there been a thorough discussion? Because you can decide, instead of having one overarching interface for all these problems, you have separate that live somehow separate from each other, but still that can be a possibility. And maybe I'm bringing to the extremes the two options.
Yeah, no, that is a very crucial point. So we had a discussion yesterday during the hackathon. I wouldn't call it a thorough discussion, but we started having a discussion on where is it that we want to put our lines in terms of want to be very general, so solve everything, not always a very good approach, or we want really to be extremely focused and extremely specialized. This is something that we started discussing, and as you said, it's not trivial to find the right balance between where you want to sit in this range of.
So we're still in the discussion. Right?
We are exactly still in the discussion, and again, what it is my commitment and my duty, my action is that I'm gonna prepare a few elements for the discussion in our, let's say, separate let's say gatherings, in order to really dig into all these aspects. And we have to do it now, because again, we're just starting, okay? And all the decisions that you make at the very initial design phases of everything have a huge impact as long as you progress, right? So you need to try to find the best decision. But certainly what you're doing is absolutely fine. And we're exactly discussing yesterday with our friends from Bosch, because they have a very specific and targeted application. Flames, laminar flames premixed with specific models, flamelet models, and so on. Then we say, okay, how do we incorporate this into a more general solver? Do we want to incorporate it? At what level? So I would not call it a thorough discussion, but an initial thorough discussion.
If I may, you and I must be twins separated at birth, because I brought up exactly this point yesterday in our hackathon discussions, and I think it's an issue, as you said, of generality. And the fact that you can reuse code and efficiency, right? Because putting all these different solvers into one single solver class may actually prevent you from doing certain things to one particular solver or application. So I think we need to think about that very carefully, because even though you may have more code, 3 separate solvers, 2 separate solvers, there may be lots of common things between those solvers that can be reused and properly architected. So I think this deserves a serious look.
Yeah, it's related to what Piero was saying. We had a similar discussion in Stanford when we coded the NICFD solver, and we were like, well, what it is to be decided if this addition is too complex to stay in the core. So is everyone downloading the core, getting also this or not? At the time, since the thermodynamics is of equilibrium type, we decided, okay, it's just a small addition, and it's not in the critical path of SU2. Here I see a huge modification, and yeah, I would like to have your opinion on how you see NEMO like in 2 years. Will it be a separate solver, or will it be downloaded together with the core version of SU2?
Well, this is probably something that we all, as a community, need to discuss. What we want to do is, of course, to avoid breaking up whatever works now. So the point is that it's not that you will be downloading NEMO and that's it. It's not going to work. It's a no way. So the idea is to still have the baseline solver as it is now in the master branch, and then having the possibility to have this separate branch that covers this.
But it's a separate solver class.
I was going to say,
yeah, it's separate solver class.
I see what you mean. You don't want to start shoving everything into the Euler and Navier-Stokes class as we had it. So there are many classes that we will reuse: geometry, linear solvers, anything.
Those are all there, going to get reused. But we can just peel off a completely separate base and child class for solver non-equilibrium, for instance. And that will have its own file, its own class structure, independent. So I think there's a clear path to architecting it in a way that preserves everything.
So you'll download the code for the thermochemical non-equilibrium solver, but that's in a separate class. The RAN solver won't be affected, let's say, with the non-ideal gas solver will not be affected.
So as a very practical example, when in configuration file at the very top, you know that you can choose the solver, then you have Navier-Stokes, Euler, there will be another one that, as Tom said, would be a separate class and will go through its own pattern.
So zero interference and zero. There'll be heavy code reuse, but proper data encapsulation so that they're not stepping on each other or overwriting things.
You will download a few more kilobytes of data. That's because
Maybe another file, another 10,000 lines of code or something.
Any other questions for Marco? Well, let's thank him again. So thank you.
Thank you again.
Okay, thank you, Swan, for the introduction. So, my name is Beishuizen, and I'm from the Bosch Thermotechnology Deventer in the Netherlands. And I will tell you a little bit today about our progress in implementing a framework for combustion in SU2. So, most of the work is actually being done and will be done by Economon and Daniel Meier from the Bosch Research and Technology Center in Sunnyvale in California. And Daniel also made this wonderful animation of the unsteady vortex shedding behind a cylinder, where the vortex shedding is being visualized by a pressure scaler, a fluid tracer, just upstream of the flow. So first I will tell you a little bit about Bosch and the problems that we are interested in before I will show you some first results. So Bosch spends, puts a lot of effort in research and development. And this is all being done by, let's say, it's done in a centralized way in Bosch research centers, which is called corporate research. So there are a number of these research centers all over the world, but the biggest one is in Renningen, close to Stuttgart. In the US, there are 3 research centers. The largest one is is the Research and Technology Center in Sunnyvale in California. So Bosch is really huge. It's now more than 400,000 people. And we are now in 60 countries all over the world with 440 regional subsidiaries. At a very high level, Bosch is divided into 4 business sectors. So there's mobility solutions, so cars, car parts, industrial technology, energy and building technology, and consumer goods. And actually, more than half of what Bosch does is in mobility solutions. So more than half of the revenue of Bosch comes from development of car parts. Now, I'm in the business units thermotechnology, which is part of the energy and building technology business sector. And in Deventer, we are working on residential heating appliances, specifically domestic wall-mounted boilers. So they are used, they basically burn gas, and the heat is used to heat hot water for hot water demand and for heating your house. So just a small introduction. So I have to see. So in the middle picture, here below, left, here on the left and below, you see the gas valve. Now let's start here. So the fan is sucking in air from the environment through this air pipe, and this then enters venturi just below this fan. And this venturi creates an under pressure, and this under pressure will then open this gas valve, which allows gas to enter the system. This is basically a safety system. So if the fan is broken or if there is some problem with sucking in the air, then there will not be any gas entering the system. So the gas and air are then pre-mixed in the fan and in the burner housing. And in the top right picture, we see a cross cuts through the appliance. And just below that, a zoom of the burner plate in gold. So air flows from top to bottom through the burner. It's at this stage completely pre-mixed. It's then being ignited by the ignition pins that you see just below the burner. And the combustion products then flow through the heat exchanger downstream of the burner. Through the heat exchanger, there are water channels. The heat is given to the water, and this hot water is then used for hot water demands or for heating your house in the winter. And what is very important for us, besides the thermal efficiency of this appliance, are the emissions. We want, already in a very early stage of the development of these appliances, a good estimate of what the carbon monoxide and nitrogen monoxide emissions will be, because they are bad for the environment. And there are very strict regulations also from by law on the amount of emissions that you are allowed to exhaust by these appliances. So what we do is we simulate a part of this entire appliance. So we usually take a slice from the heat exchanger, and we simulate the combustion and flow and the heat exchange in this slice to assess the performance and to improve our designs. So here we see typical results, not an SU2 results, but we hope that in the near future we can also do this with SU2. So the flow is from left to right, and we see that at the burner, the flames are attached to the burner wall, and downstream of the flame, the hot combustion products are cooled in the heat exchanger, which is a finned heat exchanger. And by the time that the combustion products reach the exit, the temperature has reached about 50, 60 degrees Celsius. What we want to know is typically the thermal efficiency of the system, but also peak temperatures in the solids to prevent deformation or even melting. And we want to know, of course, carbon monoxide and nitrogen monoxide emissions. Now, what kind of combustion models can we use? So of course, if you want to simulate flow, you can solve the Navier-Stokes equations directly, which is sometimes problematic if your Reynolds number is very large. So we have turbulence modeling to cope with that. We have a similar problem in combustion. So combustion can be described by a large number of reactions. For methane air combustion, there is a very well-known reaction mechanism called the GRI mechanism. You can get it from Berkeley. It has 325 reactions. and there are a total of 53 species. And these reactions are nonlinear. They are described by the Arrhenius laws. So if you want to solve combustion in detail, then you have to solve a transport equation for each of these 53 species. And they have reaction source terms that are described by these reactions. So for our applications, or I would say in general, for industrial 3D, CFD simulations, where you actually want to improve your design in a couple of iterations, this is really too expensive. It can take you weeks or months just to simulate this heat exchanger slice that I showed you before. So what kind of modeling approach can we use? So we use, and a lot of people use, a flamelet approach. That will explain you visually what this flamelet approach is. So let's consider an adiabatic flame where no heat losses occur. So either we have a very detailed measurements or a very detailed simulation, because we had a couple of 100,000 of CPU hours to spend on this. So we have this detailed picture of the flame. We're going to look in a point in the flame. And we are going to look at the thermodynamic properties. So what is...
One burning question in the part, excuse my ignorance. You study this problem steady state?
Yes.
Okay.
Yes. We are interested.
You can assume that the flow is...
Yes. We usually assume that the flow is steady. Of course, in practice, sometimes it's unsteady, but we prefer not to have unsteady flows.
Okay.
Yeah. In the flame, so what is the idea of the flamelet approach? Suppose we have detailed information of a real flame. We're going to look in a point in the flame. So we can look at temperature or viscosity or the production and consumption rates of some chemical reaction, and we are going to plot it as a function of a progress variable. So this progress variable says something about the progress of combustion. So if the progress variable is 0, it means progress, there was no combustion yet. If the progress variable has reached its maximum value, then combustion was completed. And in between, it means that we are in the reaction zone. So usually, for instance, CO2 is a progress variable. If CO2 is 0, we're still in the cooled mixture, and if it's maximum, everything good. But you can take any, linear combination of species that basically result in a monotonous increase through the reaction. So what we can do now is we are going to investigate the flame in a lot of points, and we're going to plot, let's say, the temperature as a function of a progress variable. In the adiabatic case, it turns out that they all fall on a single line. So that means, basically, that in progress variable space, the flames are one-dimensional. So they are uniquely described by this, by a one-dimensional flame. Now, if we have heat loss, then it becomes just a little bit more complicated. So the enthalpy is constant in an adiabatic flame. So the result I just showed you is for an adiabatic flame. Now, if you have heat loss, for instance, because the walls are your conjugate heat transfer, the walls are cold, then basically you can do what shall I say? So because the flame is essentially one-dimensional, you can do one-dimensional simulations and store it in a lookup table. And in these one-dimensional simulations, the entropy is constant for each of the one-dimensional simulations. So if you have heat loss, you can just perform a number of one-dimensional simulations, each with a different enthalpy, and you store this collection of flamelets in the lookup table. So what does this look like then? So in practice, what we do is in 3D, so in the, let's say, detailed simulations, the detailed 3D simulations, we solve only a transport equation for the progress variable, and we solve an energy equation, let's say the total entropy equation. In 1D, we solve these detailed reaction equations. It's quite fast, and we solve these detailed reaction equations for a number of 1D problems with different enthalpies, and we store it in a lookup table. Then in our simulations in 3D, we are just going to retrieve the thermodynamic, the chemical properties from the lookup table. So diffusion, density, the production and consumption rates, we all get them from the lookup table. So let's go to SU2. So we discussed also with Marco and the other people about the general framework for solving systems of transport equations of species. And we have started to experiment already a little bit with an implementation where we have a general framework for a system of transport equation of species in a segregated way currently in SU2. And for combustion, we currently have, we did some tests. So we have a framework that can, in principle, be used for finite rate chemistry, non-premixed and premixed combustion. And we, but it takes, of course, a lot of work to implement all of this. So currently, we are doing some tests with a very simple reaction source term, just for laminar premixed planes. It's just the gradient of the progress variable as a source term, just as some do some preliminary test with it. Then we want to get fluid properties. We can get them from different places. So we can have built-in functions. So we have a couple of built-in functions right now. We can add mixing rules to these, such that we can also do multiple species transport and combustion without going to external libraries. But for more complicated problems, we can get the properties from lookup tables or from an external library like Mutation++ or Fluid Pro. This is a bit unclear for you in the audience because the resolution of the screen is a bit low. But these are examples of what it would look like in the config file. So basically, we have our keywords for the fluid model, we have a keyword for the turbulence model, and now we have an additional keyword for the scalar model. In the left, you see an example of a passive scalar transport that you can now set up in SU2, and at the right, you see what it would look like for this very simple premixed combustion model that we have currently implemented. So you just say that the scalar model for premixed combustion is the progress variable, and the source term only depends on the laminar flame speed and the flame temperature. So validation is very important, and actually I think if you do a validation, you should really start with very simple test cases that preferably have analytic solutions or solutions that are really well established. So this is a very simple problem. It's a uniform flow, 1 meter per second, flowing from left to right. We have variable concentration at the inlets. So concentration of 1 for the first 1 meter, and then a concentration of 0 in the rest of the domain. It has a known analytical solution, which is just the error function. So basically, the solution is governed by this by the heat equation, and this problem is set up in such a way that downstream, which is normally the x direction, it's actually equal to time. So we can compare the solution of this simple heat equation with the concentration profiles at several locations downstream of the inlets, and we get a perfect match. We should get a perfect match. It also works for axisymmetric cases. It has a slightly different analytical solution, but you really have to look in detail to see the difference. The spreading rate is slightly different. We also made sure that it works in combination with turbulence. So at our location in Deventer, we mainly have laminar combustion, but you can also imagine that people are interested in turbulent combustion, or maybe even turbulent scalar mixing. So this is a simple turbulent jet, where the jet itself has a different composition than the surrounding co-flow. I just use it with the simple Spallet-Almaraz model. So of course we can do a detailed validation and check the spreading rate that is known from many measurements and simulations. But actually it is known that Spallet-Almaraz is, at least the classic model, is not performing extremely well for this. But it would be interesting to also test this for the ST model, but I haven't had time for that actually. So for combustion, as I said, we have a very simple combustion model currently that we just use to play with and test the basic implementation. We've implemented a laminar version of it, but it's very easy to also extend it to turbulence if you make this, let's say, flame wrinkling. If you implement this flame wrinkling correction in this simple adiabatic flame implementation that we currently have, the temperature is just a linear function of the progress variable. So this is our first test results of a laminar premixed flame in SU2. So it's actually a no chemistry approach. You just get a flame shape and the temperature profile. Temperature is, as I said, a direct function of the progress variable, and density is then computed using a multi-component ideal gas law. And currently the other properties are not coupled yet. You can of course use a modified Sutherland law, for instance, for viscosity, but the more general approach would be to introduce different viscosity laws for the different species that we have, and have a mixing rule for it. One thing to work on still is convergence, which is a point of attention. So we haven't really dived into the adjoint optimization of combustion problems yet, but one of the first things that we would like to do is something that does not involve the implementation of finite rate chemistry and lookup tables. What people do sometimes, so this laminar flame speed that is in the model, it's a very important property. People spend a lot of time on measuring the laminar flame speed accurately. And you can do this with Bunsen burners. They do this by measuring basically the flame angle of this conical flame. And to measure the flame angle accurately, let's say the cone has to be very straight. And we know that this cone is not straight if the velocity profile that comes out of this Bunsen tube is not uniform. So one of the first things that we would do for testing is to modify the shape of this Bunsen tube such that we get a nice uniform velocity profile. So that's the first thing on our list to do with the agenda. So some final words. So we have some basic framework for transported scalars, and we are discussing, of course, with Marco and the other people interested in combustion on how to do the exact implementation of the framework and what to generalize and what to make specific. We will start soon also on the lookup table approach. It's in collaboration actually with TU Delft. And besides just implementing all the models, it's also very important to look at convergence. So there has been some efforts on implementing artificial compressibility method and extending it also to this progress variable approach. And actually, the current version of this code is available on GitHub in the branch feature scalar. So if you want to play around with the codes that has some capabilities for transported scalars, you can get it right now and play around with it. And if you have problems with it, just send me an email or Tom or anybody from the team, and we will be happy to look into it. Okay, thank you very much, and looking forward to a good collaboration.
Okay, we have time maybe for one quick question for NISO. Anybody?
Yeah, thank you for the nice presentation. Maybe it's too much into the future, since I gathered that you didn't do any non-equilibrium computation yet.
No. So Marco Fossati is very interested in the non-equilibrium part, but our problems are mainly equilibrium chemistry.
Because you mentioned the convergence problem, which I guess are related to the conditioning of the metric, the linear system.
Yes.
But still, it's equilibrium.
Yeah, it's equilibrium. Yeah. So, but as I said, it's currently implemented in a segregated way. It might be better to implement it in a coupled way because of this additional source term. And also, we haven't completed the extension of artificial compressibility for this progress variable yet, so that might also improve convergence. So there's still a lot of things that we have on our list to test to see if we can get some nice speed up.
There are also a few terms missing from our Jacobians at the moment, I think, right?
Yeah, but you have some good ideas.
I think there's still a lot of room to improve.
It's the basic idea that this implementation will be superseded by some NEMO implementation later on, so you will transition to a new solver, but reuse some of the parts that you've already.
Yeah, so I don't expect that the way we have done it now will in the end be the way it will be for a very long time. That's it. But it's good to play around with it, get some experience with it.
Sure.
Now, for instance, we know that also after some discussion yesterday, that the segregated method might not be the best way to go forward with.
So eventually you'll be transitioning for your type of work to the new solver that you're developing to Marco and everybody else.
Yes. So and we just have to see how everything goes, what to generalize and what not, as it was mentioned before.
The turbulent jet was not a key case in your presentation, but I can't avoid commenting that aerodermodynamics model is not the most appropriate model.
Yes, I know. Yes, I know. So that's also why I did not really do a very thorough validation, but it will also be good to test it with other turbulent models.
So I think just one last question from Gura.
Very quickly, it's a bit probably also due to the pride of being part of this community. Do you know? I imagine you have searched the literature. Is there anybody around in the world who is trying to do design optimization with combustion?
Yeah.
Automated, I mean.
Yeah, there's very few literature on design optimization of combustion. So definitely not for 3D applications. So there is something being done on it, but it's all in a very early stage. So I'd say this is really the forefront, the first attempt to really do adjoint optimization for 2D and 3D, let's say industrial type problems.
Great, thanks again, ISO.
Okay.
Good morning. When I registered up for this meeting, I thought that might be a good idea to have a little talk on Conjugate, specifically on Conjugate heat transfer, because even though it's not a very, very recent work, you might have seen the questions online, like asking, and they were asking for whether there is this functionality, and so it might be a good idea to have a talk here and use the situation to keep you folks up to date. And yeah, might have seen already in the master branch that there is some code, and it does actually work. And to keep you informed, talk specifically on Conjugate heat transfer now. And first, I will explain a bit what Conjugate heat transfer problems really are, and after that, the talk will be a bit about computing discrete adjoints. For that, we've heard this guideline this morning from Juan. SU2. It's not just about solving the primal, or it's not just about evaluating, but it's also always about designing. And so there will be also one slide on how we compute discrete adjoints in general, and then there will be some slides on how we do it with if we have a multi-physics problem going on. And yeah, and after that we have some validations for the gradients. All right. So what are conjugate heat transfer problems? Typically, it's about multiple physical zones. Could be some gas, could be a solid, could be anything really. Most often, or typical application are these kind of coolers where you have metallic cooling pins extending into some coolant fluid, and the problem characteristic of such a conjugate heat transfer problem is then that we do not only have like multiple zones, but also that we have to exchange heat and temperature data on the interfaces. To give you like a bit of background information why we did start that work in Kaiserslautern, Nico, some time ago, Nico was approached by some Bosch research department, not in the Netherlands but in Germany, and they were asking for whether this is possible in SU2, and mainly because they were not so lucky with the sensitivity quality that Fluent is providing. And so our main question was, can SU2 give accurate sensitivities for such problems? And the answer is yes, it can. And but before we can have a look at the sensitivities, we had to implement like the functionality for CHD before doing any optimization on that. So that has been done a while ago. I needed some stuff, there was some stuff to be added to SU2, like a heat solver which could be run in a solid zone, and at that time also heat solver which could be coupled to incompressible fluids. Later on we have a talk by Tom who had much more progress in that direction. Still, you can use it weakly coupled, this thing like having an inviscid terminal. We needed the transfer routines to communicate the coefficients, the heat fluxes, the temperature, everything that we need to solve these kind of problems. And we had and there was a need for a known driver. And back then it was that way that if you have a look at driver_structure.cpp, it's like about, we have these fluid drivers, and then there were the turbo drivers, the FSI drivers, and all this kind of stuff. And so it was I was about to add an CHD driver, but as it is not necessary to make it that specific, it ended up in a much more general approach to having the arbitrary solver. So, and the general idea or guideline was that the driver should not know anything about the actual physics going on. It should just see some should just see solvers and transfer routines, but not actually which kind of driver or which kind of anything. And so, yeah, that's currently the one that's in the master branch. It will be superseded, I expect, by the work of Ruben. We had yesterday at the hackathon, we heard his ideas, and he already merged CHD and FSI, and this stuff is, I think, evolving quickly, fast right now. And yeah, let's see. All right, so here we have an first application of this implementation that you just saw. It's a heated aluminum cylinder in a fluid flow. So like streamlines would go like this here, right? And it's heated from at its tip by 4 watts. So that's typically what the application is. You prescribe a heat flux or a heat load, and then you try to find out by simulation what temperature it reaches. And yeah, I'm not so sure about this number here. I just saw it on my phone. I think it's 0.1, but it doesn't matter so much. And what you can see in this plot is that it's quite hot, or it has a high temperature on its top, and then it cools down. All right, that's what we expect. And that's some cross section. This temperature scale is different here, right? So what we see that if the cool fluid arrives here, the cooling effect at the stream upwards is way better than stream downwards. So that's just this problem is kind of the sanity check for CHD problems. That's exactly what we should expect, like having gradient in this direction, but also having in this direction. And so it reaches like some temperature, and concerning optimization, what engineers usually then try is to lower this temperature. So the heat flux is prescribed, but by varying the shape of these pins, we can lower this temperature. You can translate it into spreading gradients more equally around the surface, so that you have like well-distributed heat flux and a low temperature. And typical application for that is like this, is the cooler that we saw on the first slide, where we usually have some power electronics on top, which emit some certain heat. It's like the heat transfer to the air, you can neglect it. So there's a certain heat which is emitted to the coolant fluid, and still we don't want to have the electronics damaged by too high temperature. And so that's basically what we want to reduce. And yeah, so how can we reduce it in SU2? There's this nice way of doing it by gradient shape optimization or gradient-based shape optimization. So we have our shape given by actually the mesh coordinates, which determine a certain thin surface, a certain shape. And we have an objective function. In our case, it's, for instance, the average temperature on the pin's tip. And if we are able to compute the gradient of the average temperature at a given shape, we have some suggestion for a geometry update, and we could even pass it to an optimizer or whatever to have it updated in a loop. So it's not just a suggestion, but a very useful thing for optimizers to get a better design. And yeah. So the quest, but it remains the question how we can get these kind of sensitivities or these suggestions for the geometry update. And to explain a bit what's going on there. I prepared a slide on how we do these discrete adjoints computations SU2. I was a bit lucky that actually Tim, who implemented the original version, was my mentor in the very early stages of my PhD. So I learned much of this stuff from him, and yeah, to keep all the others a bit updated how this stuff works, because it might be new to you or whatever. I prepared like 2 slides on that. So if we have this objective function, it depends. We have or let me start this way. We have a shape, and given the shape, we can evaluate by running the primal sort. We can evaluate this J, the objective function. But more precisely, it's not just this, it's not like we shouldn't write it down like this, but more precisely like this. So it depends on the mesh coordinates, but also like implicitly on the flow solution. So if we would now want to compute the gradient, or like, let me start this way. This flow solution is then given by some iterative process, like we have this fluid flow iterator, for instance, iterating a couple of times the solutions until we reach a certain quality. And so by this implicit dependence, it's the computational cost for this gradient crucially depends on G, because we have to by the chain rule implicitly compute the derivative of u with respect to x, which is utterly costly. So so there's an alternative approach to that, by making this implicit dependence somehow explicitly, instead of this j here, and be careful that we cut this implicit dependence here, right? So we just think of J as a function of 2 independent variables now, and we just add the flow solution by adding this term here, and it's some kind of Lagrangian view on that. And on the subspace, or to be more precise, on the submanifold of actual flow solution, they are equal. So we didn't change anything because this term just vanishes. And but concerning the gradient, something happens now. If we claim that we can have a lambda so that this equation holds, right? While there is such a lambda and stuff like that, that's some shouldn't be this scope. I mean, there are some Lagrange multiply theorems. If you're interested, look it up. So if there is a lambda and we could compute it, then it ensures that this thing here holds. Of course, this just says that the partial derivative of this L with respect to u just vanishes. That's exactly this condition. So and there the whole magic happens, because this thing now is very cheap to compute, right? There's no cost all this implicit dependence now is hidden in this lambda. So it's all about computing this lambda, and actually that's what the discrete adjoint solver in SU2 does. And the way it does it is that we take this equation here, reformulate it a bit, or just it's not really reformulating, but just running it out, and then we end up with this fixed point iteration here, and that's exactly what happens if SU2 runs a discrete adjoint solver. All right. And we didn't make any assumptions on G. I'm now going a bit into this multi-zone stuff. We didn't make any assumptions on G except for being able to carry out, except for that we are able to carry out this derivative here. And we use it by some, I don't know whether you already did some discrete adjoint computations. If you install it, it downloads some package called CODI, code differentiation package, which is developed in our group in Kaiserslautern, and what it provides is exactly this functionality that we are able to carry out these kind of terms here. All right, and if we have now, I prepared bit more detailed slide on that. So if you're interested for an arbitrary implementation of a function in a computer program, what we make use of is automatic differentiation in reverse mode, and it basically computes stuff like this, right? Exactly this stuff here. And the way it works, you can like look for some buzzwords in the code if you're interested. The way it works is it registers some variables, some input variables. Then it records the tape. If you might have seen the functions in SU2 being called set recording and stuff like that. So, and then that's just we carry out a primer run, and during that primer run, each and every statement of the code being executed by the computer is stored in the tape. After that, we set the values for lambda, and then we evaluate. And then it's just backwards evaluation of everything that got recorded. Right. So, and if we now have a multiphysics problem going on, it's nothing really changes because we didn't make so many assumptions on G except for being able to carry out the derivatives. So for instance, if we have two zones, doesn't matter how many actually, but if we have two zones, it's described by having two iterators, two meshes, two sets of variables being mapped like that. And computing a gradient with respect to such coupled problems is nothing but in the end computing only the lambdas for both zones. And if we now like redo everything that we did before, nothing really changes except for that we end up at this place with the matrix, right? We have now all these. You have this derivative that you would have had if you would have run it at each zone on its own, but now we have these like cross terms in here. And that's also nothing so new. I mean, Ruben already did it with this FSI stuff, but following the guideline to have a generalized driver. Also, this discrete adjoint multi-zone stuff is now designed in a way that it's very modular and that it does not actually care about whether we have these kind of variables or this kind of outputs, but it's just built up very modular, and it provides some fair functionality for further stable and efficient developments. Because one of the goals was to have one tape and not retaping anything, but one tape, and then being able to first initialize only parts of this thing here. Because if you're a developer, you might want to do some sub-iterations for the first part of it for stabilization purposes, and then do the other ones and add them afterwards for an update. You might only want to evaluate cross derivatives. You might want to cut cross derivatives, and so you can evaluate only with respect to some particular variables. And you can restrict this evaluation to certain parts of the tape. Because if you just would want to have these initialized and only want the derivative with respect to this variable, it would be unnecessary to evaluate millions of zeros, right? So it's just you can restrict it to parts of the tape. All of this could be done due to some Cody functions, and as soon as the pull request is open, you see in the like wrapping or interface functions to Cody how this is actually done then. So this is the theory, and as Niso always, as Niso just said, validation is crucially important. So let us see whether our discrete adjoint implementation actually works. So here's an example. We have we choose for the first iterator Rand's solver, and it's just some 2D cylinder test case, very popular. With the coupled heat equation, the repository actually is already changed. It's done with the native energy equation within the incompressible solver. This validation process done with the other one, doesn't matter too much. For the other iterator, we choose the heat solver, being active in the solid part. And it gets heated from the inside, but like 4 kilowatts per meter causes the heat, and there's a water fluid flow around. And yeah, this is the primal solve then. We obtain a flow solution U, and we use, as we did in theory, the average temperature at the interface as an objective function. In this case, it reaches like 450 kelvins. And now it's very easy to compute the gradient for us, because this is very cheap to compute. It does not involve the iterative process for the flow solution. It's just some evaluation, and assuming we have now this lambda, which is now to be validated, we can see if this gradient is correct. So how do we do it? We suggest a geometry update like this one there, given by some delta. And then we make this change smaller and smaller and smaller and smaller and smaller and smaller, and see whether the value that could be computed by our gradient actually fits to like the final difference. Like we are evaluating for every h, we are evaluating a primal solve, and see if we can get close to this one here. And actually, we do up to some arbitrary exactness. So it's just a matter of how small we choose the geometry update. We can make it arbitrarily precise. So that was some success, and yeah, some time left. So I will just give you some idea of what we are planning to do in the future. As I already said, Ruben was successful to unite to marry the FSI stuff with the CHT stuff. Next on my list is to have the turbo machinery functionalities added there, like the non-reflecting boundary conditions and stuff like that, to have it properly included there. Having these kind of applications in mind, I mean, you know this without this part, you know it probably from the test case repository. I just added some solid mesh, and just to give you an idea what kind of applications I have in mind for the futures. It's about like cool turbine blades, because there's some optimization space or left for cool turbine blades. Don't want to have them too hot or to have them like reaching critical temperatures by certain design updates or whatever. So we want to have this incorporated. Then one other thing is that we have to speed up the coupled simulations a bit. We know that by design in SU2 if we have a coupled problems, we are splitting the Jacobian entries at the interface are in fact not correct. Well, that's just by design, and I was thinking about how to compensate this breakup a bit to speed up coupled simulations. And last thing on the list is that especially for internal flow applications like the one that we saw first, you might want to try out a bit different optimization methods, and that's also on the list. And I think I have some time left.
Thank you, Lon. We've got a couple minutes for questions.
I'm not sure I missed the tell me which variable you use for communicating that heat side, that the fluid side and structure side, that briefly also temperature?
There are different methods actually. what you want the heat fluxes and the temperature to agree on the interface. That's what you want. And there are then different methods on how you communicate that, and it's due to some the way it's done now is that fluids get dirichlet boundary conditions. They apply temperatures, and solids get the Neumann boundary conditions, which are not really Neumann. It's like Robin-like boundary conditions, and that's the way it's most stable. Also by theoretical analysis, there's some done by some guy called Giles in Oxford, and who was analyzing this a bit on a theoretical level. And what you could also do is this open foam approach by using the heat fluxes at the temperatures to have an interface temperature prescribed for both solvers. I wasn't too lucky with that approach. I mean, it wasn't that stable, so yeah. But
just one more time.
Yes.
What was your maximum temperature for the conjugate mixture? So maximum temperature means that what temperature that the temperature maximum temperature.
I think you just used an average in your optimization, but are you asking for? Are you asking about the objective function, or are you just asking in the simulations what was the
in
maximum?
the simulation? So for example, that you tested 300 have been
for specifically for the test case.
Yeah.
You mean?
So not for this case. If you have another case having higher temperature.
Yeah.
What was that maximum temperature of that case? You understand?
Of all the test cases you've run, what is the highest temperature in the surface of the fluid over the surface of the structure?
Because some methods, I know some methods work for low temperature like that 300 Kelvin, but it doesn't work for very high.
I see. Okay, now I get a bit closer to. I didn't run too many test cases, to be honest, cause it's more like developing side for me. It's just about like cylinder test cases. I think this one in the repository, like this turbine blade that you saw at the end of the talk, it was like about 500, 600 kelvins. But I didn't know that there's some that new issues pop up if temperature rises. So, but it's good to know that might be some.
Is some difference.
Okay.
What we can do is take the test case that you have for the pin and just turn up we could make maybe a very hot inflow.
Yes.
For a cold pin.
Could just rise the watts, yeah. Yeah. Okay, good idea. You could try that. What happens if we like double or like change the magnitude effect of the detection?
Any other questions? Yeah.
Well, in slide number 6, where you have the surface sensitivities of the cylinder pin, I'm just curious.
Yeah.
There you go. So in the front face, in the middle of the cylinder, where it's between red and in the front face down, so as the fluids come, somewhere around there.
Yeah.
Are there no arrows because the sensitivities are very, very small, or you chose to plot the sensitivities only along where I see the?
No, that's a very honest picture. That's a very honest picture. That's just plotted as it is. So
it's super small, the sensitivity in the front.
Yeah, I think that's not that they are very small here, but it's due to that they are way bigger.
Relative.
Because the cylinder shape is in fact not very good. Because I think it's not about like subtle temperature gradient optimizations. It's more about that these sensitivities have tried to delay the separation a bit, and having the flow attached to the cylinder is so much more important than the subtle differences. It's not popping out here really, or it's not showing up here because one might just start with an pin design where the flow is like attached.
And you managed to do an optimization, a couple steps to see where the shape would end up?
Only in 2D. In 2D, and I think that I'm close to the isothermal temperature optimization that possibly Tom will show, and Yeah, for 3Ds, I just I did some actually, yeah, but I didn't bring them here. So.
There was one more question from
yeah. One more general question related to your last slide. Especially interested in how do you plan to develop or to set up the CHT solver for turbo machinery. And the reason I'm asking is because part of the turbo machinery feature, like the giant boundary condition, are already developed, while others, like mixing plane interfaces, blah, 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 or multi-row computation, are in a specific branch.
Yes.
In the feature turbo machinery branch.
Well, there is so far there's no real strategy on that except for I want to try it out basically. So I think the way I should set it up is that I first wait for rooms superseding my multi-physics zone stuff, and then just collect every information or every implementation that I need that's already in there, and collect them somehow and put them into this driver, and then that's the basic idea. But I'm absolutely new to these kind of turbo machinery topics. It's just that I was searching for some kind of application or interesting application, also to make it interesting for other people and to get some visibility for SU2. And I thought about these kind of applications, but I'm absolutely new to that. So if you are familiar with this kind of blades and turbo machinery and whatever, would be great to have some exchange, because I am just very new to that. Just that I find it appropriate for some CHD application.
Yeah, I think it's a great example. We're seeing a lot of cross-pollination of all the great topics. So.
And possibly one could also at some point add the structural deformations on the blade with respect to like structures being weaker or softer by temperature influence. So one could make it now arbitrarily complex, but still have a chance by this generic design that we come up with.
Okay, any final questions? Okay, let's thank the speaker one more time. Thank you. Hey everyone, as Professor Alonso said, I'm at Stanford working in the aerospace design lab with Professor Alonso. So I will be talking about the uncertainty estimation module that has been that I've implemented in SU2. This is specifically for uncertainty estimation of turbulence models. And doesn't have to do with aleatoric uncertainties or input uncertainties and things like that. And so as industry has been racing towards using more and more computational resources, we're moving away from using factors of safety because those are too conservative. They're you can get now what we're moving away from those factors of safety to actual design under uncertainty to create robust designs that can work in numerous sort of situations, and with that we require these estimation of these uncertainties. And I'll be talking about how turbulence models, they are models. There are some inherent assumptions that do reduce the accuracy of these simulations. But in that space where with lower fidelity, there is, if you endow it with certain uncertainty characteristics, then you're giving your designer a lot more information and a lot more information to work with. So for my presentation, I'll just be quickly. Okay. First, just to get everyone on the same page, I'll go a little turbulence 101, and then followed by some motivation and like the objectives that we wanted to stress on when we were building this module. From then, I'll be delving a little bit into the mathematical and computational details of the framework that is used for the uncertainty quantification, its implementation in SU2, and then go over a bevy of test cases that were
were well done, simulated, and show you results from those simulations. So turbulent flows, whether you're driving a car, flying an airplane, or hitting a golf ball, it's going to be in your life. And for industrial applications, almost all, close to all flows of any industrial or even academic interest involves some sort of turbulence and its chaotic nature. What exactly is it? It's these small. It is characterized by these small-scale fluctuations in velocities, in pressures, and what it does is it enhances mixing of momentums, it enhances diffusivity and things like that. But most importantly, one of the biggest ramifications of turbulence is loss of predictability. It becomes turbulence by its nature is chaotic, and it is therefore a lot more difficult to pin down and simulate with higher degrees of fidelity. Here, I'm just going to illustrate through this opening bit using the flow from a jet as an example. So here you have sort of a mean velocity profile with small-scale fluctuations based on those over those mean velocity profile. So in general, for design, you're interested in those mean velocity in those mean quantities, and you can sort of separate your instantaneous velocity into this mean velocity and fluctuating velocity. And when we perform RAND simulations, the effect of all this, the fluctuating velocities, can be encompassed in the term that's sort of highlighted over there, which is locally known as the Reynolds stress tensor. And it sort of encapsulates the effect of these fluctuations on the flow in the steady states that you are simulating using RAND. So now the issue is those fluctuations are very difficult to compute exactly. And so in the interest of time and in the interest of computational resources, you usually use a turbulence model and make some assumptions that sort of make the Reynolds stress tensor easier to compute. The most popular one are these eddy viscosity models, and they sort of relate the Reynolds stress tensor to mean velocity gradients. This is a pretty big assumption and sort of limits some of the features and the ability of RAND simulations to capture all the little bits and pieces of this of the flow that are occurring. And so again, using the jet as an example, here you have you do this a simulation. It's a well-known jet subsonic NASA turbulence modeling resource sort of test case. You have the baseline k omega SST turbulence model will predict something, a velocity profile that is shown here in the black line, but the experimental data, it follows the same trend, but there is this discrepancy between the experimental data and the RAND simulation. And this is at the core of what we're trying to sort of not fix, but get more information about. So just a little more about this, the problem itself. So you have a real world problem, a jet, perhaps an airplane in this case, and you make some assumptions and you use certain mathematical models to whether it's RANDs, whether it's LES, and you then have to numerically, you have to discretize the domain that you're solving on, and then you do a numerical analysis on that. And the outcomes QIs, this could be lift, drag, coefficient of pressure, velocity profiles. These are things that people are generally interested in. Now there's one big step here in discretization where you get some errors in numerical discretization. I'm not going to be talking about those errors. I'm going to assume that for most of my test cases that the mesh was fine enough and discretization error didn't really play a part. What I'm more interested in is uncertainties that come from these modeling assumptions that you're making, and then using those uncertainties to act in addition to the QOIs to inform design decisions. And it is this quantification of uncertainty that I'm really going to be focusing on. So the idea is to go. So this it says this is a velocity profile at a certain point, and it's essentially a point prediction. You're saying that at this point the velocity will the simulation says, oh, the velocity is going to be exactly this at this location, but there is discrepancy. What we want to do is put sort of bounds on the quantities of interest and sort of to illustrate what are the possible situations that a simulation might be in that aren't quite captured by the turbulence model itself. And this is done using the eigenspace framework, which I will go into a little more detail. Before that, I just want to go over a little motivation. This sort of uncertainty quantification module isn't available in any of the other commercially available software. This is a research topic that has been extensively researched at Stanford in the Center for Turbulence Research, and this is their work coming directly into SU2. And while you have you can sort of combine SU2 with things like Dakota to do aleatoric uncertainty quantification and see how input uncertainties play a role in affecting your QIs. There's no built-in epistemic uncertainty or model form uncertainty quantification for these softwares. And just some of the features that we wanted to ensure that we had when we started building this class, because SU2 is used anywhere and everywhere at this point. So it was important for us that it's versatile, whether you can use it, whether or not you are fully aware of the math behind behind the uncertainty quantification module, you should be able to use it nonetheless. It's theoretically very sound with multiple papers, and there are links to all of these. And if you want to learn more about them, I'll throw up my email at the end, and you can email me about it. We want it to be reliable, so it's been tested on almost all of the turbulence model resource test cases in NASA, and been validated through that, and been validated on other benchmark turbulence flows. And it's computationally inexpensive. You have to do 5 additional simulations to your baseline simulation to inform these uncertainty bounds, but using just 5 as opposed to having to run a LES simulation, which takes orders of magnitude more time, you're able to get a lot more information from a RANS simulation. And it can be, the way it's written, it can be parallelized. The simulations can be done in parallel, can be done sequentially, and it's part of SU2, so it's open source and can be developed and improved over the next few, years maybe. So now just jumping straight into some of the modeling of the framework the eigenspace perturbation framework that is the backbone of this uncertainty quantification module. The way we estimate these uncertainties is by actually perturbing the Reynolds stress tensor itself, and then letting the turbulence model use this perturbed state to run a simulation to convergence. And what this does is you have different instantiations of the flow simulation that can be combined to give you interval bounds on your quantities of interest. So there are the 2 parts that we focus on is the eigenvalue and the eigenvector perturbation. Now the eigenvalue, in terms of what it does to the flow physically, is it changes the componentality of the flow. And whereas the eigenvector perturbation sort of stresses the extremal states of turbulence production that can be achieved by the turbulence model. And it's a lot easier than for me to show this visually than by throwing up equations. So the Reynolds stress tensor itself can be visualized as a stress ellipsoid, where the major axes are the eigenvectors and the magnitudes in these directions are the eigenvalues. So on the bottom left here, you see this the Reynolds stress ellipsoid superimposed on a barycentric map. Now these are all what a Reynolds stress ellipsoid would look like at various points on the barycentric map, which is a way to visualize the anisotropy invariance of the turbulence flow. Yeah, so turbulent flow. And so what we do is, so you have your, say you have an arbitrary Reynolds stress tensor at some point in the flow, here that's visualized by this ellipsoid. The eigenvalues that you get out of that, say, land somewhere in the middle of the barycentric map. Oh, and it's important to note that for a turbulence for a turbulence model to be physically realizable, the eigenvalues need to be within the mapping of the eigenvalues needs to be within this barycentric map. The corners of the vertices of the barycentric map are the extremal states of complementality, and so then what we do is we perturb the eigenvalue to one of these extremal states, and then we also change the alignment of the eigenvector, and then reform the say the Reynolds stress tensor and feed that into our into the turbulence model. And so with that, we actually have the baseline unperturbed SST simulation that you run just usually using your normal config file, and then we have 5 additional simulations, 3 extremal states of complementality and 2 extremal states of turbulence production, or eigenvalue perturbation, respectively eigenvalue perturbation and eigenvector perturbation. And yeah, so it's using, and those are represented by these stress ellipsoids. And so using these 5 simulations on your baseline simulation, you're able to actually put interval bounds on any and all quantities of interest, whether it's an integrated quantity of interest like lift or drag, or whether it's coefficient of pressure. And you'll see these results in a moment. And so the way it works is you have, so here there's I'd like to sort of illustrate this with the diffuser case. It's an asymmetric diffuser. So you have the baseline simulation might give you something that is in the middle, whereas one of the perturbed simulations where you maximize your turbulence production, it actually suppresses the separation that would occur at the expansion. And whereas if you minimize your turbulence production and go towards isotropic turbulence, it minimizes the turbulence production and maximizes the separation that occurs. And it is and these are the bounds that sort of form that form these interval bounds on your quantities of interest. This is illustrative, but it doesn't have to be that these 2 cases are the ones that give you that purely give you the interval bounds. It could be a mixture of those 5 perturbations that might inform those bounds itself. So within SU2, there is the implementation that we have carried out that it can, for ease of use, you can just use a Python script. You don't have to deal with any of the options. All you do is use the same mesh file, the same config file that you would use for your baseline simulation, feed it into the Python script. It'll do the perturbation, like all the other simulations for you. And at the end, you have 6 flow instantiations that you can post-process to get your interval bounds. Now, if you want to be a little more, like get into the weeds of the config files, then you can create those config files yourself and do the simulations that way. There is a tutorial for all of this that is going to be uploaded as soon as the code gets pulled in. But so hang tight. But yes, within the SU2 structure, it's basically mostly just it's specifically in the numeric structure that the changes are made, and it's minimal code invasion in that sense. And so, yeah, so this is just a step-by-step run through of what happens at each node in the mesh. So for each cell in the mesh, you have your barycentric map. You get your velocity gradients, and that's used to calculate your Reynolds stress tensor. Now, from the Reynolds stress tensor, you locate your point, your stress state on this barycentric map. You then perturb that the eigenvalues and eigenvectors to some extremal state. You create the new Reynolds stress state using the perturbed eigenvalues and eigenvectors. This then gets fed into the turbulence model, which calculates the fluxes for you in the next step, which then now you have a new state for the next iteration. And then as you go towards convergence, the perturbation converges to this extremal state, and you have different instantiation of your flow. All right, so now getting to the fun part, the testing and validation cases. This is similar to the presentation back in December, so I'm not including all the test cases that we've run because we've run a lot. So I'm just going to focus on the 4 that are at the bottom there. So to start with, oh, whoops, it's a little bit out of order, but we're going to start with the the supersonic Zeiner nozzle, which is, as we mentioned before, SA is a terrible turbulence model for jet flows. This is using SST. Oh, and another thing to mention is that all of these test cases that you will see, all of them were run using the exact same script. There is no user input. It's minimal effort on the part of the user. It's using the same settings for all of them and using SST as a turbulence model. So yes, so here you see the supersonic nozzle. On the right, you see 2 plots. It's actually centerline stagnation temperature and centerline Mach number. And so you'll see these figures. So let me just explain them. You have, again, the baseline simulation, that's the solid black line, and this is going to be the same in the next few slides. The experimental data, the dotted lines, this was taken using sensors here in this case. And then the interval bounds are what the gray part is the interval bound that is predicted by this methodology. And so here you can see that there is significant discrepancy in the Mach and temperature between the baseline and the experimental data, but the intervals are actually encapsulated pretty much all of those points within the bound, and that's what we're looking for. We want to be able to encapsulate all the experimental data within these bounds. Now this is our favorite NACA 0012 airfoil at Mach 0.15. This is a range of angle of attacks to see how the module performs in low angles of attack, at high angles of attack with high degrees of separation. And it's actually, well, I would say this is pretty incredible to see, is, if I may say so myself. At low angles of attack, you have negligible bounds because RANS is super accurate at those angles of attack because there is no separation to worry about. But as we get to higher and higher angles of attack, you see that the baseline turbulence model predictions are not very good. Whereas, and it's not very good at predicting CL max or things like that. But using these interval bounds, you have a much better understanding of what the flow solutions might be. And just to get an exact, sort of illustrate how the flow simulations are different, you have, this is at 18 degrees angle of attack, so really deep into stall over there. You have the 1C perturbation, which is like where you maximize turbulence production. The separation is suppressed, whereas where you minimize turbulence production, the the separation is magnified and you have this deep stall behavior. And this isn't just for integrated quantities. You look at coefficient of pressure along the upper wall at 10 degrees of angle of attack. RANDs, again, super good at predicting what the coefficient of pressure is, and correspondingly, the uncertainty bounds are tiny. And whereas when you have at a higher angle of attack with where you have a significant discrepancy between the experimental data and the baseline turbulence model, the uncertainty bounds are bigger and are able to, again, encapsulate the experimental data as well as we could possibly hope for it. And so actually for the NACA 012, we also did a little bit of analysis on how the numerical error is affected. So we did like a little bit of a mesh refinement study where we had multiple meshes. Sorry, I'm just gonna, I'm running out of time, so I'm gonna run through this a little quickly. But basically, if you have a mesh that is able to get more or less able to capture more or less the flow simulation, then the uncertainty bounds makes sense. If it's too coarse to really find out anything about the flow, then it's going to be bogus values either way. And so this is the two sort of superimposed on each other. Now for the 30p30n airfoil, again, RAND is, you'd think this is a pretty difficult geometry to capture, but RAND again does a pretty good job of it. And here again, you see correspondingly tiny uncertainty bounds. You see the bounds are a little larger at the front of the slat, which is where you have the most uncertainty because there's more separation and more discrepancy in the RAND and the baseline. So again, it does a very good job of holding true to what it to where the interval bounds are larger where they should be. And this is the most recent test case that we've run was the Onera M6. Again, the coefficient of pressure data is very well within the uncertainty bounds for the predicted by the module. This is actually interesting. This is sort of an additional sort of use case for this uncertainty estimation is actually being able to inform where you do your higher fidelity simulations, where in the operating envelope or even sensor placement can be informed by this to sort of try and reduce the amount of uncertainty in a multi-fidelity hierarchical network, which is what we're working on with Boeing currently. And here you see that the maximum uncertainty for the CPs is right along the shock and at the trailing edge, which is where you would expect to be uncertain about your coefficient of pressure values. And so, yeah, all this to say that this module has been working very well and has been very robust in adapting to different flow cases. You saw compressible, supersonic, transonic, subsonic cases illustrated here. And so, it's ready for release. The pull request is in, so feel free to approve it whenever you can, and there will be a tutorial to go along with it as well. So.
Okay. Thanks, John.
Yeah.
Time for one or two. Go ahead.
The one thing that bothers me a bit, and it actually can be seen in this picture.
Mm-hmm.
In most of the 2D cases, the experiment always lie on the boundary of the uncertainty domain.
Mm-hmm.
I mean, the Rand's equation don't give you enough information to so accurately show where the experiment would be. I would have expected it to be somewhere in the middle of the uncertainty domain, not repeatedly exactly on the boundary.
Mm-hmm.
So it's a kind of, I wonder why is it so?
Can't be that lucky, right?
Yeah. Well, I think this is also these meshes weren't very fine. So in the mesh refinement study, in one of the other slides, you saw that RANDs does get like the baseline does get better at predicting at agreeing with the experimental data when you get finer meshes. But yes, in this case, it seemed to be at the very boundary of what was.
Repeated in other cases.
Yeah.
The kind of supply.
Yeah, I think yes, it's.
If you can find a reason, then we can know what is the exact solution from the boundary of the domain.
Yeah.
That data, just following up, that data doesn't show up anywhere in the algorithm, right? So there's no forming anything with data anywhere. So it's just by chance.
But yeah, remember that the envelopes, the gray area, are simply saying where the solution might be. The fact that I wouldn't say we're predicting it well because it happens to be at the bound. Also, there's no distribution associated with the gray area. These are truly just upper and lower bounds. So it's not that the center is more likely and the edge is more likely or vice versa. I think it's pure luck. There is something that you may want to say as to what the magnitude of the eigenvalue and eigenvector perturbation were for these cases.
Oh, yeah. So a lot of the case, it's informed by about 2 of the perturbations with the maximal and the minimal the maximal and minimal turbulence production mechanisms. So, but it's not always the case that it is that you can get the bounds with just 2 additional simulations. You need a little more information than that.
But you also have this degree of freedom as how much you perturb the predicted state.
Yeah. So these are extremal productions, all the way to the limits of what is physically realizable, essentially, to the limits of the barycentric triangle and sort of what should be predicted by a turbulence model.
To be completely honest, even though it's representing the uncertainties, I would be much happier if that gray area were much tighter and encompassing the data.
Yeah.
That's what we want. So there's a lot of work going on now to make sure that these bounds, which at the moment are conservative, are tightened as much as possible. So there's some investigations that I don't think we have anything to say.
Yeah.
All right, we better stop there. I am hoping after the meeting, though, we can review your pull requesting. Once this dies down.
Trip to Glasgow.
Yeah. Anyway, okay. Thank you, speaker, one more time.
Okay, thanks everyone. So my name is Zhou. I'm currently a postdoc researcher at the NASA Langley Research Center. I did my PhD in Nico's group, and since roughly 2015, I've had the pleasure of leading the developmental effort in the aeroacoustic capabilities in SU2, and with very strong support from these individuals whose names you are seeing here. And so this talk will be divided into 2 parts. The first part will be primarily on my PhD work that more or less wrapped up back in February, and the second part will be what I did with Langley, also in SU2. So first question, why are we interested in aeroacoustic optimization? And on the top figure here, you see the latest FAA forecast. The growth of air travel demand is growing steadily over the next 20-30 years at a rate of about 3.4-3.5% per year, which means that by the year 2030, it's going to double. However, according to the chart you see on the bottom here, the achievable noise reduction of various aircraft certified since the 1960s has started to plateau. So this is certainly a very unsustainable situation. And one of the main reasons is that right now various noise sources are present at very different frequencies, but we've reduced them to very comparable amplitudes. So they must be reduced by commensurate amounts to affect discernible overall noise reduction. And another very important point I want to make is that to meet these very stringent noise reduction goals, it's no longer sufficient to just reduce high lift noise or engine noise or landing gear noise. We must also look at innovative ways to reduce trailing edge scattering, which is the lower bound of airframe noise. So therefore, we need very efficient simulation and design tools to explore innovative and unconventional configurations and control strategies. Just to give you some example, for example, porous trailing edge, leading edge trailing edge serrations, etc. So what has already been done in the direction of aeroacoustic and optimization? I've listed some works right now that's being published. But what one takeaway from literature review is that aeroacoustic optimizations that involving high fidelity and scale resolving simulations are typically limited to very simple geometries and vice versa. So, and that's really limited by these three challenges. So the first one is very obvious, that we have these aeroacoustic simulations are very computationally intensive, and also often, especially for broadband noise reduction, we have very large set of design variables, and the design spaces are typically uncharted, so we don't really frequently we don't know how to perturb the design. And also, noise reducing modifications are typically accompanied by a marked loss of lift or increase of drag sometimes. So our answer to these challenges, as you can probably expect, is adjoint. So particularly consistent and robust discrete adjoint on the basis of algorithmic differentiation that will allow us to explore unconventional design concepts. So in SU2, we've implemented a permeable surface FW Fox-Williams-Hawkins acoustic solver, and we implemented the boundary integral form of this. So essentially, the way it works, that you solve a CFD, you perform a CFD simulation, and then the flow data on this permeable surface is then extracted, and that's used to compute the integral form of the FWH equation here. So you have essentially three terms. The first term is the thickness term, which is negligible unless you have moving surfaces. The second term is typically the dominant one for airframe noise, and that's the loading. That's the loading term. That includes the lift fluctuation on the surface. The last term is a quadruple source term, and at low Mach number, this term is typically omitted. And these source terms are integrated. Before they are integrated, they are evaluated first in retarded time to account for propagation. And in SU2, so this is the 3D version of the implementation of the formulation. In SU2, we also have implemented a 2D version in frequency domain, and this is after David Lockhart's formulation. Okay. So now, how is it integrated then with the adjoint solver? So this is the flow chart. So first you provided the initial condition and the initial design. This is then the CFD, unsteady CFD solver then performs what we call the fixed point iteration at every time step. And then these snapshots are then extracted by the FWH solver. Only the flow data on the permeable surface are extracted by the FWH solver, which then computes the far field pressure fluctuation. And the objective function in our case is typically defined as the root mean square of the P prime. And then in the adjoint phase, the DJ du term is the sensitivity of the noise objective with respect to the flow variables on that surface, and that's computed. And this term is differentiated with AD, and that's then coupled or accumulated to the flow adjoint at every time step as we compute the flow adjoint. And so everything is implemented in SU2. The shape optimization is fully automated process now in SU2. I've omitted the derivation of the unsteady adjoint, unsteady coupled adjoint solver, but if you're interested, I can point you to some of the related publications that we have, which I'll also list at the end of the talk. So we've performed a number of verification cases just to make sure that the coupling works, and it gives the correct pressure data compared to the direct solver. But more important examination is actually the validation against experiment, and in this case we look at a rod airfoil configuration because we do have measurement data provided by the folks in Lyon. So these flow conditions and the setup, we mimic exactly the experimental setup. We use a structure mesh, about 6 million elements with additional refinement in the rod airfoil gap. The near field acoustic sources are in this case computed by DDS with Spalart-Amara's turbulence model, and this is thanks to the development of Eduardo Molina, who's now at in Juan's group in Stanford. So so then we use the time domain 3D FWH solver. We propagate the acoustic sources to the 3 far field microphone positions. And by the way, this is the permeable FWH surface that encloses the whole configuration. Before I show you the results, just a note as to why we have to switch from the typical unsteady runs to DDS. So as we know, U-runs with the turbulence model is very well tuned for and inexpensive for attached boundary layer, but for separated flow, the performance is not very good. LDS, on the other hand, scales very strongly with Reynolds number in wall-bounded flows, but it does very well, and it's independent of Reynolds number in separated zones. So DDS or DDS takes the best of the 2 worlds, where we will have runs in a boundary layer and LES in separated regions. And for this validation case, we use the formulation from Spalart in 2006. Again, I would like to acknowledge the very critical implementation or contribution from Eduardo on this DDS branch, and I think many of us will come to benefit from his contribution. So a clear advantage of DDS is that when you refine, you get more turbulent content, and so which is like a sort of a LES-like behavior, and this is very critical to predict noise accurately. So some validation results. So the red dots are the experimental measurement, and the black lines are SU2 results. The blue lines are the LES results computed by another group from TU Berlin. And we see that we have, for tonal noise, we have very good agreement around the spectral peak. In fact, we're actually doing better than the LES results. However, we do have, for the broadband range, we do have a very clear overprediction in all the 3 polar angles. This is most likely because of, if you look at the mesh, we've coarsened way too fast outside of the boundary layer, and also in the wake region as well. So we're now resolving the turbulent wake properly. That's why you have these high frequency error, and also potentially it's also because we don't compute the quadruple source. Okay, now we go ahead and look at optimization. So first we look at a 2D case. Very similar setup. The only difference, well, we have a different mesh, but another difference is that we pitch the airfoil up 5 degrees because in this case we would like to look at lift constraint. So we want to do a lift constraint case for optimization. We only use unsteady runs to compute the noise source, and the objective function is defined as the root mean square of the P prime. And in this case, we do a shape optimization of the wing of the airfoil essentially, and it's parameterized with freeform deformation. So we ran two cases. The first case is an unconstrained case without a lift constraint, and what we see is that you get something like a 36% reduction on noise, but you also have a very clear loss of lift. Roughly, you've lost almost 60% of the lift at the end. However, if you look at the lift constraint noise minimization case, the lift fluctuates throughout the optimization, but eventually it does recover to the baseline level. Of course, then the noise reduction is more moderate compared to the unconstrained case. This is just the directivity comparison of the baseline and the two optimization cases. We see that we do have noise reduction in almost all directions except for very shallow upstream angles. Now that's the comparison of the design. The y-axis is blown up just to accentuate the differences between the designs. But clearly we do see a very wavy surface, and one of the reasons for this is because for the leading edge, the optimizer likes to bulge out the leading edge, because around the leading edge is much better at dealing with interaction noise, dealing with vortex interaction than the sharp leading edge. And also in the trailing edge for the red line, you see that this is because we do have a lift constraint, so it's highly cusp. Okay, right. Then we went for a 3D case. The setup is exactly the same, except we just extrude the mesh in the Z direction. The angle of attack, we pitch it back down to 0 degrees. Again, this is the upper surface of the design. So again, you see that the optimizer progressively introduced more and more surface waviness in the streamwise direction. And the reason is, if you look at the sensitivity, the surface sensitivity in the Z direction, we do see that they are expanded. And these bands in the streamwise direction, they switch signs. So you see that it's positive, it's negative, positive, and so on. So it does want to introduce this kind of waviness. We don't see any span-wise variation in terms of in surface sensitivity, and this is because for the noise source was resolved was computed with unsteady runs, so we don't have a vortex vortex breakdown, and so you have very coherent vortices hitting the leading edge of the airfoil. So to take advantage of the span-wise variation, we need to look at scale resolving simulations. What we did then was that we took these two designs, so the baseline and optimized design, and we analyzed them with DDS and FWH coupling. So in terms of directivity, we do see that the noise reduction is more or less omnidirectional, and we get up to 6 dB reduction in terms of the overall sound pressure level. Because we use DDS, it allows us to examine the noise spectra at these three polar angles. So again, the peak frequency, we know it should be around the Strouhal number of 0.19. It's captured very well in the baseline configuration, and the peak amplitude is reduced by 5 to 6 dB in the optimized design. However, if you look at the broadband range, the reduction is not omnidirectional, but at least the peak SPL is not shifted to a higher frequency. So to really minimize the broadband noise, the objective function needs to be redefined to target directly the high frequency component, which means that we need to perform an optimizations directly with the DDS and FWH solver in the loop. However, this is easier said than done with which I'll explain a bit more later on. So when I was wrapping up my my PhD thesis, this was the state of the SU2 CAA solver. So this was back in February. So we had basically 2D and 3D URANs and DDS coupling with the FWH solver implemented in SU2. We have an adjoint-based capability, coupled design capability supported by AD. We performed validation against experiment. The tonal noise was very well captured, but the broadband still needs to be improved. We have a number of conference proceedings, and right now we are working on our first AIAA journal together. In terms of future work, the first order of business is to further validate the solver against various benchmark cases, and this I'll work very closely with Eduardo at Stanford in this direction. And the second one is what I get paid to do at NASA, is to couple the SU2 solver with their NOP2 code for tonal noise reduction of the propeller and wing configuration, and this is jointly done with Len Lopes at Langley. And hopefully in a not too distant future, we will couple this then with OpenMDAO to do system level design. So now at this point, a big open question is what do you do then with broadband noise? Because so far we've done optimization with unsteady runs. So then what do you do with broadband? So it turns out it's not really as simple as we think. The first challenge is that we have very large, typically very large metrics for DDS. The second challenge is that we have this regularization problem when we run adjoint solver when you have a chaotic LES content. So our solution is to couple the runs with what's known as the SNGR. So it's essentially a synthetic turbulence method, and we've started working on this since April of this year, and this is the second part of my talk. Okay, so this is a joint venture with folks in Chalmers who are experts in turbulence modeling and synthetic turbulence methods, and this work is supported by NASA. So, as I said before, to accurately predict broadband noise, we need scale resolving simulations to resolve noise sources. However, this is a problem with adjoint solvers. It presents a fundamental obstacle, and this is very well reported investigated by Bolonigan and Wan since 2012. And in Nico's group, we've also noticed that this issue when we were trying to do jet noise sensitivity analysis, that the adjoint really starts to diverge. So clearly, we need to seek a middle ground between run-space approaches and scale resolving simulations. So the idea that we have is to start with a run simulation and extract the turbulent quantities predicted by runs, and then we stochastically synthesize the turbulent velocity field using this SNG model to compute, and then the turbulent velocity field is then used to compute the quadrupole or the broadband noise source, which can be then propagated to the far field to allow us to examine the far field broadband noise. So it's important to keep in mind before I go further what this method is designed to do, what it's not designed to do. It is designed to provide us with a a tool to do fast assessment of broadband noise characteristics and provide trends for design optimization. It will allow us to circumvent the regularization issue that's plaguing the adjoint solution for scale resolving simulations. Because of the additional layer of modeling, it's not designed to predict broadband noise to an absolute level, right? Okay, so how does SNG work? Essentially, the turbulent velocity field can be written as a sum of random Fourier modes, and essentially the wave number vector and the phase shift and also the direction of the velocity vector, they are randomly generated, and the magnitude of the velocity of each mode is computed so that the turbulent energy spectrum corresponds to the isotropic von Karman spectrum. So that's how U is computed from this energy spectrum E, and it essentially looks like this. So KE is the wave number corresponding to the maximum energy, and the K eta corresponds to the Kolmogorov scale, and these two, the KE and K eta, are computed by K and epsilon, which are extracted from preceding runs simulation. How does it couple with adjoint? Well, it's done essentially in the same fashion. You have in this case, a steady run solver. The SNG takes the flow data from runs to compute the broadband noise source, and then in the adjoint phase, the effect, the DJ DU effect, is accumulated to the CFD, to the adjoint CFD solver. Again, I've omitted the adjoint derivation. We do have a paper coming out at SciTech next year, so I invite you to follow our paper. So just a very simple test case right now. Here we are looking at airflow self noise. In this case, so we have a airflow higher Reynolds number, angle of attack of 8 degrees. So in this case, we have very thick wake, but the flow is very much still very much attached. So in this case, the dominant noise source is the quadrupole source, so it's very much broadband dominated. So we perform runs SST simulation. Then the TKE and omega are in this window, in this user-defined window, is extracted to the SNG, and the user also has the freedom of defining the frequency range that they want to minimize, and everything is implemented in SU2. The objective function is essentially the time and spatially averaged Lighthill stress tensor, and certainly the Frobenius norm of it. What's interesting here is that we see that the TKE, the peak TKE, is located in the turbulent boundary, within the turbulent boundary layer. However, the broadband noise source, which is the middle figure here, you see that the broadband noise source is washed further down in the wake, and also the most sensitive region, if you look at the sensitivity, is also further down in the wake. So the message here is that the shape optimization that you perform needs to know this, needs to be conducted so that you morph the shape to reduce the TKE in the wake, where the strongest quadrupole sources are. So this is just a validation of sensitivity. We see that so we use Higgs-Hanna bump function on both surfaces, and we see that the agreement is excellent. I think it's down to the 5th decimal place compared to finite difference. Okay, so optimization history. In this case, the objective function is reduced by 40%, so in this case, we didn't explicitly impose a aerodynamic performance constraint, but we got lucky. The CLCD is somehow recovers, and we end up with this new airfoil shape, but how does it compare then with a baseline? And this is now the comparison. So we see that essentially the noise source is compared to the baseline is essentially removed, and the peak broadband noise source in the present in the baseline design is reduced by 75%. We do have plans to verify this with a scale resolving simulation node, and we have a related publication, like I said, coming up in SciTech next year. So the next steps, again, we want to verify this with a LES-based simulation in SU2, and we want to extend the formulation to tackle anisotropic turbulence, and also we want to propagate. Right now, the optimization is performed based to target the source. So we want to propagate the source to the solid surface or the permeable surface so that it can be then propagated further with the existing FWH solver to the far field. Number of 3D test cases we are interested in looking at, and also at NASA they are very much interested in propeller and rotor noise. So we need to extend this formulation to unsteady, to tackle unsteady cases. This is the last slide, I promise. So just to outline some of the synergistic activities. So first of all, at NASA, we're looking at rotor and propeller noise reduction and coupling SU2 with NOP. And I'm starting to work very closely with Eduardo to look at validation cases. We have a series of benchmark cases that we want to look at Embraer. They are interested in jet flap interaction and the propeller noise as well. And certainly for the RANS SNG topic, we are working closely with Chalmers and at Polyme with Myers. We are trying to apply this for rotor icing detection, and the last two groups are interesting because these two groups are primarily experimental groups. So they want the Cottbus guys. They actually want to 3D print our design and put it in their anechoic tunnel to run some to measure the noise level. And yeah, TU Berlin, they want to look at trailing edge noise prediction with SU2. And these two groups, by the way, they are switching from OpenFOAM to us. Yeah, so the last block is our development plan. So extending FWH to tackle moving surfaces, so rotor and propeller noise. One thing that's very critical that we need to implement is the sliding mesh capabilities, which already exist, but we need to make sure that the adjoint also works so that we can do rotor blade designs. We should think about changing the optimizer, because currently there's a lot of scaling issues with the optimizer. Francisco did a lot of work to rescale the optimizer, and that works quite well, but it requires a lot of some tuning. So I would say we should look at other possibilities, and the rest are more or less wish lists, I would say. And well, the LES with explicit SGS, that's requested by the TU Berlin user, but that's not difficult to implement, so I would do it. So yeah, thank you for your attention.
Okay, thank you, Magin. Okay, so we're running a little behind. Maybe we can do one question while we start to. Is it okay? Yeah. Can you tell us that? Go ahead there.
Okay, sure. I want to ask about the first half of your
Sure.
About the DES. I think you might want to check the EDS option, not the DDS.
Mm-hmm.
With the Fitzpatrick currently recommend about the extended DS, better one.
Yes, this.
And Eduardo actually program also in SU2.
Right. Right. So that this validation case was in fact run last year or the year before. So at that time we only had the DDS option. So really Eduardo's implementation has really come a long way. So we should. That's why we need to revisit some of these test cases and rerun it. Yeah.
You will see some difference because
certainly, yeah.
I did see difference in the implementation between the DPS and the EPS.
Yeah.
Also, another issue is the load dissipation option. FD or MTS, there is currently a pull request running on the MTS with some correction. You might want to look at that. If also you can see influence whatever you use on the results. So you probably would like to look at that.
They're ongoing. I think they broke it into 2 or 3 pull requests actually because they found several issues.
Yeah.
So, yeah, they're improving that very quickly. So that's the advantage. We can pull that in and you can take advantage of it as well. Any other questions? Carol.
Very interesting this work. I'm not an expert of aeroacoustics again, but I happen to have attended the inaugural lecture of Damiano Casalino at the TUDEP. We recently hired him as a professor of aeroacoustics. And as you probably know, he works also for EXA Corporation, and they have this lattice-Boltzmann solver. Not knowing much of anything, I was curious if we can comment a bit on what are the differences with respect to the lattice-Boltzmann approach to the solution of the aeroacoustic problem.
So from what I know, I think the EXA, the power flow code is performing quite well, and it's when it comes to very complex geometries, and like for example, landing gear with hydraulic lines, and it's very I think it's very hard to beat the lattice-Boltzmann.
Still using an acoustic analogy like you do.
Right. It's the
use lattice-Boltzmann for the same flow.
Yeah.
That's something they didn't catch in the presentation of Damiano. They still use some.
Yeah, they're not resolved more than far field.
Right. You still need to propagate it to the far field. But in terms of resolving the turbulent noise sources, lattice-Boltzmann is very good, I would say. That's why it's on one of the wish lists.
I had a couple of questions. I didn't catch in this first half of the presentation. The cost function was the root mean square of the pressure at an entire set of locations equally weighted, or
no. So I believe all these cases were I have 3 polar angles, so at 3 locations.
Okay. Which
below the geometry.
Oh, below the geometry.
Yeah.
Okay. Evenly spaced between 0 and 180, or
no? So if the downstream angle is 0, so you have 45, 90, and 135, and they are at the same radial distance from the measure from the trading edge.
I was also surprised the optimized airfoil is a 2D one. The red one, it's putting a lot of reflex on the trailing edge. So if anything, that's decreasing the lift. So it's redistributing the lift.
Right. The reason is that I pinned the trading edge here.
Yeah.
So I pinned the trading edge point. So that's why this point can't move, but then you need a camber, right, to meet the lift. So that's why you have this very high camber, but then it has to come back up again.
Yeah. But it's introducing negative
lift
there. So that actually I didn't realize that not moving the trailing edge may actually be leading to more oscillations. I was asking about the cost function to see, I guess what may be happening is that you have directionality of the noise sort of created by the geometry, and that's decreasing at those particular orientations. You see some lobes there, right?
Yeah.
I see. That'd be interesting. It'd be interesting to have more observer locations.
Yeah.
And more evenly weighted.
Right.
So that's very cool.
I assume your FWH surface has quite some influence on the results as well.
Absolutely.
How can you define it?
So the placement of FWH surface is like an art, because you can't you need to place it so that within the FWH surface you sufficiently resolve the source, right? Because the assumption is that you can drop the quadruple term if your quadruple term is resolved within that surface. Otherwise, you have these sources convecting through the surface, and you have spurious noise.
So there's random or some rules, or you get some criteria to define that surface?
So what we typically do is, and I think many other groups do this, is that they run a simulation and then they see how the turbulent wave convex, and then they see, okay, well, you know, it shouldn't be too narrow, because then you cut through the wake, right? You definitely shouldn't touch the shear layer or anything like that. So I know for jet noise problems, people even leave the exit open, right? Because there the shear layer is very, very long. You will penetrate the outflow boundary of the air filtration.
Unfortunately, there's no real sense of convergence, because as you expand the surface,
right,
you're capturing more of the quadrupole sources, right? And hopefully all of them.
Right.
But you're also going further away, so the dissipation and the numerical scheme is going down. So it's a bit of an art. It's tricky. No mathematical sense of convergence unless you have an infinite on that.
There's also a lot of debates as to whether permeable surface version is better than the solid surface version, because you can compute this on the solid surface as well.
Then you need the volume terms, right? Don't you have to integrate through the whole
right
volume
yeah.
mesh?
To comment about the average surfaces, it's true that there is no mathematical formal way of convergence, but practically, if you are not in the shear layer, you see some conversion. Usually, you reach a situation where it's not so sensitive to the application.
Right.
I was going to say the other thing as a comment, I think your ability to do rotors in the near future is huge. Most of the people looking at this urban air mobility eVTOLs, as you probably well know, are going to be facing the challenge of noise, and anything that can be done beyond just sort of slowing down RPM and increasing solidity and some basic rules of thumbs that are going to require detailed CFD analysis will be very helpful. So especially if you can get another 2, 3, 4 feet.
Okay, there are no more questions. Let's thank Becca one more time.
Thank you.
And then okay, well, this is about the work we've done on the higher order schemes in SU2, and as you see from the number of authors on this slide, it has been quite a collaboration between a lot of people. So it's going to be twofold, because I'm going to say something about the DG discretization, and Kevin is going to say something about the Wino solver he is developing with the group at Strathclyde. But first, we're going to say something about motivation for the high order schemes, and then later on, Kevin's going to take over for the Wino solver. I will continue with the DG solver, say something about shock capturing, LES models, and performance optimization. Say something about a very important topic: is grid generation, how we can access the code, and the number of things we still have to do. So if you go to the next one. So why do we need the high order schemes in the first place, right? Because the second order scheme have been extremely successful for RANs. We have seen a tremendous amount of very interesting applications already today, and we'll see more in the afternoon. You see here just a few examples of them. So they're both in aeronautical and non-aeronautical parts. But next one, Kevin, we have to hurry up a little bit, otherwise the launch is going to be late. But there are a couple of applications where second order accuracy may not be sufficient, or at least not be efficient. And this typically have to do when you go for a high order modeling of the turbulence. And typically when you go to LES, either well resolved or well modeled and DNS approaches. And you see here to the left, you see a picture of an LES computation we already done with the high order DG solver. And for that, we all know that the second order discretization may be quite dissipative, and turbulence and artificial dissipation bite each other. So you may need very, very fine grids in order to resolve the turbulence correctly, and maybe we can do better with the high order solver. So that's the main motivation. So the high order solver is intended for high fidelity modeling of the turbulence. So we're not targeting RANs, certainly not at the moment, but we first will target LES type of applications. Yeah, could you go to the next one? So what are the options to increase the order of the accuracy? So the first one is to increase the stencil. And if you are going to use the Wino scheme that that Kevin is going to talk about in a minute, you're going to combine that with smoothness indicators, and that's typically on unstructured grids. That's going to be a significant number of challenges. The other option, which I will talk about, is to increase the polynomial degree inside an element. That typically leads to high order finite element methods. And the one I'm going to talk about is the discontinuous Galukin finite element method, and where you see a picture on the left of a typical location of the degrees of freedom, in a tetrahedral element. Yeah, now that's up to you, Kevin, to say something about the Wino part.
Thanks, Edwin. So yeah, as Edwin said, the group at Strathclyde here has been working on implementing high order schemes within the finite volume side of SU2. As part of this, first we implemented a couple of limiters within the muscle scheme to theoretically get third order accuracy, as well as 4 orders of accuracy higher than that. We implemented most of the framework for the weighted, essentially non-oscillatory or Wino schemes. And we'd use the double vortex pairing as a test case to assess the relative performance to make sure we can capture all the information. So a quick word on the double vortex pairing case. It was first observed experimentally in the 70s to study the vortex pairing mechanism using 2 co-flowing streams of water. What you see, the images on the right are just the passive scalar in time to aid with the flow visualization. We initialized the solution with velocity perturbations which inflate in time, forming 2 discrete vortices, which eventually roll around each other and merge to form one vortical structure with a wavelength of approximately twice the 2 original vortices. We chose this as a test case because it exhibits fine structures as well as discontinuities, which require an accurate as well as a robust scheme to capture all the fine detail. So briefly, some results. On the upper left is a result from 11th order accurate Wino scheme from our in-house code, which we use as a reference solution. And the other results are outputs from the limiters within SU2. As you can see at the bottom 2 images, we're able to capture the 2 new limiters, enable us to capture slightly more of the internal structures as the passive scalar plots more closely match the Wino 11. So moving on, one difficulty for unstructured grids and finite volume solvers is it's difficult using a muscle-based approach to obtain orders of accuracy above third order, which served as the motivation for us implementing the Wino scheme, which should theoretically allow us to reach much higher orders of accuracy. And the way a Wino scheme works is you construct a higher order polynomial using multiple stencils of multiple neighboring cells. And using this extended stencil, you can put this information together to assemble a polynomial, which should be able to give a higher order accuracy. So the implementation we've gone for currently contains 2 types of stencils, one central and one directional. So for a target cell in red, the central stencil takes information from all around the target cell, whereas your directional stencils, which are used as correctors, are only for certain regions of the flow. And for each of these stencils, the number of cells within each stencil scales with order of accuracy, where R is the target, the order of polynomial you're trying to construct to, and K is the minimum number of cells you need within each stencil. And to ensure a robust scheme, we actually need to double this. So you can see for high order of accuracy, the information you need from the stencils grows quite considerably. So for each of these stencils, you assemble a higher order polynomial, and then the essentially non-oscillatory part comes from the fact that we use nonlinear weights to assess how smooth each polynomial is in each stencil, and that information is then put together to get your final solution. And usually for cases with smooth solutions, the central stencil is given the largest weight, since you're taking information from all around the base cell. It should give you the most accurate solution. So our status on the implementation as of now is most of the framework is within the code set between the pre-processing and solution reconstruction part. We have functions to assemble the different stencils, as well as carry out all the matrix multiplications to calculate the geometrical parameters, which is then fed into the reconstruction step, which then handles the third order Wiener reconstruction. But there are certain parts of the domain for which we cannot assemble the stencil source. So for that, the muscle reconstruction is used. As of right now, there are some issues which are needing to be ironed out. There are some oscillations present at discontinuities which grow in time, which I'm currently working to fix, and the implementation is slightly inefficient, so it runs quite slowly. For future work, first, I'd like to get this working in 2D for triangular elements. And then once that's done, we can extend that to handle quadrilateral as well as hybrid grids. After that, we can add the necessary functions to handle fourth and fifth order and so on. After that, we can extend this to 3D, which requires a few extra pre-processing steps. And then some nice to haves would be, there are some tunable parameters used per problem, which if they're read from the config file rather than hard-coded, it would make it easier to run, as well as lots of parallel implementations and performance optimizations to reduce runtime would be nice as well. Over to Edwin for his work on the DG solver.
Okay, thanks, Kevin. So first, a little bit of basic principles if you're not familiar with a DG or finite element discretization. So the idea is that within an element, you do a higher order polynomial variation of your solution. And the difference between a continuous Galerkin and a discontinuous Galerkin is that for the latter, so discontinuous Galerkin, the solution is allowed to jump over the element boundaries, which makes it easier to define the extension to higher order solutions. No matter what type of finite element formulation you're using, you always use the weak formulation. In terms of the DG discretization, so you do the integration over the element, so not over the entire domain, but over the element, and you end up with that integral expression you see here on the slide that involves both an integral over the volume as well as an integral over the boundary of the element. And those integrals for high order discretization, you have to compute with high enough accuracy to prevent instabilities and you're getting aliasing errors. And typically what you do if you use a polynomial order of P for your elements, you typically need that for the Euler-Navier-Stokes equation that you have to integrate polynomials up to order 2p plus 3 or so exactly. So that means if you go, say, for p is 4, at least or a fifth order accurate scheme, say, then you have to integrate an 11th order, 11th order polynomial exactly, which is it's quite expensive in terms of CPU requirements. So it's very computationally intensive, that you have to realize. So we don't do any compromises on the accuracy or on the aliasing. We just solve that particular equation. However, can you go back? So the DG solver, because it can be run very efficiently on modern hardware. I can come back to at the end of the talk. It still may be very expensive, and so we may have to look in hybridized DG techniques in order to reduce the CPU requirements. But that is for later. Okay, good to go. So what we can currently do, it's both 2D and 3D, just like the finite volume solver. It can handle all kind of the elements you can think of. So quadrilaterals, triangles, tetrahedra, pyramids, prisms, and hexahedra. In order to preserve boundary, we can handle curved elements of arbitrary order near that boundary. That's an issue with the grid generator. I say something on that at the end. We do allow that the polynomial order can differ in individual elements, so we allow for P refinement locally. The viscous discretization is tricky. We solve that with so-called SIP, so symmetric interior penalty for the viscous fluxes. That also leads to a very expensive discretization. but it gives stability. At the moment, we only have explicit time integration schemes of either the Runge-Kutta type, or we allow for time-accurate local time stepping via so-called ADER DG. I'm not going to say too much about it, seen the time, but that can actually be quite tricky. But it's a nice way of speeding things up if you compare it to the Runge-Kutta type explicit time integration schemes. We can typically save a factor of 4 to 5, although it's depending on the test case. And we have some preliminary implementation of the LES models and the shock capturing. Could you go to the next? Yeah. So on the shock capturing, that's mainly the work the people at Stanford is doing, which is J1 and Juan. It consists of, it relies on 2 components. Namely, first you have to sense the discontinuity. So where is it? And the second part is resolving the discontinuity. Well, sensing the discontinuity, you can do it in 2 ways. So it's the modal decay. That's what J1 has implemented. Another way of doing is the so-called MOOD approach, where MOOD stands for multidimensional optimal order detection. That's a different way of doing it, and we can still looking into what is the best way of doing so. As soon as you detect the discontinuity, you can resolve it, and that you have to be very careful about, because if you go and plainly say implement a limiter, you have to be very careful that you don't destroy all the high order accuracy, because if you typically apply a limiter without doing special things, you destroy the entire order of accuracy, and you typically end up with at most a second order discretization. The other possibility is artificial viscosity and filtering, and that's what J1 has implemented. And another possibility is subcell limiting, where you basically do an a posteriori error analysis and can come to the conclusion that in a particular cell you have to do something else. And typically you can apply their high order Wiener scheme instead of the DG discretization. So that would make the previous work, the previous thing that Kevin is doing on Wiener schemes, very interesting to combine things. Could you go to the next? So what was implemented in DG in SU2 is a discontinuity sensor. So basically what you do is you look at the modal coefficient. So you transform to the modal form of the DG method, and you're going to look at the ratio of the modal coefficients. And if for a smooth solution, those modal coefficients well, decay very quickly, but for a discontinuous solution, they don't. So that is an indication that a discontinuity is present. So that's the extension of Parallel Person's work on a shock sensor. And for the resolving method, we use a filtering method, and the filtering strength is determined by the sensor value. That means if you have a high sensor value, you're going to use more filtering than if you have a low sensor value. So what's the current status for that? Is that it works to 2D triangular elements up to 3, and the input of the filtering is an input parameter from the user. Could you go to the next one, Kevin? There you see it. Well, it's not perfect yet, as you see. So the left one is the discontinuous Galerkin solution with a shock there. This is the standard NACA 0012 test case. I think it's Mach 0.8, 1.25 degree angle of attack. What you see is that definitely the finite volume solver has a much smoother solution, so there are no wiggles in there. But it's actually not too bad. If you go to the next one. Here you see the pressure plot on the surface, and what you do see is, of course, there are still a few wiggles present, but they are well, limited actually. And what you also see that on the pressure side, you see that the DG discretization actually resolves the shock a bit better than the finite volume solution. So it's not perfect yet, but it looks already pretty reasonable. To go to the next. Next topic is on LES models. So that's what we are mainly interested in the high order solver. So the standard subgrid scale models are implemented or are about to implement. But what's more interesting is the wall models, because for high Reynolds numbers you cannot afford to do a fully resolved simulation, and consequently you need some kind of wall models. And at the moment we're going to use that. We use one-dimensional equilibrium models based on the boundary layer equation, and this is the work of folks at Stanford as well. And what we do there is the following. Could you go to the next slide, please? So what we do there, we define an exchange location where below we're going to use the wall model, and above that exchange location we're going to use the resolved LES. So that means that we have to use a specified value of that exchange location, and in the pre-processing step we're going to do a full parallel search in the entire grid where to locate this location. What you see here in the drawing is that it's in the first cell, but in principle it can be in any cell of the wall, and also it can be any element type of the wall. And the ADT search capability allows for this option. I have to be a little bit careful with that. If you want to combine this with time accurate local time stepping, you have to make sure that the time step value in the element which contains the exchange location is exactly the same as the time step you're going to do in the element near the wall. But that's just a minor implementation detail. But that leads to some complications I'm not going to talk about. The wall model itself, what you do there, you see the equations here on the right hand side, is a one-dimensional wall model where you ignore the advection terms. You only have the diffusion terms, and this leads to basically a one-dimensional elliptic problem. And you typically solve for that in what they call the wall model point. So the user defines how many points he wants to use in order to resolve this system of equations, and resolve that's typically with a second order finite difference discretization. Yeah, and that gives you the wall shear stress, and in principle also the heat flux, and that is input to the discretization of the actual DG discretization, and it means that the solution inside the first cell is completely ignored in that DG solution. Could you go to the next one? Here you see what's currently there. This is actually a wall resolved case. You see the movie of that is playing, and that is used as a validation case for the LES modeling. Yeah, what you see there, it's still converging, so it's pretty takes a pretty long computational time. But you also see that it actually matches the experimental data. Well, the log law, it matches it. It's pretty well. And the wall modeled case, well, we're still debugging that, and hopefully we'll have that running quite soon. Could you go to the next? Well, I mentioned in the beginning that in principle a DG discretization runs very efficiently on modern hardware, but it doesn't come for free, and you need to do something, some special things with it. Because my first naive implementation, because I've heard that everything was going very fast, but actually we only reached less than 5% peak on a modern Xeon, and it was a bit of a disappointing. Well, it turns out that you have to do something very special in order to get that performance. So typically you have to use specialized matrix multiplication software, and the best performance we're going to get at the moment is when we use the Intel MKL library. Also, explicit unrolling of small loops turned out to be quite a significant improvement in terms of efficiency. That leads, however, to specialized 2D and 3D code. And in the vectorization direction of the matrix multiplications, you want to have an 128-byte alignment for the data in order to get more or less the peak performance from this from the specialized matrix multiplication software. This means that as we have 5 conserved variables in 3D and 128 byte in terms of double precision, that's 16 variables. We're going to use 3 elements together in this matrix multiplication, and then you pad the 15 size, so 3 times 5 is 15 to 16, and then you actually get pretty good performance out of it. So at the moment, these matrix multiplications, also called the jam calls in terms of blast terminology, runs at about 60% of peak on Xeon. And the entire code itself now runs at 35 to 40%, depending on the case, on Xeon on a single core. Unfortunately, when we use the plain MPI implementation, that doesn't scale that perfectly. And the idea is then to use a hybrid MPI OpenMP to increase its flexibility and also to increase the parallel performance. And we are about to start that work, which is all. I didn't mention that this is all together with Intel. If you go to the next slide, please. So if you're not familiar with that, Intel has a couple of very nice performance analysis tools. I'm not going to go all spend a lot of detail on this one, but this is for a typical case we ran. And what you see there is you see that the total CPU time of this case is about 545 seconds. And of that time, so 350 seconds, that's so 60% or so, is spent in the matrix multiplications. So that's good news, because those run at very high efficiency, and that means that the other terms, the functions you see in there, those are the non-matrix multiplication parts. They run at significantly lower efficiency, but because the matrix multiplication is dominant, those do not need to be optimized that well. They need to be optimized, but not to a ridiculous level of optimization, which leads to unreadable code. And if you go to the next one, that's pretty much the same picture. What you see that you see the number of gigaflops. It runs roughly at 40 gigaflops this particular case, and where the machine has a peak performance of 130 gigaflops. So that's actually not too bad at all. Probably if you do the same analysis with a finite volume solver, you will get to a much lower efficiency count. Could you go to the next? Yeah, this is very important. I'm only going to touch it briefly, because seeing the time. But this is the high order grid generation, and this is also the work with pointwise, the work of Steve Carman's doing there. What you need for a high order DSG discretization, that you need curved elements near the boundary. Yeah, and typically that possesses a problem for the grid generation. What we have in SU2 itself is an in-house capability to generate high order grids for relatively simple academic test cases. That's the grid deformation tool that's available inside SU2. And that works nice, as I said, for simple test cases. But if you go to more challenging geometries, that fails. Fortunately, in Pointwise, they have realized this as well, and Pointwise version 18.2, which will be available in a week or two, that will have degree of elevation and mesh curving capabilities. And in principle, that means that we should be able to generate high order curved grids around more complicated geometries. So hopefully that works fine. We still have to test how it works in practice, but we'll see. We'll see what it brings. Okay, you could go to the next one. That's fine. For people who are interested in it, how can we access the code? Typical older development is carried out from the feature home branch on GitHub, and we have actually a pull request that's been approved with develop, so it's about to be merged with develop. We need to do some cleaning up with the test cases, and but that's well, it's about to be merged, I would say. And that also probably is also too good. It's also pretty good news for other people, because if you may know, there are the the search routines in the finite volume solver, but the search routine in the DG solver are actually much more advanced. So if you need some advanced searching routines, you can use them from the DG solver, because it will be merged pretty soon in the develop version. From Feature Home, there are several other development branches that exist in there, but basically you can generate your own one. Yeah, could you go to the next one? Well, at the current status is that the DG solver is producing results. It's working pretty nicely for some test cases, but there is a lot of work that still remains to be done. First, we'd like to finish the shock capturing capability and also the LES wall models. And then, of course, we have to go to do the statistic gathering for the LES, and that's very common to the DDS and the URANS simulation. So Eduardo is going to help out on that one. What we're going to do here in the University of Twente is we're going to improve boundary conditions, typically non-reflective treatment of boundary conditions. We're going to improve the time step estimates, because at the moment we would use a finite volume kind of time step estimate. We have to run at rather low CFL numbers. That's caused by the fact that we use a very compact stencil. And the consequence of that is that the spectral radius becomes larger. A nice way of doing this is doing an eigenvalue analysis of the Jacobian matrix. And basically, the Jacobian matrix we get for free, because we can compute that with Codipack automatically, pretty much. So we have done some work on that one, and we'll need to do a better analysis of the data in order to improve the time step estimate. The parallel performance needs to be optimized, and that's including OpenMP. So that's going to be a collaboration with Intel. What I didn't say anything about at the moment is entropy variables, because at the moment we use the conserved variables as working variables. However, that leads to a non-symmetric form of the matrices, and that may lead to instability. So if you work in entropy variables, you're actually going to obtain a symmetric form, which is better for stability. And especially when you for high Reynolds number, that may be something we have to use. Also, I said something about hybridized techniques, because the standard DG digitization is very expensive in terms of CPU requirements, and so you can use some hybridized techniques, for example, embedded DG, to reduce the computational requirements. Although in the beginning we thought that we would not need implicit algorithms. We actually may need them, so we're going to we have to look into that. We want to look at the discrete adjoint version of it as well, although there are some issues with what we saw in the previous talk when we are going to combine that with LES, so we definitely have to be very careful about that. And a very important topic is, of course, V&V. In combination with manufactured solutions. We already have a few manufactured solutions in place, so also that would be nice to combine that with the finite volume solver in order to so that both can do the same kind of manufactured solution. So what you see here is it's quite a long list of topics. So if people are interested and would like to collaborate on that one, we're very interested in that. In doing so, because we cannot do everything ourselves. So, well, go to the next one. This is all I had, and you see here some nice movies of an LES simulation of an SD 7003 wing, or the Reynolds number of 60,000, which is a fully resolved, well-resolved case. So, if you have any questions for me or for Kevin, then please do so.
Okay, thanks. Questions?
Okay, I have a question. So, Edwin, can we now change the order of the elements for each cell individually?
Yes, we can.
Okay. And what kind of polynomials do you actually use for the basis functions?
Depends on the element, right? But the typical Legendre polynomials. But when you extend that to triangle grids or tetrahedra, you have to do some special things in order to make them orthogonal. But if you look at the, say, tensor product elements, you use Legendre polynomials.
And what kind of grid internal node distribution do you use? You use something like the
equidistant. At the moment, we use equidistant distribution. That may not be optimal for very high orders of accuracy, because you get then something with the Runge phenomenon. Probably you've heard of it. However, that comes into play when you go to polynomial orders of 7, 8, or higher. And our target at the moment is, say, at most polynomial order of 4. And for that, it's not an issue. If you look at the condition number of the interpolation matrix for a polynomial order of 4, then it's pretty much the same than if you would use a kind of an optimum distribution. For example, the Gauss-Lobato poems. Probably you're referring to that. But it definitely, yes, when you go to higher order accuracy, when you say polynomial orders of p equals 10 or something, yeah, this definitely becomes an issue. But at the moment, we're not targeting that.
Okay, thanks.
Okay, I had a comment and a question. So since we have a lot of the key folks in the room, I'm looking at Nico and some of the CodiPack folks here. So Edwin, we had emailed about once you start including OpenMP, how that's going to interact with CodiPack. And I'm wondering if there's any work going in that direction now with OpenMP. Maybe you can comment, Nico.
Yes, Max is working on it.
Okay.
So that's good news.
When we want to go for many core architectures, we need that.
Yeah.
Is there any limitation on the form of the cells? Can you work both with tetra, hexa, and prismatic cells, or limited?
At the moment, we support in 3D. We support hexes, pyramids, stats, and tetrahedra. You have to be careful with the quality of the grids, though. It looks like the DG solver is much more sensitive to grid quality than the finite volume solver is. And the reason is that the finite volume solver uses a dual-based approach, dual grid-based approach. And as a consequence, if you have a bad element, that's kind of smeared out. While if you use the DG solver, you have to work on that bad element. I'm not saying that it doesn't work, but you're very much restricted in the time in the time steps you can take, because if you have a very flat element, that's going to lead to a very small time step, and that may lead to restrictions in terms of your time steps. In terms of stability, I don't know whether that is the case, because we still have to test that. The problem is that when we had this kind of bad elements in the grid, when we tried to create a high order grid out of it, it always gave me negative volumes, and we couldn't run it on it anyways. So that's also an issue. But you have to be careful with the grid quality you are using. So that is a disadvantage. Yes.
Okay. Other questions? Stop there. Okay, then let's thank him again.
Thank you, Juan, for the introduction. And to me, the hard work to start the first presentation after lunch, which is always quite difficult, also for me, of course. So before starting, so this will be probably my last present as a member of the SU2 Developers Meeting in a meeting like this, official meeting. And I really like to thank all the co-workers listed here that were before mentioned by Professor Alonso, but also to all you, to all the community. It has been a great pleasure for me to collaborate in this effort, and I really got very good energies with this project during the years, and the people that they work with were really fantastic. All right, so the presentation of today is just an overview of the features that are currently available in a specific feature of SU2. And the plan is to have this by the end of my PhD, which hopefully will occur at the end of this year. So I have to wrap up everything and create a quite big pull request to put everything that you're going to see into the develop. I didn't go too much into the details of the implementation, although it's kind of an overview. So if you want to know more about it, feel free to ask now or later in the day and so on. Yeah. So this is the outline of the presentation. I will give an introduction, comment on what was before, past work, what we had to face in the last year mainly, what is the current status of the development, and what are we working on actually. So the outlook to the future implementation in SU2, more in particular for turbo machinery. The focus of the presentation is on unsteady design and why we want to do this. So sometimes it's actually a necessity to do this. If you think of configuration like open rotors, turbo machinery, rotorcraft, and propellers, in which you really have to go for unsteady solutions most of the time. We also expect to give a step forward in the performance prediction, but also in the optimization. So this is something very important that we wanted to analyze and to develop in the code. So this feature to give prediction of the flows, take into account unsteadiness, but also at the design level. And last but not least, we see unsteady design as really a key enabler for MDO problems. And here I listed a few of those, such as fluid structure interaction or noise. So these kind of problems, they really need an unsteady solver to be solved. And so the unsteady resolution is a fundamental requirement. At the moment, for the optimization in SU2, there are, I would say, at least that I know, three possible approaches. The first one is the time domain harmonic balance approach, the discrete adjoint of this version. Then we have also the time accurate discrete adjoint. We earlier we saw some application by Beckett before on the time accurate discrete adjoint. And we also have the time accurate continuous adjoint. This was actually past work made by Economon. The focus of this presentation will be on the time domain harmonic balance discrete adjoint. Because it's very appealing for turbo machinery applications. This is maybe the only equation I want to show here. The main idea here we have dual time stepping discretization of a steady problem. The main idea is to replace that term there with something that is approximate enough and fast enough to represent the unsteadiness in the problem. And it turns out that we can approximate this term with a simple matrix multiplication and add this source term as additional source term to this equation to solve the unsteady problems. So the time derivative actually listed here can be easily replaced, I would say, as a matrix multiplication, and this matrix multiplication is time independent. So this is very important because by doing this, we are actually having a great and amazing similarity between an unsteady problem with a steady state plus additional source terms. And we can inherit all the infrastructure that was already in the code for steady state to then apply for unsteady application. This is very important, especially on design level. So we just solve for blade passing frequencies harmonic, and then we use the discrete Fourier transform to obtain the time accurate solution back once we have these solutions. And okay, so all this was already implemented in SU2. So this is a chart which I have to acknowledge a former PhD student of Professor Alonso, Dr. Naik. So he actually split the unsteady problem in two kinds of problems, as you can see here. We have tonal problems characterized by a set of discrete frequencies, and periodic problems characterized just by one fundamental frequencies and its harmonics. We can subdivide this in two different problems, one in which we know a priori the set of discrete frequencies, and this is the case for turbomachinery. Other cases, like the one we saw before on noise or landing gears, in which we don't know a priori what are these discrete frequencies. The same goes for periodic problems. We have known periodicity, for example, in wind energy. This is very often the case, and for vortex shelling, we don't know the period. When we don't know the period, it means that we don't know it numerically, although we could know it from experiments and so on. The capabilities of the adjoint in SU2 for design problems are actually with harmonic balance tackling these subcategories here, in which we know a priori which are the set of frequencies that we want to resolve. So we had in the past already successfully applied this to several test cases. I'm showing here the optimization of an unsteady NACA profile characterized by two frequencies that are not harmonically related one to each other. So first, as we can see here, the flow solver by increasing the number of time instances resolved by the harmonic balance solver. And this is the objective function, so we needed up to 9 time instances to, well, I would say, resolve the drag coefficient as a function of time as compared to a time accurate unsteady simulation. After this, we created the adjoint of the harmonic balance. We validated the gradients, and I wanted to show this because it's something actually very nice, was the way the adjoint inherited the convergence from the flow solver. This is something really nice, and it's not always the case. But with the implementation that we have in SU2, this is the case. This is actually the optimization history. So we see a reduction of the drag coefficient by maintaining the lift, and also we had some specification on the constraints on the thickness of the airfoil. And here you can see the baseline versus the optimized geometry. We did exactly the same thing for turbomachinery row. So here you can see the optimization history for this turbine cascade, in which we have the reduction of the total pressure loss coefficient and the constraint on the outlet angle of the blade. Here you will see the baseline versus the optimized geometry, and then we resimulated this with the Urans simulation, and we verified actually that we got the performance that were predicted by the optimizer. So this is what was, let's say, 2 years ago. So we had some limitation in this work. We had the problem limited to single geometries for the HB-based solver. We just tested it for 2D problems only. And there was not really a general turbomachinery interface. By this, I mean there was not a general interface that was handling all type of turbomachinery. And also the framework for the optimization was just limited to a single braid row. So the current status of the development had to start to have a generalized unsteady turbo interface. So we started with the interpolation method class and the sliding mesh available in SU2. And we created a new class based on the turbo vertex data structure. By doing this, we allowed for being very general of any kind of turbomachinery configuration. So we can now solve without any effort radial inflow, radial outflow turbines, axial turbines, for example. So this is quite general. And also the interface handles in a general way, because it's based on the turbo vertex data structure, the periodic boundary condition, and also the grid movements with periodicity that we need to perform for a turbomachinery application. The limitation at the moment is on the type of mesh that we are using. So this is just for a structured 3D mesh, although the unstructured mesh will work, but extra effort for interpolation on the span-wise level of the turbo machine has to be generalized also for unsteady flow. But this is something that we just need time, and yeah, it can be done. Okay. So some application of this. So as I told you, the interface is pretty general. I just here some few examples. We have a radial outflow turbine here configuration. the interface was handling good also the periodicity in this case. Radial inflow turbine, also without any problem. Here we have actually an axial stage with a time accurate simulation, and all this kind of turbine architecture were handled good by SU2. Right. So we are talking about the interface. The other thing we needed to do is to extend the single zone flow and adjoint solver to multi-zone. So the past status of the code was is represented here in these schematics here. So we have one geometrical zone, which for example can correspond to the stator, so one row. And then for each stator, we have one additional layer corresponding to the time instances that we want to solve. So we have this multi-zone in time, but we have single zone in space. So what we had to do is to extend this to multi-row in space and multi-row in time. And each zone of here, you see this connection here, are done by the interface that I just showed you. And this also entailed the fact that we had to adapt the adjoint to handle all the coupling between the zones. So we had in the adjoint formulation additional source terms and additional cross terms in order to get the right derivatives for each time zone. So there was quite some effort here, but we were successful in obtaining both the flow and the adjoint for multi-row simulations. So here for an axial stage, I compare here the for verifying the flow. I compared the entropy generation by increasing the number of resolved frequencies, and they pretty much collapse to the time accurate simulation. So this was quite nice, and there was the first verification of the flow. We couldn't do a very good verification also with experiments, because as I will show you later, one big, let's say, limitation is that the phase lag boundary recognition is still missing on the features for turbo machinery. So then we created an FFD box. Here I showed FFD box just for the rotor, but we also have one for the stator, and we validated the adjoint sensitivities using second order finite difference. It was quite okay after some effort, I would say. And we noticed that the adjoint memory and the CPU scaled like the number of frequency resolved +1. And so this is actually something that we have to keep in mind if you want to expand this method for multi-row simulation, that the memory for adjoint problem can become really a burden. So this is the results of now a concurrent optimization between stator and rotor. So we now couple them for unsteady simulation. This is the baseline versus the harmonic balance results, but we also wanted to compare them with the steady state and mixing plane simulation. We actually achieved for some particular conditions quite some differences between the shapes, but also on the performance. I don't show the results here that we get in this respect, because I thought that for the developer meeting was more important to focus on which features were available in the code rather than commenting the results. We got anyway 2 percentage points of gaining on this case. As I told you earlier, then we also were able to apply this for 3D applications. So we applied this for the Aachen turbine stage, and here you can see the entropy contours for this particular configuration and the adjoint sensitivities. Here I don't have a legend for this because since the sensitivity for the stator were so low compared to the rotor, I decided to normalize them for each row. So I should have had two different legends to show this. But okay, we also got the adjoint for this. The main issues with the 3D, and this is something that it's going on, is the shape optimization for this kind of problems can be really, really challenging. Because for internal flows, we are, as you know, bounded by, for example, in turbo machine by up and shroud, and this can become really, really challenging if you want to perform a constrained shape optimization, because the mesh can really be destroyed easily after a few iterations of the optimizer. So we have some ideas about this, which I will comment later. The current limitations of the software are listed here. There are many, but for me, I think the essential ones are these first 3 points here, which I'm going to comment. So the first one is the phase lag boundary condition for both HB and TA. There was, I say, a pretty nice implementation of the phase lag boundary condition for HB in the former SU-MB code. So we could leverage from that implementation also in SU2. What to do to the time accurate simulation here will require much more effort because there are some tricky aspects to take into account. As I told you before, I would say that the fluid form deformation box that was actually mainly used for external aerodynamics is not the smartest idea for turbomachinery design. Therefore, what we are investigating in our group now is to use CAD design-based optimization. So we are actually differentiating an in-house CAD software in order to perform also the 3D optimization of this kind of blades. And also, we want to test more thoroughly the time accurate adjoint for multi-zone to understand to which level we can go to the harmonic balance to compete actually with the time accurate simulations. So the time accurate simulation also will allow us to solve problems like vortex shedding. This we cannot do at the moment. This is actually a simulation that I got with SU2, and this is with harmonic balance cannot be possible to simulate something like this, or let's say it can be possible to simulate something like this, but we need to tweak the input frequencies in such a way that we converge to the exact numerical frequencies given by this shedding. Another field in which a colleague of mine, Nidhi Shanand, was mentioned before, is working on now is on concurrent aerostructure optimization. So we want to expand the current unsteady framework also to include mechanical effects. So basically, we will have two objective functions to feed the optimizer, and then to optimize the blades, take into account not just the performance, but also structural aspects. And this was my last slide, and this concludes the presentation. Please, if you have questions, feel free. I will be very happy to answer.
Thank you, Antonio. Questions?
I'll ask one. I'd like if you could put up the animation of the time accurate that you had vortex shedding in, just 2 slides before. Right? So are you, there's a frequency there that is not something you know a priori. Although you've done a simulation, so you now know what it is.
Yeah.
But it's probably unlikely that that frequency is going to be a multiple of the fundamental frequency in the actual problem, right? So you think you can capture the harmonic balance? This has always been the problem we've had with some of these situations, right?
Yeah. So of this particular test case, we know exactly the Strual number for both experimental campaign that they did and so on.
But there's no other rows, so there's no blade passing.
No.
So there's no forcing. It's all natural.
Yeah, it's all natural. Yes. So well, I think as you know, I mean the approach used by McCullen. So so that can be an approach to find the numerical.
Although remember, I don't know if you've seen Kadar's. You guys work quite closely, but in his thesis, I think he showed that McCullen's approach is
it's not
a bit of luck to get that one vortex shedding cylinder case to work. I don't think in general you can show that a residual goes down when you capture the right frequencies.
No.
Kadar showed in some examples that I think you've seen that
that's not the case. Yeah.
But it's very challenging.
Yeah, and what is also challenging is to understand all these kind of algorithms, also the one that Kedar actually is proposing in his dissertation, how much they can be applied to CFD. So if it's really cost effective to apply such kind.
In this case, if you actually.
In this case, maybe yes, because.
Done a simulation.
Yeah.
You may capture 90–95%.
Yeah. In this case, yes. But if then you have interaction with the other rows, that might.
But at that point, even if you capture the frequency, you have to do something a little bit different, right? You have to put a frequency there, another frequency, blade passing frequency, and the multiple additions and
Yeah, and then you also have a linear combination of the frequencies, so it's becoming a mess.
So I have a question. Do you have a feeling for how expensive it would be instead of trying harmonic balance, just do the full unsteady? I mean,
yes, I have a little bit. So the issues with the time accurate unsteady are two. So one is the computational cost, right? And the other is the storage, which is not a problem for this kind of problems. There are some techniques, for example, using checkpointing. To make fair comparison is quite difficult. I have now an idea that for up to 3 frequencies, it still makes sense to use harmonic balance.
Okay.
But it really depends how much you want to resolve and what kind of problems you are solving. So if you have a big mesh, so time accurate simulations, they might become prohibitive if you don't use a proper collocation method or something like that.
We found it also depends on the speed of rotation of the machine.
Totally.
And the length of the domain. Totally. Right? Sometimes when you have things that are rotating relatively slowly and there are pressure waves going back and forth, a solution can take a long time.
Yes. You have huge transients that if you want to capture, so yeah, it's.
But in some of the very high speed machines, relatively short domains, the time accurate converts to solutions.
Yeah.
So for high pressure turbine, we prefer time accurate.
Yeah.
But for compressor, we prefer that harmonic balance. But the problem is that compressor always has separation, and separation has unknown frequency.
Yes.
And harmonic balance is not that.
Let's say theoretically could predict. The issue is that how do you identify these frequencies? So this is the.
There is no frequency. Frequency. No. Even for this one, actually you don't have any other load. That is one. And another one is that you hit that periodic boundary condition, and that periodic boundary condition with the frequency. That's why you have that kind of way. But in realistic situation, there is no kind of periodic projection.
Yeah, no, this is a.
In principle, they tried a lot about that using harmonic balance for that projection, but no one believes that is the problem.
But that's exactly what we were mentioning before. That I mean, we don't know that frequency. Yeah, so this is a problem.
There is another group using time accurate solution with harmonic balance. So for that kind of setting, use time accurate solution for small region like hybrid glass area, like a pocket.
Yeah. That can be also interesting maybe on that joint, so you can maybe get your gradients in a way and the flow solution in another and combine them. That can be also something.
It's complicated. I mean, we've been banging our head against the harmonic balance with unknown frequencies for a while. I'm not quite convinced it's a good solution. That's why I was asking my question.
Yeah. And also can be also very expensive, so I don't know.
Any final questions before we move on? No? Okay. Thanks again.
Hello everyone, I'm Mark Morelli of Politecnico di Milano. I'm in the first year of my PhD and I've just started using SU2. Over the next few years I'm going to hope to look to start doing more of the development side of it. My other research is on rotorcraft icing, and hence today I'm going to be presenting my preliminary results on rotorcraft icing simulations and the CFD analysis of rotors and hover, as well as some rotor fuselage interactions. So first of all, I'd like to outline my presentation today. I'll talk to you about the background of my PhD. Here I'll discuss the problem of rotorcraft icing. I'll introduce the simulation framework which we're using to simulate this, and I'll discuss the challenges involved with simulating rotorcraft icing. This will lead me on to discussing helicopter and hover flight. I'll talk about the current status of the simulations which have currently been done using SU2, and the SU2 simulations which we've been doing. I'll then talk about forward flight modeling of helicopters and the limitations within SU2, which means we cannot simulate this right now, specifically the blade dynamics. I'll then further go on to talk about rotor fuselage interactions, where we've been using sliding mesh technique to help simulate this. and the test cases we've been using for the Gustav Weston 609 tilt rotor, and the significance of the ERICA project. So let me talk about the rotorcraft icing environment. Well, rotorcraft icing has severely damaging consequences and a threat to flight safety during some of the most challenging and unforgiving environments. Icing on the main rotor alters the blade's geometry. This has increases surface roughness, which leads to increased drag, reduction in lift, and premature onset stall. These aerodynamic changes have implications on the helicopter stability, flight condition, and power and torque characteristics. An example of a helicopter icing incident can be shown here of a Sea King mountain rescue helicopter in the Highlands of Scotland when it was on the search and rescue mission. Here the pilot suddenly recognized a sudden reduction of power and lift, and this was known due to the icing. He had to abort the search and rescue mission immediately. Right now, we're using both experimental methods and in-flight testing to understand rotorcraft icing. Both of these, however, are expensive and challenging. It's for this reason why we're working on ways to simulate rotorcraft icing at a fraction of both the time and cost of experimental methods and in-flight tests. The main goal of this is to increase flight safety and reduce the number of rotorcraft accidents. An example of an in-flight icing test can be shown here on the bottom right. It's quite difficult to understand rotorcraft icing. Different meteorological conditions cause different ice shapes. There are two different ice shapes largely known, this being rime ice and glaze ice. Rime ice occurs at far lower temperatures. This when supercooled water droplets impinge and instantaneously freeze on impact. This gives way to an opaque structure, as can be shown on the top right here. Particularly large rates of ice accretion can cause a spearhead shape. Glazed ice, on the other hand, occurs at far higher temperatures, close to the melting point. This occurs when supercooled water droplets impinge and run back before freezing. This gives way to a transparent structure, and during high rates of ice accretion causes these characteristic horns on the bottom right here. Our icing software, hence, is required to model all different types of ice accretion. And the simulation framework which we're doing so uses a three-stage process and an iterative loop to iteratively update the solution. And this can be better shown here, where we have a flow solver, this being SU2 in our case. This is where we've solved the flow field around the aerodynamic body. We then pass this information on to droplet solver. This calculates the trajectories of the water droplets and determines the location of which they impact on the airfoil. We then pass this information on to an ice accretion solver. And using ice accretion laws, we can determine the ice accretion shape. Within rotorcraft, what are the challenges involved? Well, rotorcraft have complex rotor geometry. It's an entirely three-dimensional problem, which means that there's large mesh sizes. Rotor blades can be non-linearly twisted and have different airfoils along the radius of the blade, which makes it time-consuming to mesh. These large mesh sizes give rise to large computational times. It's also hugely important to validate this flow field to ensure that we have correct ice accretion shapes. And we need to validate this flow field for different rotorcraft flight conditions. We need to understand it for hover, forward flight, climb, and descent. We also need to understand this for different rotorcraft configurations. The majority of people here will be used to seeing the conventional main rotor, tail rotor rotorcraft. But others exist as well. For instance, you've got the coaxial helicopters. This is where you've got one main rotor situated on top of the other. This eliminates the need for the tail rotor. There's also tandem helicopters. A lot of you will know of the Chinook helicopter. This is where you've got one main rotor situated behind another main rotor. You've got tilt rotor aircraft. This is where rotorcraft can act as a conventional rotorcraft and hover, but they transform into conventional aircraft during forward flight. Finally, you have intermeshing helicopters. Here you have two main rotors, one situated beside another, and as they rotate, they intermesh without intersecting. And one of the final challenges we need to understand is calculating the droplet collection efficiency on rotorcraft. Here we're using a high-fidelity Lagrangian particle tracking technique. But one of the problems with this is that we need to introduce a large amount of water droplets and gives rise to large computation times. Another problem we have is that doing particle tracking over multiple zones can be challenging, as we do not want to lose the trajectories of the droplets from one zone to another. So now I want to discuss hoverflight, and particularly SU2. Hoverflight represents the simplest flight condition Here the blades experience no blade normal velocity, and the blade motion can be considered constant with azimuth angle. This means it can essentially be considered a steady state problem. And Palacios and his group from Stanford have demonstrated this using SU2 for hover flight. They validated their results against the Caradon and tungsten experimental results. Here they use the rotating frame method, and they consider it entirely a steady simulation. For our rotorcraft icing test cases and some other rotorcraft problems, we cannot consider it as a steady case. This says rotorcraft icing stipulates a slight inflow to the water droplet blade interaction purposes during hover. Also during hover flight, we need to consider it as unsteady because there's a significant inflow velocity. So we have to further testing of this. So this leads me back to the Caradon and tungsten experiment, which we've just discussed. We went back and we looked at this, and we found that there's over 32 different experiments been done on this. Each of these had varying collective pitch inputs and rotational speeds. All of these 32 experiments had different blade pressure coefficients, which are well documented along different radial positions of the blade. And for our test case, we chose 3 different test cases with varying collective angle and varying Mach tip numbers. A schematic of this setup can be shown here on the top right. The method which we used to solve this was full Navier-Stokes equations, which are solved in a rotating reference frame. We used Almer's turbulence modeling and second order dual time stepping with a row convective numerical method and second order upward muscle schemes. The mesh we used had over 9 million cells. We used the ISM CFD software to produce this, and we ensured that there was a Y plus of less than 1 within the boundary layer. We used over 20 boundary layers. So our first test case can be shown here of 0 degrees collective. This also had a rotational speed of 1,500 RPM corresponding to Mach tip number 0.52. We chose this because at 0 degrees collective input, it means that there's no induced velocity by the rotor. And with a symmetric airfoil, it means that the upper and lower pressure coefficients of the blade are symmetric. And it also means that the solution converges quickly. This can be shown at the different radial sections from closer to the root towards the tip of the blade. The second test that we chose was 8 degrees collective input with a 1,250 RPM, a Mach tip number of 0.439. And this was the same test case, which was done from the rotating frame method, previously done in SU2. This allowed us to compare experimental tests with the rotating frame and our rigid motion unsteady test. You can see the results here are in quite good comparison. The final test we chose was that of a higher Mach tip number with a rotational speed of 2,500 RPM. We compared this against other CFD data and as well as experimental data. There's slight discrepancies in the results we got here, and I think that's due to the mesh resolution where the shock's forming on the upper surface of the blade towards the tip of the blade. Now I want to discuss the challenges with modeling forward flight. In forward flight, the blades experience a blade normal velocity, which depends on the azimuth angle position. And the blade normal velocity can be described at any different radial position along the blade and as a function of the advance ratio and azimuth angle. Azimuth angle is, the advance ratio is known as the ratio between the free stream Mach number and the Mach tip number. Because of this blade normal velocity, hinges are introduced to eliminate the rolling moment which arises in forward flight. The flapping hinge allows the blade to flap, i.e. move in the plane of rotation containing the blade and the shaft. And the flapping causes large Coriolis moments in the plane of rotation, and the lag hinge is provided to relieve these moments. Lastly, the pitching hinge is introduced to allow the blade to pitch independently. Schematic of this can be shown here of the different blade motions and hinge positions. The rotation, flapping, lead lagging, and pitching angles, however, are not possible to implement in SU2, and it's currently one of our limitations. Numerically, this can be expressed with the following set of equations, where psi is the azimuth angle position, omega is the rotation rate, t is time. The beta terms here describe the flapping motion of the blade, where beta naught is known as the precone angle, and the sine and cosine terms are the longitudinal and lateral high harmonic frequencies. The delta term here is the lagging motion, and the theta term here is the pitching motion. The theta 0 here known as the collective input, which I've just been discussing. One of the ways I'm considering modeling this in SU2 is to introduce the following transformation matrices. Here we have the transformation matrices, so we can incorporate the rotation, the flapping, the lead lagging, and pitching. The time derivatives of these can then be found, and assuming a constant rotation rate, the flapping, lead lagging, and pitching can be written as the following terms. The coordinates of point P in this blade fixed reference frame, blade fixed system in terms of coordinates of helicopter frame of reference after rotation, flapping, and lead lagging can then become where you can see here the different rotation matrices, as well as the flapping, as well as the hinge positions introduced. The velocity of point P in terms of the helicopter fixed frame of reference can then be expressed. And using these equations, the position and velocity of any point P in the helicopter fixed frame of reference can be expressed as a function of the azimuth angle. Way of which I would suggest possibly doing this in SU2 is to use the rigid motion to describe the rotation. On the contrary, the flapping, lead lagging, and pitching motion would be better off described using deformation techniques. If we could combine these two, that would be a good approach, and it's supported from this reference here. Possible S2 configuration file of which we could implement this could include the following, where we introduce a new type of grid movement, say rotorcraft motion, which requires on specifying the rotational speed, blade motion, the hinge positions, and the center of rotation. And this is how we can model forward flight. I want to now go on to the rotor fuselage interactions. Rotor fuselage interaction aerodynamics is hugely important to design and performance of helicopters. One of the challenges with rotor fuselage interactions is that it's difficult to simulate due to it having such complex configurations. Here we've thought about using the sliding mesh technique to introduce this. Here we're using we account for the movement of the rotor whilst enabling the fuselage to remain stationary. And this technique was based on Klein, Sanchez, and finally Nagori. Our test case we're considering is that of the Gustl Weston 6 or 9 tilt rotor. And we're interested in this because it has full ice protection systems. Also during forward flight, there's no extra blade dynamics included in this tilt rotor, so it's something we can simulate right now. This is the mesh which we're using. Here you can see the stationary fuselage in zone 0, and we have the clockwise and anti-clockwise rotating blades in zones 1 and 2. Here you can see the complex geometry of the rotor, the wing, and the fuselage, where they're all interacting within one another. And we've used the Q criterion to visualize the vortices. Due to sensitive information, we can't really show much more of these details with the Gustl Weston. But for this reason, we are interested in the ERICA project. The ERICA is an enhanced roadcraft innovative concept achievement. This is a development of European project, and over the past years has had much research into it. This provides different experimental flight configurations corresponding to the airplane mode, transition mode, and helicopter modes, different pressure profile comparisons on fuselage, fixed wing, and tilt wing. The graph on the left here shows the different nacelle, tilt wing, and fixed wing positions during trim. And the graph on the right here shows the pressure coefficients on the fuselage, the fixed wing, and the tilt wing. This is a project which we're looking to simulate over the next year with SU2. I'd now like to bring you back to the icing simulations which we've been doing. So here you can see water droplets introduced into the flow field as blades are rotating. This is allowing us to understand the location of which the water droplets are impacting. This can be shown here, where we've taken an intersection of the mesh, and you can see as the blades are rotating, it induces an inflow, and the droplets come down as they rotate. This was introduced to simplify, to simulate the Canadian in-flight icing wind tunnel facilities on the bottom left shown here. I'd now like to conclude. So for hoverfly, I think SU2 is in good agreement with both experimental data, rotating frame, and rigid motion. So for steady state and for unsteady state simulations. The rotor fuselage simulations, which we've been doing, Well, I'd like to start doing that on the Erica test, as it provides a simulation rich in flow physics, and there's a lot of data available on it. And one of the problems with the road fuselage simulations is that periodicity in the sliding meshes is still an issue. And now I want to just briefly discuss the challenges for forward flight simulation as well. It's clear that development is required in this. We need to incorporate the blade motion and the multiple reference frames and possibly nested grid movement. Thank you for listening.
Thank you, Miles. I think we have plenty of time for questions, right? Yes. Yeah. So open the floor. Questions? Second. Yeah.
So first of all, very nice talk. I have a question with the rotor fuselage case.
Oh, you hear me?
For this configuration, do you have any validation, or is there any validation there?
That's why we're interested in the Erica project, because that provides data for validation of the rotor fuselage simulations. Obviously, if we're wanting to talk about the 609 aircraft, we can't get the information is really sensitive of that. So that's why I want to start simulating the Erica project.
No. I have a comment, maybe not so much a question. I was interested in when you said you might need to do rigid motion plus deformation.
Mm-hmm.
We may have something for you. So years ago in Juan's group, we were playing around with the UH-60 and isolated rotor and trying to do rigid rotation, but also changing pitch and whatnot. So there might be a hidden option still in the code, external_rotation.
Okay.
Dig around and see if it still works. But we were doing this rigid rotation on the entire grid, and then move the blades and deform the mesh to get form around that. So see if it still works.
Yeah, I was
happy to show you that.
I was unaware of that, so I'll definitely check it out.
No promises. It's been years. So.
It won't work for the Augusta Westland.
Yeah.
That one you need some sliding mesh.
You'll need a slide.
But it will give us a good idea of how to start implementing it.
Any other questions?
So, if I understand correctly, you first solve the flow field, and then you introduce the Lagrangian particles.
Yeah.
So there's no two-way coupling between the particles and the flow field.
No.
So it's also not considered important. That's why you can neglect it, or you don't know, or can you say something about it?
Not so sure about that. No.
Okay.
And if you can just comment on it. Yeah, the answer to your question is it is not expecting to have a huge impact. So usually the majority of codes that are dealing with icing always do one-way coupling. So you flow, you do droplet, and then you do ice, and then you go back. But you're not expecting that the droplet of water will change dramatically the flow that is hitting your surface.
You do ice one at a time, meaning you grow the whole thing?
Yeah.
Or you do just a little bit of growth and then go back?
Well, this is really a way to refine the process, because typically, for example, if you want to certify your aircraft into non-icing, you have different envelopes. Like, for example, the envelope where you're asking to certify that after 45 minutes of icing, you still have worthiness in your vehicle. So what happens is that you can simulate 45 minutes of icing just with the same flow, but that doesn't change too much, doesn't work too much. But what you can do is that you can split the time for which you want to address accretion in multiple time steps. Then you get solve flow, solve droplet impingement, you solve ice for, let's say, 10 seconds. Then from the mesh, you go back, you start, and then you do the same. And then you usually collect roughly that. But it's not expected that, I mean, unless you're dealing with super cooled large droplets, which are usually a mean volumetric diameter that is above 100 microns, it can be 500 microns or even more. The droplets are usually with a sort of type of Gaussian distribution around 20 microns of diameter. It's not expected that you have. Alberto, can you comment?
No, I fully agree, of course. It's the two-way coupling probably needed when it's a joint PhD with the University of Glasgow. You will also include some simulation of runout and wideout. that case, there is some influence. And when you're landing on say, sand or snow, you're catching up some velocities. And yeah, but not in the usually not in the ice. For the multi-step accretion, yes, change the mesh in the high-Mach, especially for this configuration. But it's of course the way forward for large flight time.
I have a curiosity question. Can you go back to the slide where you had the flow, the streamlines, and then the ice accretion? My question is the following: if you run the same problem multiple times, is it deterministic, the ice accretion? Meaning, do you always get the exact same shape of the ice in the rightmost picture, or is there any stochasticity in these types of solvers?
There's a lot of uncertainty in ice accretion, and something that we're working on.
I realize it's uncertainty, but the predictive tool, is it deterministic?
Yeah.
It is. Okay. So it always produces the same shape if you give it the same initial conditions. Is that a good model of the physics? Meaning, if you put the same shape, clean up the eyes, let it freeze again, does it always freeze in the same, very similar manner, or is it?
An experiment, you always get a
different shape. Yeah. But dramatically different, or?
It can be very. Something totally different.
So, is there something to be said about adding stochasticity to the polymice?
It's in the model of the cloud.
I see.
Carol. I was curious, I didn't understand, or you didn't touch upon it. How do you model ice formation?
So there's
you start from humid air, and then you model also solidification.
So there's the Stefan problem, which describes what happens within the boundary layer, and then we model the different ice shapes from that. So as I said, if we have different icing types, it depends on the different ice shape. Was that?
Pre-treat the boundary layer of ice. We have a liquid film that is traveling surface, which is driven by the air. And every time step you solve this step of problem, the amount of ice is solid, liquid.
Using a shallow water.
Yeah, that's a liquid film assumption.
Sorry, we were just.
Do you want to share?
No, so the question probably is that so when you do this shallow water modeling, what you do is that you don't physically model the actual ripples of water that you have on the surface. It's just one model where you assume that you have a certain distribution of velocity of the film inside the water, then shallow water, and then you apply this equation to address the transition of phase. Then once you have that, you translate that into displacement of the node of the surface mesh.
Any other questions or comments? Okay, let's thank Miles again. Yeah.
Okay, thank you. So good afternoon, everyone. So I'm very pleased to be able to talk about anisotropic mesh adaptation capabilities within SU2 today. So next slide, please run. So I will briefly describe what my research team at INRIA Gamma 3 is doing. So basically, we are a team focusing on the complete meshing pipelines, basically from CAD to surface meshing, volume mesh generation, but also boundary layer meshing or X-mesh generation. But today I will focus on adaptivity, and this will concern error estimates, anisotropic mesh adaptation, but also how we can interpolate a solution from a mesh to another mesh. So next slide, please. So a few words about the current collaboration between INRIA, Gamma 3, and Stanford. So basically, we have a long-lasting, collaboration for maybe 10 years. we did a collaboration for the first Sonic Boom workshop in 2014. So at that time, basically, we were doing mostly in-visit runs, and this was a joint work with Onera. And in 2016, with Victoria Manu postdoc, we first decide to discuss what will be the possibility of exposing an interface for SU2 in order to do mesh adaptation. So next one. So the outline. So I will give you a brief background on anisotropic mesh adaptation. So basically, everything for us is based on what we call metric-based mesh adaptation. It's one way to prescribe anisotropy, size, and orientation along some direction. So I will then go through quickly on error estimates. I will then describe a little bit how we are going to generate anisotropic meshes once we have metric-based error estimates. I will show you one numerical example, which is a Rance adaptation, and then we will jump into the interface, which is called PyAMG in SU2. I will present the Python bindings and also a couple of numerical adaptive examples. So the motivation in order to use anisotropic mesh adaptation is mostly motivated by the physical phenomena. In typical aerodynamics, physical phenomena have strong anisotropic components. So on the picture, you can see a typical example of a wake of a business jet, or on the right picture, a supersonic aircraft, where basically you have a lot of discontinuities across all fields, all solution of the solution fields. So basically, anisotropic mesh adaptation is just a way to optimize the ratio between the CPU time and accuracy. So on the next slide, I will show you what I would call an extreme example, just to show what the gain of doing that. So this is a direct sonic boom propagation. So you have a supersonic aircraft flying at an altitude of 10 kilometers, and we are going to simulate the shock waves generated by all the discontinuities of the geometry from the aircraft down to the ground. So on the next slide, I will give you the sizing. So basically, it's 10-kilometer domains, and on the red square, this is the location of the aircraft. So the initial mesh is composed of 500,000 vertices, and just to point out the difficulty, the numerical difficulty is this is the volume ratio we have is going to 10 to the minus 11 up to 5 to 10 to the minus 10. And if we are looking at the sales ratio is 10 to the 9. And these two pictures show the final adapted mesh, and we can see that it's already quite a coarse mesh because it's 3 million, it's almost 3 million, it's more than 3 million vertices, and we can see the trace of the shocks generated by the aircraft down to the domain. So next slide, please. So this is my point. So in order to generate this kind of meshes, this run was about 4 hours in parallel. And if we were willing to do so with uniform refinement, it will ask 10 to the power 18 TETs. And if we will assume that the scalability of the solver will be perfect, it will be equivalent to 1,000 years of computation. So of course, this is an extreme simulation, but just to give you an example of the element we are generated. So we have basically 300 meters in one direction, which is more or less 3-foot soccer fields. And on the other direction, we have 1 centimeter. So my point is to draw that mesh adaptation is just a way to try to capture, to do early capturing of physical phenomena. And we have shown also that typically when you have flow with shocks, you can ensure that you will still get second order of convergence on flow with shocks. And we are also interested in capturing all the scales of the flow. So next slide. So what's the difference of doing mesh adaptation with respect of doing a typical several runs? So the main difficulty is that mesh adaptation, it's nonlinear problems because you want to converge both your solution and your mesh. So basically what you have to do, you start from a uniform mesh or initial mesh, coarse mesh. You compute your solution. So this is going to be done with SU2. And then we are going to compute what we call a metric. So metric is just a sizing information. I will give you just in the next slide a couple of information on it. And from that, we are going to generate a new mesh that is going to fit the sizing and orientation of the metric. And we will then interpolate the solution from the old mesh on the new mesh, and we will loop again. So all the three items, metric computation, mesh generation, and solution interpolation, is going to be done by pi AMG. And on the left side, you have a couple of iterations on the DAGA-12 transonic computation. So next slide. So the idea of metric-based mesh adaptation to generate anisotropic meshes, it's quite old and simple idea. The idea is simply to change the way you are going to compute distance and volume within your mesh. So the fundamental concept is to say, okay, imagine you have a mesh generation algorithm and you want to turn it into an anisotropic mesh generation algorithm. All you have to do is you have to change the way you compute the distance, or to change the way you are going to compute angles and volumes. So the simplest way to do that is simply to define a new dot product. So when this dot product is constant all over the domain, you are defining what you call a Euclidean metric space. And when this dot product is varying in the computational domain, you are defining what you call the Riemannian metric space. And in that case, it is equivalent to curve the space. So if you look at the surface on the bottom right, it is equivalent to compute the distance following the red cross. It was exactly the same if you are computing the distance on the squared domain equipped with a Riemannian metric space. So basically the ellipsis we are plotting here is simply the set of points that are a distance of 1 with respect to the local dot product. So next slide, please. So once you have a metric-based framework, you can start to generate quantities that are going to be described in the metric-based framework. So the first step we have to do mesh adaptation is simply to derive an error estimate with anisotropic information in it. So the scope first is to, starting from a numerical solution for SU2, you will have to derive a metric field to drive adaptivity. So there are a lot of studies for that. I will simply focus on the most common. The first one is what we call multi-scale error. So this one is the simplest one. You pick up a field of interest, for instance, the Mach number, the density, the velocity, or the vorticity, and you are simply controlling the interpolation error on these fields. So for this, in this case, all the scales of the solution are adapted, and the density of the mesh depends on the density of the magnitude of the input field. On the other hand, on the right hand, you can have also goal-oriented error estimate. So in that case, you want to derive the best mesh to a given functional. This can be the lift, this can be the drag. And in that case, you are going to change a little bit the distribution of the degrees of freedom in order to have the best observation. So on the picture, you can see this is two supersonic simulation. On the left-hand side, every part of the field is adapted. So you have the wake, you have the upper shocks, the lower shocks. Here we have an angle of attack. So typically the upper shocks are stronger than the lower shocks. On the contrary, what we can see is that if we only want to observe the pressure distribution below the aircraft, we can see that we have a much more refined sequence of shocks below the aircraft. So next slide, please. So once we have metric fields, what we have now, we have the current or initial mesh, and on top of this initial mesh, we have a metric field that is intended to describe the error distribution. Then the scope is to use an anisotropic mesh generator in order to generate a mesh which is going to follow the metric fields. So this is what we call a unit mesh. Basically, the idea is to generate a mesh with unit edge lengths and unit volume depths or triangles, but they are going to be unit in the metric This means that when you are going to see the mesh in the physical space, of course, it's going to be anisotropic. So next slide, please. So there is a lot of meshing software around to do that, and all you have to do is to use a basic set of operators. So you have typically the point smoothing. So you simply try to move the point around, and you are not changing the topology. Then you have the swap of edges. So you are taking the quad around two edges, and you try to flip the diagonals. You have the collapse of edges. So imagine you have a small edges, you want to remove it. You have point insertion, and of course you can imagine a lot of additional operators. So the idea of the basic algorithm to generate an adaptive meshes is really simple. You have basically two steps. The first step, you are trying. Oh, can you hear me?
Yes. Can you still hear it?
Yes.
Yep.
Yes. So we have two steps. The first step is we are trying to generate a unique mesh. So the idea is to split long edges when you compute the length in the metric. And the idea is, of course, to collapse small edges, but small edges with the length computing in the metric. And in the second step, you simply have an optimization procedure where you are trying to perform point smoothing and swaps. And all these operators are applied sequentially in order to converge to the final solution, and they are monitored by quality functions. So next slides. So one of the specificity of pi-AMG, what is going to be distributed, and which is the core of the talk today, is that in pi-AMG, we are using only one operator, which is what we call a cavity-based operator. So basically, every time you want to perform a meshing modification of your mesh, it can be a collapse, it can be an insertion, it can be a swap. You are doing to do a point reinsertion. So the idea behind it is that it's a completely uniform framework. You just have to change the initialization of the cavity. And when you are doing so, every time you are improving this operator, you are improving the whole mesh, because every operation is based on the single operator. So basically what we have is, with this operator, we can do line adaptation, surface adaptation, or 2D adaptation, volume adaptation. We can also handle non-manifold geometry. So non-manifold geometry is when you have internal surfaces, for instance. And an important point for us is that as we are using the same operator, which is basically an insertion, we have a uniform speed for all operators. And this is a crucial point when we want to run this in parallel. So next slide. So I will present just one computation, which was going to be based on the iLift CRM example of the iLift workshop. So it's a low-Mach computation with a 16 degrees angle of attack, 3.2 million Reynolds number. And in this process, we start from a very coarse mesh, and we are going to try to refine the solution. For the geometry approximation, so I didn't talk a lot about that, but we are going to use what we call a P3 curve mesh, which is built on top of the CAD package. For this computation, we are not using SU2. We are using INRIA in-house solver, so it's just an illustration. So it's a typical finite volume, finite element scheme. We are using HLLC with an implicit. We have SA negative, and it's really a standard practice. And we are using a goal-oriented range error estimate, which is based, of course, on the lift functional. And one important point is that this computation is fully anisotropic, meaning that we don't have any quasi-structure boundary layer mesh inserted. So next slide, please. So this is the final solution. So we have everything is adapted. We are adapting the volume. We are adapting the surface mesh with a typical surface projection. So we can see on the top left image a cut in the wake of the aircraft. We have also a cut across the section where we can see all the wakes going for basically the equivalent of the three element air force. We can see also the breakdown of the vertices due to the junctions. And the image on the left bottom is an imprint of the surface mesh, and we have really fine surface grids. So this final mesh is only 13 million vertices, and we get it after 10 adaptations. So next slide. So if we compare the lift solution we have with adaptivity with workshop participant, so what we are doing, we are comparing one of the coarse grid we have, which is 3 million vertices, with what with the level 2 grid, which is a 13 million vertices. And we can see that we are really in the standard deviation and almost on the mean, with only 13 million vertices if we compare with the fine and extra fine grid, which are 200 million vertices. So this is just an illustration that if you have a strong solver, meaning that it is going to be robust to anisotropy, you can quickly reach a nice level of convergence. So next slide, please. So now we are going to talk a little bit about the adaptive meshing module interface within SU2. So of course, there exists a lot of challenges when we want to expose adaptivity in flow solver. The first one is automaticity, meaning what we want is have a reduced set of parameters, because we have already a lot of parameters for the flow solver. Here we want to have a reduced set of that. And the main difficulty will be related to the geometry, because when we are going to do adaptivity, you are going to generate a lot of mesh, and you really want to get a consistent geometry. So typically surface approximation, projection, CAD input is really important, especially in aerodynamics. The third point is also important. When we are doing adaptivity, we have a kind of competition between the quality of and the anisotropy. So the quality is going to be mandatory to make sure that you have the stability, and anisotropy is going to be the guarantee to get a high level of accuracy. And of course, we have a competition between the two, and we have to make sure that the solver is going to be stable, but also accurate. And the error estimate also are moving a lot, and so there is a lot of theoretical developments that are still ongoing. And typical issue with CFD solvers, so related to the challenges, is first, most of the time the associativity of the boundary condition to the CAD to the initial geometry are completely lost. The solver has to get some restart capabilities, and also it's important to have strong linear solvers. This is really a key component in order to make sure that you will have stability and convergence. So next slide, please. So what are the technical details? So we have been using Python in order to, in the very end, be able to provide a main solve entry that can be adaptive, and so that it will be easier to use adaptivity in design loop, for instance. Basically, mesh solution and remeshing option are going to be basic Python dictionaries. And we made the choice to first, in this version, expose only a reduced set of capabilities of what you have. So basically, instead of providing a completely CAD projection, we are going to reduce that to P3 high order geometry. In order of error estimate, we are not exposing goal-oriented, but only multi-scale error estimates. And for the boundary layer, we are still working on a fully anisotropic, but I think in future release, we will progressively enlarge the set of capabilities with respect to the user input. And also, we really want to have a reduced number of user parameters for mesh adaptation. So currently, you can only control the level of accuracy, how smooth you want your mesh to be, which is called the gradation, and the sensor you have. And this is fully integrated within the SU2 config files. So if you want to try it, and if you have to get more detail on that, so we have created a PyMG website. So you have a lot of tutorials. We expect to enlarge it in the coming months. You can download the PyMG, you can run the code and give feedback if you want. Next slide, please. So just a quick example, just to see how simple is it to use it. So basically, once everything is set up, if you want to define a mesh, it's simply a dictionary with some keywords. So the keywords are really straightforward. It's going to be triangle, states, edges, corner, XY for 2D meshes, XYZ for 3D meshes. If you want to store a solution, in order to adapt to that solution, you simply have to add the keyword sensor. And for the meshing option, you can have control on the minimal size, maximal size, the norm in the LP norm for the multiscale error estimate, or the gradation. So it's a basic example here, or where you have only a square. The mesh of a square composed of 2 triangles. So you define your mesh, and you define a remesh option that is going to be only maximal size, and then you are simply calling adapt mesh, and you will get a uniform mesh which is refined to the size 0.5. So next example. If then you want to get a more involved example, so you can define a remesh option dictionary, for instance. So in some case, you are providing gradation. Target is the complexity you want. So the target is related to the number of elements you are going to have in your final mesh. And then you simply have to perform a couple of loops. And at each time, you are going to update the sensor of the mesh. And then you can write your mesh and use the dictionary directly. So next, please. So when you want to use AMG with SU2, in fact, you don't have to know how to use AMG. In fact, everything is contained in the config files. So all the parameters you have it's straightforward. So our goal is to make sure that if you already have a config file, you simply add the section for mesh adaptation, and then you are almost free to go. And we are building a Python script which is called mesh adaptation amg.p in order to drive adaptivity. So basically, AMG bindings are mostly transparent to the user. So next slide, please. So they are transparent to the user, but the user has to be aware of some of the work that is done in order to have maybe good practice. So when you are doing an adaptation, there is what I call behind the scene. So basically what we are doing is we are going to convert SU2 data structure into Python dictionary. And the most part of it is going to expand and split the markers to be as close as possible of the most detailed geometry description. So it's typically in the mesh you are using. When you have multiple patches, you simply say, okay, typically for the aircraft, I only have 2 boundary conditions. So I have the body and I have the inlet. So it's easy to run the CFD code for that. But then if you think of doing an adaptation on it, we lose almost every piece of information. So we have to recover almost patches we have to numerically recover the ridges, the discontinuity of the geometry, because initially this geometry was composed of multiple patches. So in this case, 83 cat patches. So I think a good practice would be to make sure that every time you are going to run a mesh, to keep your CFD mesh as close as possible at the CAN mesh you add in first. So next mesh. So what is the current status on mesh adaptation? So typically what we have in SU2, we can do NVC runs 3D with high order surface projection. We can do runs simulation with frozen boundary layers. So I will show an example on that. We are working on supporting 2D and structured boundary layers. So this work is really ongoing. And the adaptive code is still a custom branch of SU2, but we plan in the coming months to be able to merge that. And you have a web page of examples that give you all the files you need. You can download on the meshes in order to try yourself adaptation with SU2. So next, I will just give you some examples to conclude. So this is an MVC theorem case, so transonic with 2.1 degrees of attack. Again, we're starting from a very coarse mesh. We set up a P3 curve mesh. So this is completely embedded in the script. You don't have to do it yourself. So maybe we will plan to also expose some routine in order to help the user to make sure that the geometry is well defined for adaptivity. In terms of software in SU2, we are using GST with multigrid, FGEM, GMRS. The error estimate for that is simply the Mach number. And the final mesh I'm going to show you in a moment is about 3 million vertices. So in the next slide, you can see a cut on the wing. So you can see that you have the typical shocks you have on these transonic airfoils. You can see that the wake is refined also because we are adapting on the Mach numbers. So all these examples are really details, and you can see the solution yourself. The next example is a supersonic case with a runs computation. So it's Mach 2 with 10 degrees angle of attack, 1.6 millions. Again, here we start from a coarse mesh, but we have what we call a frozen boundary layers. So in that case, it's more or less the same kind of parameter for SU2. We don't have multigrid for that one. And the final mesh, the final adapted mesh, so we are not counting the boundary layer elements, is around 1.3 million vertices. So on the next mesh, we can see that all the detached shocks are captured. We can see also the frozen boundary layers and a distribution of the Mach. So next slides. So the conclusion, so we are ready to release a better version of adaptive mesh generation in 2D and 3D. Basically, error estimate are included, interpolation to restart. You can do surface 2D and volume mesh generation. It has been tested on a couple of in-visit run and runs adaptation. So the ongoing work is, of course, to increase the set of documented adaptive test case in 2 and 3D. We really want to push completely unstructured mesh adaptation and detail the best practice, how to set up your geometry to make sure that you are sure that anisotropic mesh adaptation or your adaptive rod is going to converge. So basically, if you want to keep in touch with us, you are free to visit the website to download the code, and also we have created a mailing list, so you just have to send an email with the subscribe topic. So I think the final slide is just a recap of the website, and thank you for your attention.
Thank you, Adrian. We do have a little bit of time for questions for Adrian. And Adrian, if you can't hear the question, just let me know and I can repeat it for you. So.
Okay, great.
Any questions? Alberto, yeah.
Yeah, more of a curiosity concerning the interpolation between meshes. Sometimes you have problems, the solutions start oscillating just because of interpolation, or you lose accuracy. So what's the trick here?
Do you hear that?
Yes. Okay. So just to make sure it's right, it's regarding the interpolation from solution to solution.
Yes.
Yep.
Okay. So in that case, we are doing only a steady solution. So we are simply using a linear approach. So there is no oscillating because we are not creating a new high order representation of the solution. I didn't talk about that, but I agree that if you really want to do, for instance, unsteady simulation, then the interpolation is critical. And in that case, we are using what we call conservative interpolation to make sure that conservative variables like the density are conserved in the computation. And we are also making sure that we are not creating local maxima, and we are verifying the maximal principle. But basically, when you are using steady solution, it's not really an issue.
Okay.
Thank you.
Thank you, Adrian.
The only issue maybe is for run simulation, you have to make sure that you are interpolating surface to surface and volume to surface in order to make sure that you are not creating some sort of velocity on the surface, which is supposed to be 0. So we are doing that.
In fact, yesterday during the hackathon, one of the projects that was being looked at is this idea that not for adaptation, but rather in order to get RANS calculations on complex geometries to converge, sometimes it's useful to run a coarser mesh simulation and then just provide that simulation to a finer mesh as an initial condition. And we're talking about all these things, so I think there may be a discussion that needs to be had. This is in particular, I think, two of the students at Stanford that know Victorian very well. It may be that you already have all this in PyAMG, and we just need to use it.
Yeah, you can do the, I didn't talk about that, but you can use only the interpolation if needed. I mean,
yeah, I was going to ask you, do you do anything particular when you have a coarse grid and now you're going to interpolate to the fine grid? But of course, you have more nodes on the surface, on the true CAD surface, and some of those points may actually fall outside of the original domain.
So basically, for that, what we have is when we are doing interpolation, we are doing a topological interpolation, meaning ridge points are interpolating with initial ridge points, and surface points are interpolated on surface points. So I mean, even if your surface falls inside the volume, we are taking only surface information.
So you're making a distinction. You're doing a surface interpolation only in a UV parametric space of some sort.
No, yes, it's more or less the case. We are trying to find the closest points close to the surface, and we are doing the same for the volume. I mean, if on one coarse mesh, for instance, you want to interpolate a mesh typically close to boundary layers, you can take the distance to the body to find the most related points in the coarse or fine mesh. So basically, we are doing an interpolation, is a distance-based interpolation in that case. And when
you do use a distance to the wall then, because we were speculating yesterday if it's possible to take the coarse grid cell and deform it together with its solution to conform to the true surface of the geometry, and then you're guaranteed that every point that's going to be interpolated is within the domain.
Yes, but in that case, you have to solve a PD. You have to solve a PD. In my case, I'm solving only a distance computation and local interpolation.
Oh, this will still be a deformation mapping, so it's a simple.
Yes, but it's local. It's completely local.
Yeah. Okay, that's really interesting. Yeah. Tom, question.
There's a question online, and I hope I didn't miss it, but the question is, can you also use it for transient problems, so dynamic mesh adaptation, say for moving shocks or buffeting?
Did you hear that?
So it's about unsteady, right?
Yeah, whether you can use the methodology for unsteady problems and adapting every few time steps, I suppose.
Okay, so in that case, it's a little bit more involved. I mean, it's possible, but we have to design a completely new script to make sure that we have we have the full picture, because we want to control the error in space and time. So I think we have to work a little bit more within SU2 and also to define a new script to do that. But for all the basic components, everything is in it. So I think it's much more to do scripting, this kind of stuff.
Yeah, so, but just to be clear, you're saying it's not ready because the conversion between SU2 and PyAMG is not ready for that yet, but in your work and Frédéric Alazet's for many years, you guys have been doing unsteady adaptation. You just have to do it every few time steps, just repeat the same process and reload balance after you do this, right? So,
yes.
Yeah.
Data structures are probably the biggest.
Yeah, so they've been doing that in their work for a long time, but of course you have to have a proper interface, and then as every few time steps you adapt, and you adapt whatever the need is, and then the calculations does not load balance, so you have to repartition essentially, or fix the partitions. Nico.
So the shear layer was frozen for this local goal adaptation. So what happens if you have a strong indication to define your mesh in the shear layer? Are you then doing a Y plus adaptation, or what's going on there?
Do you hear that, Adrian?
Yeah, sure. The frozen boundary layer is just a workaround to do runs currently, but we can easily improve the scheme. So basically, what you want to do when you impose a boundary layer is simply want to impose the Y plus 1 from the very beginning, and you don't want to wait for a long time to make sure that the size of the grid is going to reach y+1. So basically, if you have a shock or a wake or something impacting the boundary layer, what we can do, but this is not done currently, we can simply deactivate progressively the boundary layer and wait the complete adaptation to go down to y+ automatically. And that's why we currently are pushing techniques with fully unstructured anisotropic, because in that case, it's completely straightforward and all the interaction are completely handled automatically.
So Adrian, I know I always ask you this question, but when do you guys expect to fully support boundary layer adaptation? Is this a 3-year effort? Is it a 1-year effort?
It depends on what you do. I think it's an effort both on SU2 side and AMG side. Yeah. I think we have to really push to see what is the critical point of some convergence issue with SU2 when you have strong anisotropy on the surface and near the boundary layer with fully unstructured scheme.
But forget about SU2. Is this fully available now in AMG or not?
What, the adaptation with the boundary layer? Yeah, yes,
with
you can.
The boundary layer. It is, okay. I thought it was still in development. So
it is, but it's a frozen case, so it's not yet completely fully automatic.
Okay, yeah, I didn't mean the frozen case, but a true adaptation in the boundary layer is still
being... True adaptation is done. I mean, it's on the iLift CRM, so we are currently running this case to really see what is the bottleneck or what are the config parameter files that can be used to do that. Once you have that, you can do transonic with high Reynolds and boundary layers.
Great. One more question from Tom.
I have one more very practical one. So thanks again for the talk. Once this script is ready and the branch that you guys have been working on is ready, what's the practical rollout? So will the Python script show up in the SU2 repository and with the config options, and then people will go download AMG, or what's the workflow?
So basically the workflow, you just have to download, so imagine if the Python script running SU2 with adaptation is in the main branch, all you have to do is just to download AMG. It's a Python wheel. So you simply have to install the Python wheels, and once this is done, you're free to go.
Okay.
Great.
Sounds great. Looking forward to it.
Adrian, thank you so much for the work and for the presentation, and thanks for doing this remotely. So we appreciate it. Thanks again.
Thank you.
So this work is, I had introduced sort of the beginning of it last year in December. And then a lot happened in the 6 months after that, and then it got published, and I want to share all those updates so you guys know what's in the solver and what's going on. And of course, this interacts with a bunch of other things happening in the community, of course, anything from combustion to other low-speed flows, other incompressible work that you're going to see after this. So you're seeing more incompressible flows now in the code. So I think this is a good thing. So I won't bore you with the agenda, typical stuff. Let's get right into it. I'm also not going to bore you too much with the company line, but I'll at least say one or two things just to echo what Nisa was saying. So Bosch is very large, and we also invest a lot in research. We create products that are invented for life. There you go. That's a TM. Copyright, I have to say something. No, I'm serious. They invest a lot of money in research, and they're very open-minded about collaborations and open source software, publishing whenever possible. And really, it's a pleasure to be here. We really want to support the community, and I just want to make sure that message is loud and clear. In terms of the problems at Bosch, what kinds of things do we see? Not many airplanes, at least not yet. So just so folks especially in the US, it's a little unclear sometimes what all Bosch has their hands on, but we are one of the leading suppliers of, let's say, mobility solutions in the world, if not the leading supplier of mobility solutions. So automotive technology, but also industrial technologies, energy and building technologies. So you saw Niso's presentation and Daniel's work earlier for domestic heating appliances. So a lot of things in the energy and building space. And then the consumer goods that everybody knows are just, round off error, a small percent of what we sell. So that is motivation for what I'm going to talk about today. So as we all know, the SU2 started out as an external aerodynamics code. It's become pretty well established for that purpose. Typical algorithms and schemes for that kind of a scenario. So higher speed, transonic, etc. External flows. At Bosch, we're a little more interested now in internal incompressible flows and often with heat transfer. And so the question arises, well, what do we have for this type of problem in the code right now? And the answer last year was, well, little to none, kind of artificial compressibility, some basic things, but we really needed to expand that. So that's what this talk is all about. So what was in the code last time, this is sort of just a quick view of some literature of the approaches you can have for, let's say, density-based incompressible flows. And we had some things implemented in the code. The first one that comes to mind is artificial compressibility, the classic approach from 1967, I want to say, where you sort of, you turn it into a coupled algorithm, you trick the density equation into becoming a pressure equation with some, some tricks, and then you solve the problem in a coupled manner. Along those lines, you had other preconditioning approaches that would take the fully compressible Navier-Stokes equations and precondition it for low and higher Mach number flows. These are also well known in the literature. You can see some more recent work where you're working at the level of the dissipation in the schemes for doing things to make sure you can handle low speed situations. There are a few different flux schemes for that and corrections you can make. Low Mach number fixes for the row solver, for instance. And then you can go all the way to something like the Weiss-Smith preconditioner, which was set up for mixed low and high Mach flows. So you really want to handle the full regime of flow problems and do that with a preconditioning approach. Sort of a survey of what's available. Most of these, if not all, are implemented inside of SU2 in the compressible solver. The incompressible solver up until now was just the artificial compressibility approach. So last year, only working for, let's say, constant density flows without heat transfer. There is no energy equation. So with this work, what we're trying to do is find something that is in between artificial compressibility, the original simple approach, isothermal, so no energy equation, constant density. That's not quite as complicated as the Weiss-Smith preconditioner for fully compressible Navier-Stokes, mixed and high speed, because there's extra complexity there. So that's really the idea of this work, is develop a coupled algorithm, something in between, a little more general than artificial compressibility, but just for low speed and compressible flows, possibly with variable density, however, because this is important for certain applications like combustion. So that's what we're after, something in between. To do that, we're going to start with the low Mach Navier-Stokes equation. So we're going to allow for variable density in the equation set. And essentially what happens, it's basically a simplification of the energy equation in the end. So it looks just like fully compressible Navier-Stokes, except in the energy equation, it's slightly simpler. We remove a couple terms that have to do with pressure, and also there's a viscous term, a stress tensor dotted with velocity that fall out. So it gets slightly simpler, a little bit easier to handle. However, in this case, we're still going to have an ideal gas assumption. So we're still going to let the density vary as a function of temperature with a constant background pressure. So we're still going to let density vary. So incompressible flow, but variable density. So ideal gas. So we're going to start from this form of the equations. But then basically, we're more or less following the approach of Weiss-Smith. So the same kind of preconditioning approach I'm using here to create a coupled algorithm for incompressible flows. So if you follow the paper, that's a really, really nice paper from 1995. I recommend you walk through it. It's really well done. You can follow that formulation, and you arrive at something similar for the slightly different set of equations. So now note the big difference here is that was for fully compressible. I'm applying the same formulation for the low Mach equation. So subtle difference. And what you have then is you recover this preconditioner, what looks like a preconditioner out in front of the equations, this gamma, and the form is something like this. It looks very similar to the Weiss-Smith version. There's some simplification for the energy equation, again, as I noted before. And it draws a nice clear link to artificial compressibility, which I'll say more about. So the idea is we have this preconditioner, but everything else is very much the same as the current compressible solver in SU2. And there's a few reasons for that. One, we already had a nice structure, set up for solving coupled problems. So I'm leaving it to other people more experienced than myself in pressure-based solvers to work in that direction. So this is a very quick access point to take what we had and be able to add an energy equation and solve it in a coupled manner, and also have the adjoint working, which I'll talk about in a moment. So that means we can also use all of our coupled algorithms for time integration. The flux schemes also need to be modified, which I'll say a word about, but a lot of the same machinery that's already there, we can leverage again. So this is a very quick, in 6 months' time or so, re-implement what we need and get going. So maybe one more word about this preconditioner. I'd prefer maybe to call it just a coupled algorithm. It looks like a preconditioner, but it's only for low-speed flows, incompressible flows. So maybe it's sort of a hybrid approach between artificial compressibility and preconditioning. But there is a very clear link between these things, and this happens in the literature a bunch. If you read all these old papers, you'll see that people say, okay, artificial compressibility is more or less a preconditioning approach, and well, depending on how you twist it, they're very clearly related. And this really draws a clear link. If you break down looking at what beta is, so if I go back one slide, this beta squared term, this shows up all over artificial compressibility papers, or if you look back to the work of Turkel or the original paper from '67. And what beta is an artificial sound speed. So even still in this sort of coupled approach, I'm calling it, it still looks like an artificial sound speed. If you take the eigenvalues of the preconditioned envisaged Jacobian, you see exactly this. So the beta factor becomes more or less the artificial sound speed. So you're still using this artificial compressibility idea to drive the coupled equations to an incompressible solution. And again, this just really makes it clear that artificial compressibility and preconditioning, well, they're basically the same. It's very, very similar. Okay, so I'm going to leave it at that in terms of equations. I'm not going to bore you with anything else. There's a lot more in the paper. So just in June at AIAA, I put together a paper on this. So there's plenty of development in there, all the equations, the flux schemes, et cetera, all written out in detail. So check it out if you're interested. What is in there is the following. So we'll just call it a custom preconditioning method. So the reason I like this is it's a little bit simpler without needing the fully compressible Navier-Stokes equations. I find this is nice because convergence is a bit better. Sometimes I don't need to worry about limiters, for instance. I can often get away without the limiter, which helps convergence quite a bit. So I'm focusing just on incompressible flows. So Euler, Navier-Stokes, and RANS all available. You can use it in different modes. So you could do constant density. You can turn on the energy equation in a, let's say, one-way coupled manner. You can couple them and do variable density. There's a Boussinesq approximation. There's a lot in there in terms of the modeling. So it's a conservative formulation, but it's the working variables are the primitive variables. So it's a little bit different from the compressible code in that sense. And then the flux schemes have also been customized to take into account this type of approach in the dissipation terms, because they do change a little bit. And then sort of all the other same tools that we have in the compressible code. So if you're familiar with the compressible code and you go look at this version, it's going to look very familiar to you in a lot of ways. You'll know your way around. And one of the keys is that now it does enable this variable density incompressible flow. And along the way, we put in 2 new fluid models. So you, of course, can just leave the density constant, but you can now use ideal gas with the incompressible flow solver. And as I said, you can turn on the energy equation for all sorts of purposes. So as of last year this time, this was not available. And within that year, now it's all put out in version 6.1. This is all there for anybody to use, released. So it's all out. I have to say something about adjoints. I'm not going to go into this a whole lot. You guys know all about adjoint methods. We're, of course, leveraging all the frameworks we have inside of the code already. One of the nice things I will highlight is the quickness with which an adjoint is available due to the CodiPack implementation that we have embedded in the code. So for anybody who's not familiar, I think most folks in this room are. Please check out the work of Nico's group in this area for CodiPack. I was able to essentially leverage, because again, everything was already more or less there for the coupled problem, just upgrading the old incompressible solver. It was a matter of, maybe tweaking 1 or 2 bugs and just recompiling. And and the adjoint was there, consistent with all the nice fluid models and changes to the preconditioning and everything. So that is working as well. Okay, so let's talk a little bit about results. In the paper, I'll give you all the gory details about the cases and the comparisons. I'll just flash some stuff here. So in the paper, I wanted to spend a lot of time doing detailed V&V of a bunch of the NASA cases and a few others that are a little more complicated. And so all that data you will find. Even some simpler ones, starting with, okay, inviscid problems, buoyancy-driven cavities. So now you have essentially heated plates that are separated, and you let the flow be driven just by the temperature difference. Laminar flat plates, turbulent flat plates, matching with NASA cases, and doing comparisons against Fun3D, for instance, their incompressible version matching quite well. Turbulent ACA 0012, bump and channel, axisymmetric pipe. There's an axisymmetric mode as well that's in there, that's available. Laminar backward facing step, classic problem from literature. And everything, as you can see, matched quite well. Feeling very confident in the implementation, and most of these cases I just listed are now tutorials on the website. So if you want, not only is the code released, but you can go to the website. Most of these config files and meshes are there for you to run. So ready to go. One interesting thing about this, while I have it up, the laminar backward facing step, for this, we also added the ability to input flow profiles at your inlets. So that's also now available. And if you want to learn how to use that, check that tutorial. So that's now an option. Okay, maybe a little more advanced. Not too much more. It's still a simple problem, but we're also running things, you know, in 3D, internal flows, turbulent type calculations. It is just a quick qualitative view to say that things are matching quite well. We're feeling pretty comfortable with the implementation. This is just a constant density problem. And it's working for some complex geometries as well. So this was just a quick test. I had Daniel convert an old mesh from the open for this one, but this is just a car geometry, Reynolds number 6 million. Things are behaving fairly well. So again, this is available for you to use anytime. All right, now one case to actually show the adjoint and some optimization work. So this is a talk about variable density and compressible flows. So this is a very simple variable density incompressible flow. Basically a 2D pin problem. So we have a heat sink type of concept. What I'm showing here is density, velocity, pressure, and temperature. So the pin, if you want to call it that, is heated. It's not a great resolution there, but the wall, so that's a 1000 degree Kelvin pin in a 288.15 Kelvin free stream. And it's using ideal gas. So it's variable density with the ideal gas law. So you see that density is varying here in the flow around the pin. That also causes a change in the pressure field. So this is a true variable density case with a pretty high speed or pretty high temperature pin inside, so that you see the effects. So what I'm doing here is setting up 50 FFD variables on the top and bottom of the pin. So essentially these two rows, top and bottom, are allowed to move vertically so that you can get the deformation you see on the right. That's the mesh in the background. Of course, the first thing we do is check that the gradients are working okay. Everything makes sense. This is a comparison, finite difference, direct differentiation, so forward mode, and the discrete adjoint for a drag objective with respect to all 50 of those points. And maybe a little bit hard to see, but the only one that I don't trust is the finite difference. I think the other two are right on top of each other, and so everything's okay here. And as further evidence of that, this is another quick check that the gradients are okay for a integrated heat flux objective over the cylinder for the same 50 points. Direct differentiation compared to discrete adjoint, which are matching wonderfully, but I couldn't actually get a step size with finite difference that would give me reasonable results. So I think it's another important thing that you see where we're able to get very high quality gradients in this case. So we feel confident the gradients are okay. So then just an example of what we can do for shape optimization. So this is just a heat flux minimization. Well, let's say it's a minimization in the sense that we're going more negative, let's say, from the heat flux that's leaving the pin. And And the top right is just a picture of the mesh as this goes. So just to orient you a little bit, we have heat flux here. So it's a heat flux minimization with a CD constraint, I think to match the initial, which is around 2.06. And this is showing the major optimizer iterations, I think, not just the evaluations, but the major optimization iterations. So if I play that again, oh, it loops. Okay, good. So like some folks in the room have said earlier today, the optimizer, when you're trying to get the constrained problems to work, the SLSQP is not very forgiving. So I would second that we improve that. I think there are a few branches of the code that have different optimizers hooked up, but I think it's time that we move some of that to the develop branch and really integrate that, because I've had a lot of conversations with people in the room the past 2 days, and I think I've had conversations about that 3 or 4 times. So, but this one, it behaves okay. We're able to improve heat flux and more or less match our meet our drag constraint. Okay, so we can also do design for something a little more complicated. Again, not too fancy, a 90-degree bend, but it's 3D. Okay, so a little more interesting. Same type of setup, but this time it's a custom objective function to minimize the tangential velocity at the outlet plane. So what we're trying to do is essentially make that whole outlet plane blue. Just trying to minimize the velocity there, the tangential velocity. There's an FFD box sort of in this area, so I'm going to show the pipe, the changes of the geometry in these 2 areas. And the bottom right is the objective. I'm calling it the secondary strength. This is from a paper from some of our collaborators at Stanford, Andrew Benko. They have a few metrics they like to look at for the strength of secondary flows inside of internal flow problems. And this is a metric he came up with. I borrowed it and implemented it to do this kind of design. So yeah, you see some interesting changes of the geometry to try to basically remove some of the vorticity, some of the vortex inside of the pipe. This is SST. No, maybe this is laminar. This might be laminar. I have an SST version, but this particular one is laminar. By the way, we're using SST most of the time for internals. One more thing. Okay, this is my last couple slides. I think some of you in the room will be very happy to see some of this, although I have to admit it's not finished yet. But one more thing, periodic boundary condition. This has been, I think, a pain in a bunch of people's sides for years. And I've promised many a time to fix it, and we've tried to fix it many times. And I finally said, forget the implementation we have, let's rewrite it. So the way it's done now, I have a branch where this is working. Not fully functional yet, but soon it'll be finished. New implementation style. So the periodic boundary condition is now based on the concept of completing the residual rather than adding halo cells. So the way it used to work is we would find this row of cells up here, and we would copy it down here, and then we would do essentially an MPI communication and let them compute their full fluxes and loop over their nodes and let it carry on. The problem with that is the complexity with which it's required to set up these halo cells when you start to have adjacent periodic faces and you're doing MPI and you're partitioning and you have 2 sets of things you're partitioning and communicate. It gets a little complicated and it gotten sort of clogged up. So I'm trying a new implementation where it's based on just completing the residual. And so at least for actually flow problems in general, this is working fine. So this is just a simple external flow case, but periodic on the top and bottom. And I'm getting everything matching quite well, even second order. You have to be a little bit careful with making sure your gradients are also consistent, things like limiters. So since if I come back, what we're basically doing is computing half of the residual here, half of the residual here, and then they communicate the residuals to each other rather than changing solutions and computing the fluxes themselves. So it's a little simpler in terms of the geometry. It's still complicated in terms of some communications, but it's actually quite a bit easier to implement it this way, I'm finding so far. So working fairly well for at least simple problems. And the beautiful thing is in this formulation, it's easy also to get triply periodic things or adjacent periodic faces to work now, which also had not been working. People have been asking for this for a long time. So this is not exciting. This is just maintaining a free stream in a cube, but it's possible to do this kind of a problem now as well. Same approach, and the problem here is that this node on the corner is defined 8 times. So you have 8 partial cells that have to sum, and so you have to go X, then Y, then Z. Anyway, this is coming. And maybe just a last note, some folks may have seen, you can now export pair-view binary output using parallel capability, so with MPI-IO. So you don't even need to call SU2 SOL anymore. You can just export parallel binaries when the restarts get written, and it's pretty high performance. It's working quite well. Okay. So just to wrap up, in the first part, we talked about the density-based incompressible solver. You could either see it as a generalization of artificial compressibility or a simplification of Weiss-Smith preconditioning. I found that adding the preconditioning to all of the equations is very important. So making sure you're treating all equations in the system with this preconditioning was important for stability, especially for RANs. And now we're playing around with this, adding extra scalars and whatnot, and also adding the preconditioning to those scalars can be important, and we're investigating that. I think NISO's already done some work there. Showed a lot of V&V cases with classic stuff. V&V, so everything there is available for you. So it's open data, the source code is there for you, open to the public. There's tutorials telling you how to use it. Everything is open. So I think this is really critical. Just, give everybody everything in the open data to reproduce it as well. So I think that's, I'm very happy in this group. We do a lot of this, and I hope we all keep doing that. And lastly, it's meant as a reference. So very excited to see what we build on top of this. And also there's going to be more work presented in a moment about pressure-based solvers, and I hope we keep building in that area too. Really just improving what we have for incompressible and low-speed flows is, I think, going to be a growing area in the next couple of years. So looking forward to that. Okay, that's it. Thank you.
Great. Thank you. We have time for questions for Tom.
I'm sure you can imagine my question. I'm super attracted by this development. We would like to go into incompressible flows for heat exchanger problems, but we are interested in complex fluids. So have you thought about that?
So you will be happy to know that the fluid models I added are built directly into your guys' classes. So I've already, alongside what you have there for ideal gas and van der Waals and Peng-Robinson, I have new ones that I put right in line for constant density, incompressible ideal gas. Any interface you add there, it'll work here. Already thought about that. We also have an interest in complex fluid models. So I think it's already well aligned, yeah.
I don't think Kira was expecting that answer. Look at his smiles.
Big smile.
Yeah. Other questions for Tom?
Yeah.
The periodic So what is actually the...
I was hoping you'd be happy, you wouldn't ask any questions. Anyway, go ahead.
I mean, what is now that, so you showed some scripts, have you done, for example, tests in which you have a shockwave entering?
No, nothing complicated. So right now it's only in the Euler solver, but it would work for viscous problems too if I just copied it in the right place. I haven't done the limiters yet. So anything where you're looping over your edges and you have, let me put it this way. You're going to compute the residual. So whatever you need to compute the residual, you have to make sure is available to those two nodes. So I need to make sure that the solutions are the same and say the gradients are the same. And if there's a limiter multiplying it, that needs to be the same. And the problem there is if you're looping over the edges to compute the limiter or you're looping over the edges to compute the gradient, you only have half of the cell. So I need to do something there. I've already done it for green Gauss. I need to do something for weighted least squares and the limiter, but I don't see any showstoppers. Okay. Other than that, it's improving the performance because, yeah.
Eventually, then the idea would be to replace completely the SU2 mesh stack.
So after thank you for saying that. So you do not need to call a preprocessor anymore. This is on the fly. So we rewrote the whole partitioning input. That was earlier this year. I should have put a slide on that. The whole mesh input has been rewritten. And so that's all very clean now. And in doing that, part of it was motivated by fixing this problem. But then I just said, forget that. We wrote it clean. The grid input and the partitioning is now clean. And then we always had wanted to do this on the fly. So you shouldn't have to run a preprocessor, get another mesh to go run. So the idea here is you just, same options, you put periodic 1 and 2, and you just call CFD now, and it's going to take care of this. And that's how it should work. So, yeah.
So you said you implemented a axisymmetric conjugate.
Yeah, that's there. So the source terms are a little bit different for the incompressible equations because my energy equation is simpler. But we had exchanged some emails. The reference that we were using is a good one. So, and in the paper, if you want to see the source terms, just grab the paper, at least for incompressible. But yeah, it's very similar.
Mm-hmm. Do they use the rotating frame of reference?
Yeah. So the old incompressible solver did not have any of the grid movement or ALE stuff. Sharanya, who was one of Rafa's students, I don't know if they're online maybe, was at Bosch with me over the summer, and she had done a nice job to start putting in all of the ALE formulation. So rotating frame, any of the pitching, plunging, grid motion stuff, along with all of the flux corrections, so you have grid motion. So it's in development stages, but yes, we clearly want to do unsteady problems, and also, yeah, we're interested in unsteady problems at Bosch too. So not as much rotating rotor blades, but it's a good place to start for checking all that development anyway. So that was one of the first places we went to.
I don't know if Rafa is there, but I unmuted him. Rafa, if you're there and you want to make a comment, you're more than welcome to. If you heard the. Maybe he doesn't
Maybe
know.
not. Maybe not.
Let me mute him back up. Yeah.
Long story short, yeah, it's under development. So.
Any other questions for Tom? So, Tom, on the on the parallelization of the periodic boundary condition, that can get complicated, right? If you have, let's say, a node that shares 2 periodic boundaries.
I know.
And you have a boundary partition that goes right through those nodes. That, I mean, this in the early days of parallelizing codes gave people a lot of trouble. Right?
So that right there is what I wanted.
Yeah.
This is a good example because at these corners,
yes, yeah, absolutely.
You have it. It's actually the corners are defined 8 times.
Yeah.
And they share multiple faces here. So what's nice about this is they only have to worry about their local edges.
Yeah.
And they're going to compute what's in their dual. Part of the problem is we're vertex based, so we sit on the surface,
yes, exactly.
which makes it even more complicated.
Exactly.
If they just take care of what they need to do, if they start with the right solution and the right gradient, compute their little piece, then it's actually quite easy just to, I mean, as long as you track.
But then you have to accumulate, right?
You just have to make sure you go X direction first.
Yeah.
So then this 8th goes to this 8th.
Yeah.
Then you go Y direction. Half goes to whatever, and then you go Z, and it works okay. So this is working in parallel too. This is working in parallel.
Okay.
Yeah.
All right.
I think it's going to work.
I
need a little
remember
more time.
that being complicated, but
yeah, it's not easy, but it's going to work.
Especially in the vertex-based code. The cell center would have been easier. So. Okay. Well, thank you, Tom.
So good evening, everyone. I'm Akshay. I'm doing my PhD now. I work with Edwin at University of Pente, but mainly work at ECN with Hussein. So this is still a project under development, and I'm still in very early stages. So the whole idea is to just put this idea out there. The idea is to implement a pressure-based solver, and as Tom also mentioned, the incompressible part of SU2 was not really good so far. So we're just working on it. So the outline of my talk today will be, I just give you a brief bit of context on who we are and why we are interested in this, and then just explain to you what is the research plan I have, and finally, in the end, I'll just show some of the things that ECN is interested in doing and have used SU2 for, and what we're planning to use in the future. So ECN, or the Energy Research Center of the Netherlands, we are an energy research company, and we recently merged with TNO's Natural Science Research Company, and we focus mainly on renewable energy technologies like wind, solar, biomass, etc. We work on the wind energy unit in the aerodynamics group, and traditionally at the aerodynamics group, we have had a variety of low fidelity tools used to design the whole gamut of the wind turbine design. So we have had boundary layer tools for airfoil analysis, lifting line BEM method tools for blade load computations, and so on. And right up to wind farm optimization and design, we use parabolized Navier-Stokes tools. So so far, these are all low fidelity models, and with the industry is growing and so on. So we are now looking to use the CFD for a lot of these operations. And one of the main reasons we chose SU2 is that it's easy to get into the development process. And so with this, the typical applications we have at ECN are generally airfoil analysis with add-ons like flaps you can see here, or vortex generators and so on, lift enhancement devices and so on, or wind turbine rotor simulations, again, periodic boundaries, and so on. And the other last one, as I mentioned, was the wind farm design, where we represent individual wind turbines with actuator discs and try to design the layout of the wind farm to extract the most energy as possible. And typical use case at ECN, or when you're dealing with wind energy, is that you're typically dealing with very, very low speed. So you're dealing with a few meters per second, 10, 12 meters per second. So you're essentially zero Mach number and very high Reynolds number. So under this situation, the artificial compressibility method that was there till at least some time ago, we did not have very good experience with using the unsteady problems, especially, and even with doing the steady state problems, we had some issues with the mesh requirements were quite high. So so if we wanted to use SU2 as the base for our future developments, we decided to first implement a pure incompressible solver. So the idea was to do a pressure-based solver, and so this is where I come in, and I in my PhD I'm planning to implement a segregated pressure-based solver based on the simple family of algorithms, simple R, simple C, and so on. So the main difference from the existing code layout or the governing equation layout is, instead of solving all the equations in a coupled way, we are now, it's somehow a predictor corrector type approach, where we are first solving the momentum equations and we then try to satisfy the continuity criteria by a pressure correction equation. So a lot of code is reusable, but it involves some restructuring in terms of the way the iterations are carried out and some of the way the code is coupled. So the research plan I have for my PhD project is, since I'm very new to SU2, I needed to sort of get familiar with how SU2 works and how all the ins and outs of the code. So the idea was to first go slowly and first develop a research code which sort of mimics what SU2 is doing right now, develop an artificial compressibility version, try to implement the same way, and then convert that into a pressure-based solver. With this idea, I can then slowly go into SU2 and then implement it. So that was the research code part, and then the idea is, the first thing I realized is, you can see from the governing equations, so the pressure correction equation or the discrete continuity equation is of the Poisson form. So we needed a Poisson solver for that. The existing Poisson solver in SU2 was a finite element one, and yeah, we wanted to maintain the consistency in the discretization. So yeah, the first thing I did was to implement a finite volume discretization for Poisson. And then, yeah, just to follow the same sort of implementation structure in SU2, where you discretize the convective terms in Euler solvers and then to discuss until now. So just to follow the same thing as exists. So again, as I mentioned, it's still very early in the development stage, and I don't really have a lot of results per se. So I'm just going to show you some of the things that I have from my research code and what I am planning to do with SU2. So the research code I wrote is just basically solving the standard lid-driven cavity problem. Try to keep a very low Reynolds number so as not to get into the turbulence and so on. So try to maintain the vortex-based finite volume. The boundary conditions are a bit tricky compared to the cell-centered, so wanted to maintain that and yeah, basically follow the same sort of existing features in SU2. So I just compute the velocity along the center line, like in the lid and just compare it with some benchmark solutions, and it works quite well. So yeah, now I'm in the process of implementing this in SU2. So the first thing I did was to extend the Poisson solver for finite volume discretization. So I tested with some analytical test cases and so on. I have not put the results here. There is simple sinusoidal problems, but the main sort of the roadblock or the challenge with pressure base is that you have to solve this Poisson problem multiple times in a single time step. And Poisson problems can get extremely expensive. So the idea is to use multigrid, and yeah, the multigrid already exists in SU2. So I just extended the multigrid for Poisson, and Poisson is generally sort of tailor-made for multigrid, so it's an elliptic problem. We get very good speed up as expected. But one of the comments, one of the things that we might need to look into is an algebraic multigrid, because when you're looking at unsteady pressure-based equation, you're having to do multiple, like with the dual time stepping, especially you're doing many Poisson solves within the whole problem. So that might be something that is in the future. So this is the current stage of the research I have at in SU2 right now. So the idea is to use the same sort of fluid driver structure and everything, but it's still the iteration structure, and the solver, the numerics, well, of course, will change because there is now no acoustic waves as to help with our characteristic boundary conditions and so on. So there is some change in the philosophy of the way we write the upwind schemes and so on. But it's a work in progress right now. I'm using the research code I have, and we are trying to implement different problems in the research code and comparing results and so on. So the work in progress. And the other things, of course, I'm still doing in a serial program. I need to extend it to MPI, and it's probably in the wish list is to add periodic and ALE formulations and so on. So this aspect was just about my PhD project and what I plan to do. At ECN, we also have some other plans for SU2, and yeah, just to show some of the earlier results we did with SU2 is fairly like straightforward. Here we're just comparing with the open form. So this airfoil was used in one of the cases where this was this was one of the proposed designs to replace wind turbine blades. So this sort of structure is attached to a cable which is going to move in a 8 sort of a loop, and that movement is going to generate the power instead of having a standard wind turbine rotating. So this was one of the concepts we tried. So here we compare the results with open form, and it's fairly good. And this was actually carried out in the version 5 of SU2. It's quite old as well. And yeah, the other sort of things we are looking at ECN are wind farm modeling. So where we're trying to use actuator disks to approximate each of the wind turbine in a wind farm layout. So the way we do right now is use a parabolized Navier-Stokes. So essentially we separate each turbines by themselves, and we compute the weight behind the turbine and sort of feed it in a serial way, like each turbine interacts with only the turbine directly behind it or directly in contact with it. So there's no upstream influence, or there's no interaction within the farm. So the idea of using the actuator disk in SU2 is to leverage the full Navier-Stokes capability and try to get better wind farm layouts and so on with this actuator disk approach. So these are some of the things we are planning to use SU2 for, and yeah, it. Thank you. It's relatively short because we're still starting off, and interesting to hear your comments. Thank you.
In the test cases you showed at the end, that you had run this were with previous versions of the compressible solver, I imagine, running at fairly low Mach number, or was it artificial compressibility?
This was with the artificial compressibility, and yeah, I think this was with artificial compressibility. These are all the same
It's about the code development part. So you're working on the Poisson solve. Are you putting that all inside of the solver class, or are you going to have a segregated solver for Poisson and a solver for flow?
I have a segregated solver right now, because somehow it's basically couples, like the same way you couple the turbulent solver with the flow solver. So it's similar sort of like coupled right now. It has its own solver direct Poisson numeric.
Okay, so you left it completely in its own file. I guess, yeah, apart from the algorithm being segregated, I guess I was interested in the files and the classes. If those are segregated. Okay, so those are also separate. Okay.
I was interested in your suggestion of using algebraic multigrid for the Poisson solve. I mentioned this morning very briefly that we had some discussions with the folks at Livermore, Lawrence Livermore National Lab, the hybrid, I guess, library that they put together that has an algebraic multigrid capability that is pretty good. So we were thinking of trying to prototype something together with them. Normally, people think it works fairly well for scalar equations, but when you get to systems of conservation laws, it's not such a so if you want to think about doing that, that's publicly available. At least the prototype.
Yeah, actually, Edwin, the supervisor, he has a AMG library which I'm actually testing with my research code.
Algebraic.
Yeah, algebraic.
Okay. I didn't realize I wouldn't have been working on that.
So yeah, I mean, I'm still doing it on my research code.
Yeah.
Good.
Yep. Okay. Any other questions? We're ahead of time, so let's thank Akshay again.
Yeah.
So
thank you.
Right. Thank you, Juan. So my name is Ruben, and here with Tim, I think most of you, if not all, already know us quite well. And we're here today to present this initiative that has been going on for a few months, which is the idea of putting together a developer society, an international developer society. So this has been going on since the beginning of the year. That Tom and Francisco and Tim have started it, and then I've been giving a helping hand over the last months as well. So the first question that comes here is why are we putting together an IDS? What's the objective of the IDS? Well, I think it becomes quite obvious that we have a lot of interest in SU2 from many people from all over the place, all around the globe, from academia, from industry. So I think it's pretty safe to say that SU2 is a global product, right? And as a global product, there are a lot of agents involved in the growth of SU2, and not only in its present, but also in its future. So some of the agents involved, we can classify it as organization. So we have academia. There are a lot of people from academia involved in SU2. There are a lot of people from industry. We have been growing the number of industrial partners lately. But also among the organizations, there are individuals that we can classify as users, people who are just using the code, or not other people who are developing the code. And all of these people have an impact on where the code is now and where the code is going. So the idea behind the IDS is to give a helping hand in bringing together the developers. So the developer community, people who are putting code into the code base and who need help into, well, how do I implement this feature? How can I immerse this stuff? We saw it yesterday in the hackathon. There are a lot of open topics. And I think the idea behind the IDS is to bring all this community together. So if we look at SU2 from a bit of a businessy approach, this is, I guess, the only non-technical presentation today, we can say that we have a lot of aspects that the community has to manage together. So on one side, we have administrative management that the IDS is not concerned or not involved in. But of course, we are all aware that there's a lot of need for administrative managing, resources, managing legal aspects, managing marketing, etc. But then there's also technical management and a lot of aspects that need to be taken care of. So for example, maintenance. We have a big code base, over 250,000 lines of code that needs to be maintained. There's a website, there's a tutorial website, there's documentation. All of these aspects have to be maintained. Also, there are some other aspects like development. So we need to define not only where we are now, but also where we're going, what's the strategic direction of the code, what are the new features that we want to see, not in 1 year time, 5 years time, whatever. Also, there's aspects like training that are very important. And in training, I want to make the distinction between training users and training developers, because there's a big distinction there. You want people to use the code and for the code to be easy to use, but also you want developers to be able to implement their very nice features and do it in the best possible way. So we all benefit from that. And the same applies for support. People might have questions. People maybe want to learn how to use the code. Users might email us and say, oh, how do I use this nice feature that I saw in your paper last year? So the IDS is mainly concerned with aspects that relate to training and support developers, and also to help out on the definition of the strategic direction and the new features that we want to have. So let me illustrate a little bit what I mean by this, starting with the development part, so the future of SU2. So when it comes to the SU2, where we want to go, what new features we want to have. Of course, it goes back to the agents that I was mentioning before. We have academia, we have people in academia that want to do cutting edge research. So what someone from academia may want is, okay, I want a product that has the latest methods, so I can do cutting edge research. Or I want to leverage on the community's expertise, and that has been quite successful. And we can see from today that we have a lot of collaboration between different groups in academia. So all of these ideas go into the direction or shape where we want to be. Also, we have industrial partners, and industrial partners might say, okay, it's very nice to have the latest methods, but what I want is something that is reliable, or what I want is something with which I can obtain a fast solution, or something that is easy to integrate into my processes. So of course, if there are changes required in the code to achieve these goals, that also affects the strategic direction of SU2. At the end of the day, both these groups want SU2 to fit their needs. But also, if we bring it down to the individuals, we get the user community. And the user community can come from industry, can come from academia, can just be people who are hobbyists and they just like to run SU2 and to play around with CFD. And users, what they want is a product that is easy to use, right? So it's a product that is well documented, that has a lot of tutorials, that people can get quickly started up with it. Another group of individuals are the developers. And being us in that situation, what comes through our mind is, okay, I want something that is easy to extend, or I want my contribution to be used by others, or I want to get support from other developers. So you have a cool feature, I think I can help out with what you have, I think you can help me out as well. Why don't we get together and we get hacking in the code? At the end of the day, both users and developers want the SU2 to make their life easier. And the idea of the IDS is to make the life of the developers easier. So to be able to give it a joint voice, or to bring us together to have a forum where we can chat about developing issues all over time. If I now go to the training and support parts, again, we go back to this individual's point of view. So respect to training, what I'm referring to training is we need to have tutorials, we need to have courses, maybe, or we organize workshops every so often. When I talk about support, it's more about personalized attention. So both aspects need to be taken care of. And of course, users want training from the perspective of, I want to use the code. So what kind of tutorial they want the user? Okay, I want a tutorial for SU2 for aerodynamic design. I want to learn how to use SU2 for aerodynamic design. Or for example, I want to get started. So I think a good course will be to have a getting started with SU2. And that's what users will be interested in. At the same time, what kind of questions will SU2 users have for support? Well, why is my code diverging? Or how do I use this feature, right? So those will be questions that users will ask all of us here. On the other hand, we have developers, and we have all the ones that have been developing the code. We have all been at that position of, okay, I have this code in front of me. I need to start hacking in for my PhD. How do I learn? So developers may be more interested in a tutorial about code development guidelines, or on a course on how to leverage on the class structure to implement a new solver. At the same time, what kind of questions will a developer ask a hypothetical support? Well, how do I implement this feature? Not how I use it, but rather how do I implement this in the code without breaking anyone else's code? Or why is my branch not passing the regression test? And I think that now after the hackathon, that's already a bit more sorted, but of course, anyone starting have these kind of questions. So the goal of the IDS is to, again, bring us all together and try to respond to this kind of problems, right? So now I will let Tim to go ahead and explain a little bit more on the mission of the IDS and the initiatives that we have thought over the last months, right?
Yeah, thank you. So taking on from where Ruben was talking about, so how do we actually, so what is actually then now the concrete mission of the IDS? So the first thing is we want to connect. So we want to organize and promote the exchange amongst all the developers. We saw already yesterday that here and during the hackathon this works actually quite well, but we want to scale that up. So we want to have that not only once a year, we want to have it permanently, every day. The second thing is we want to inspire. We want to promote the growth of the code by supporting developers, but not just us three supporting the developers, but also the developers themselves. They should support other developers. So, and I think we need that in order to grow the code. And the last thing is we want to represent the interests of the developer within the whole SU2 ecosystem. I want to go into the details now on what concrete things we plan or what we already have. So in order to connect the developers, first of all, we want to simplify the communication channels. At the moment, there's not a clear channel on which the developers can communicate. So they are all over the world, and actually we have no idea on the concrete number of developers. And we want to create, first of all, a single mailing list, so that people know, okay, they can register there and to get the newest information and stuff like that. What other developers have planned. No more scattershot emails. So I want to consolidate all this information. And then one of the most important things is we want to keep the developers posted with planned releases, workshops, activities, and other ongoing things. Although GitHub is already quite nice in providing this information, it only works if you open a pull request or something like that. And we want to start even before people open a pull request. And then, of course, we also want to set up some regular calls to coordinate some of the technical details of the code. I want to get people involved in also the major reworking of the code, like we proposed yesterday with the output and the input and output structure. We want to get the people involved there, so that they can also give their ideas on these topics. And then we want to encourage also technical discussions amongst all the developers. So we already have, I will show that later, the forum, but we want to extend that to be more like a social network. So we want that people can search other people to see what they are working on and stuff like that. So they really should get in contact. Yeah. Although in the past this person-to-person communication was working quite okay, and yeah, otherwise we wouldn't be here, I think. But in order to grow, we really have to scale that up. Also that we avoid, for example, duplicate work and stuff like that. Yeah, so this, people should know what other people are working on. And then encourage, yeah, this is the result, and we want to encourage more collaboration and inspire also new ideas. I think we also saw that yesterday, that can be quite fruitful. Yeah, the next thing is we want to inspire. So inspire the growth of SU2. And first of all, the society is an open community. Yeah, so it's a non-profit organization. Yeah, it's completely open for anyone. Even if you have not coded at all, yeah, it's absolutely no problem. We want to guide you all along that way. There is not only the coding side that we are interested on. So it can be also some non-code contributions that you want to work on, like some training material or something like that. And we also want to encourage that. And then, of course, one important thing is that we know that it is hard to get some volunteers because there's always some work that's not that glamorous, right? And for that reason, we want to incentivize the contributions of people. Yeah? And this is why we have thought of a member grade system inside the society. Yeah? So we want to give the term SU2 developer actually a meaning, so that people can say, okay, I'm an SU2 developer and want to define what they mean. And we want to reward things that are maybe less glamorous. We want to encourage that people do some code revisions on GitHub. We want to, we want to encourage them to give some comments on new features and stuff like that. And then, to go to the membership system, we thought of the following way. So the most basic member grade that we have, we call it a junior developer. Yeah, so this is open to anybody who has an idea on what he wants to do with the code. Yeah, it doesn't matter whether he started with the implementation or not. This is open for anyone. The second grade is the developer, and that requires some demonstrated contribution. Yeah, but not only code. It can be also, like I said before, it can be training material or whatever, some tutorial on how to get started with the coding and stuff like that, or some GitHub tutorial or JIT tutorial. Yeah. So we want to really incentivize everything. And also developer is the minimum level to vote on some elections that we want to have in the future. And there's also time things. So I mean, we don't want to be that strict on this time requirement, but there should be some time that you could show that you worked on the code, or you wrote something, some tutorial. So the next level would be a principal developer, and here we are a little bit more strict. So we require at least 4 years of proven record. And it also requires a recommendation letter from a principal developer to, again, foster communication between developers. And this will be also the minimum level to hold some office in the future structure. Then there is last grade, and that would be the senior developer, and that requires 8 years of proven record. Since the code is only 7 years old, we don't have one at the moment. And this one would be the minimum level to be, for example, a repository maintainer. Yeah. But how can we actually make sure that that someone can demonstrate this track record? Yeah. How do we define that? And for that reason, we thought of some kind of currency. Yeah. We haven't thought of a name how we should call it. Yeah. But we just call it project currency at the moment. But we thought already of this. Yeah. This. I don't know how to call it. Yeah. We have to define that. Yeah, but we want the contributions that people delivered. We want to be that it's countable. Yeah? But not all contributions are, of course, equally weighted. So, for example, how you can get some of these currency points would be the following: through some forum posts, social media posts, pull request reviews are very important. They probably count more than just the social media post. Some tutorials, then also publications on some development are also important contributions. Then, of course, also author pull requests, and finally also merged pull requests. But we want to also incentivize also the hosting of some workshops. Yeah, or maybe some hackathons or whatever. Yeah, so even that will give some points. But I want to emphasize that that all of this is not final. Yeah, so if you have some ideas, we would be happy to hear these things. This is just some sample from that. So we have already a website and we have already some features there. For example, we have forum. We have some some profiles for every member where you can put in some information on what your main area of work is and how to contact you. Yeah, so we also plan to have publication lists, then this point system I was talking about before. We want to have some direct messaging, so that you can directly contact people within this platform and you don't have to rely on email or whatever. And then maybe also to create user groups. Yeah, so if people team up on for the development of some feature, then it would make sense to have this somewhere in this web portal, so that people know, okay, this group is working on that feature, how to contact them. Yeah, like it's written here, still everything is a work in progress. And this is the website is at the moment set up in WordPress, and if you have some experience with PHP or WordPress, get in touch with us. We need every help we can get. And then the last thing is we want to represent the interests of the developers. And for that reason, we plan to have a system like other non-profit organizations consisting of a small number of officers with the president and the vice president. And they will be appointed by direct votes of the developers. And they perform special duties then. And other work will then be delegated to some special body. Yeah, if you want to learn more, just go to the website. Or if you want to help out, we're really happy if you do that. Just write an email to admin@SU2Dev and can help with that. Okay, thanks for your attention.
Questions for Ruben? Suggestions?
I have one. Oh, sorry. Nice.
I mean, so there are already forums, like for instance physics forums, where you have a system that is similar to what you are proposing. So you can get points for helping people. You can write tutorials on the forum, and they keep track of this. You can become a gold member, etc. So have you looked into how other people are setting this up? Like for instance, the
kind of existing firms?
Of course, we saw some example. I mean, for example, Stack Exchange is one of the
Stack Overflow is a classic.
Stack Overflow. It's one of the things that come up right when you look.
Because I guess a lot of these ideas are not are freely available. I mean,
of course,
just,
yes, yes.
Implement existing.
Yeah, exactly. We're still debating on what would be the best system and how to set it up correctly on within this portal that we have. But this is, yeah, it would be similar to that actually.
I had a question. So one of the things that intrigues me most is the connecting of each other. So avoiding redundancy, making sure we have good communication lanes when people are collaborating on projects. So I really like in the website you've already set up that we can do that with the profiles, having searchable things in a social network. One thing that's always been missing from GitHub, there is a GitHub option to do projects. I've always felt that we're missing one piece. It's something that's lightweight project management. So if 5 people from all around the world are hacking on something, we need one really simple way that's not a whole lot of overhead to update it. Do you think we can embed something in the website you've set up that just, you can group maybe a handful of people and say just a couple bullets, we're doing X, Y, Z? Is there
I mean, for example, we could use the forum for that. I mean, this is the forum. I think that would be the easiest way actually. Yeah. Otherwise,
projects featuring
there's a projects feature where you can set up new projects and sort of track your issues and pull requests as they get finished.
Separated by project, so it does not spill over, but people can search.
Yeah, it's just a way to link. So in the top bar, there are issues, there are pull requests, releases, etc. There's one that's projects. And inside of there, you can create a new page and you can maybe list a bunch of issues that you're working on and maybe some pull requests that are related, and you can sort of make task lists and check things out. But we never really, it's a little bit of work to maintain, and we never really rallied around that idea. So I mean,
yeah, and you cannot really say, okay, what people are working on what thing. This is not possible. Yeah.
People, so it's another
thing. Thank you. Very interesting. I just wanted to share with you an observation. I don't know how many people are already actively participating here. The thought that came to my mind while you were talking about ways of engaging developers, which I think is extremely important, and maybe even critical now, because there is the need of raising a new generation and so forth. Of course, in volunteer communities, recognition is very important. On the other hand, if you make it too deterministic, I've seen there immediately, I recognize myself, the engineering approach, making it deterministic with coins and etc. I have the impression it could be overdoing that. Looks like something you would not end up doing unless the community is super large. If it's a smaller community, maybe you have to leave it more to subjective decision. Recognizing is extremely important, and maybe you want to have during the developers meeting a moment in which a plaque is given or some public recognition is given.
Yeah.
But I'm not sure. I wonder what you think about it. How many developers are out there would be available to spend their time?
This is something we don't know.
How many folks have,
well, we have like 110 people. Yeah.
110 people participate.
Yeah. But that doesn't mean that they are actively developing.
Exactly.
This is yeah. But this is something we don't know. Actually. This is what I meant. So,
I mean, this is the idea, though, is we really want to find a way to incentivize people, because it is, I think, the way if we can take advantage of this huge group and grow it and scale it, that's really our huge advantage. So I'm definitely open to these ideas. We don't know. We wanted to propose something and see if it stuck. So at least, yeah, this is just one concept.
At some point, you're going to have to try something.
Yeah.
And see how it goes. If it doesn't work, you have to be willing to change.
Okay, any other thoughts? Let's thank Ruben and Tim again. I guess that means that we've reached the end of the day. So congratulations for making it through. 13 presentations, that's quite a bit, right? Congratulations again. Thanks to all of the presenters for not just doing the work, but putting together some very thoughtful presentations, which obviously are showcasing some amazing things that are being done. I just wrote some notes to myself here as I was listening to the presentations today. I have to say, I'm always amazed at sort of how much things are progressing from short periods of time. I mean, it was 9 months ago that we met last time because it was December, right? So we really are, I think the community is living up to the spirit of leveraging each other's expertise and contributions in order to make new contributions, but also to progress more quickly. So I think I see a little bit of evidence of the progress of research, implementations, and applications being accelerated. I'm really happy about that because that was one of the things that I think as a community we've always wanted to do. I was pleased to see exciting ideas. I would say very high quality work, excellent collaborations. I think these have occurred naturally, but it is very clear that without some of those collaborations, none of the projects that were relying on those collaborations would have progressed that quickly. So I think what heartens me as well is that you can see that the community that we have that's very strong, it really feels like a community. So people are helping each other out nicely. So I enjoy that. We are going to go outside, I think, Marco, and take a picture before everybody disappears, like last year where we only had like a third of the participants or something. So we'll do that in a minute. But before we wrap up, I also wanted to open the floor for comments. And I want to start with both Marco and Tom to see if you had any final comments or remarks or any thoughts that you wanted to share. And then we'll go through the audience to see if we could have a little bit of the debrief and some questions, suggestions, et cetera, et cetera. So who wants to start?
Maybe just a comment. Today was obviously really high quality work. I wanted to say something about yesterday.
Mm-hmm.
I thought that the hackathon yesterday was really great, the level of in-depth discussion. I think some of us were talking last night. There was less short-term sort of hacking than I thought would happen, but maybe more importantly, there were a lot of deep conversations with planning. And I think you can only really get to that depth when we're here for 4, 5, 6 hours together in person. So I was very pleased. I think that's going to pay off in the next 6 months or a year.
I agree. And it was more strategic, I think, rather than coding near term, get an app done and try it like in a normal hackathon. But
it's good to think first.
I was going to say,
in the end, I'm perfectly happy with that.
No, when you hear the word hackathon, normally it's done in the CS community to say, come in, you didn't know anything about this tool, you learn the basics and you prototype a very simple app. And that has its value. But in here, everybody knows SU2 in some senses. And there was no point in, we know that we can't spend 3 hours and make a significant contribution to the code base. So I think those discussions and the strategic directions they may set are really the most valuable thing. So we may call it something other than a hackathon. But yeah, I agree.
Well, yeah, we should keep that up.
Tom, or Marco?
No, I mean, I just wanted to echo what, again, Tom and Yuan are saying about the hackathon, because it was really useful. And the other aspect that I think was kind of, crucial was the session in the morning where you gave this tutorial on how to become a developer. Talking just by, again, first-hand experience, I have a PhD student who is starting next month. She was connected and she said, fine, I feel like I can help.
Yeah.
Can be a developer. So I think that was a very, very useful and important element of.
By the way, we were just talking, all the presentations will be up on the web like we always do, but the video, well, the presentation yesterday morning and the video will be up on the web. And I think that's a resource for students that may have not watched it, that are coming 2 months from now, just so they can actually watch this and not have to wait till next year, till whenever another workshop occurs where something like this is presented. So let's get used to archiving these things. Also, these sessions today we should have on the web very shortly as well.
Maybe one comment on that. Tonight I'll take this Word doc and hyperlink everything and post it online too. I think everybody got the slides, but if not, it'll be online.
Yep.